We are all very happy to welcome you here to the symposium. And before we begin, I just wanted to give a few essential pieces of information. So this auditorium is called the Leelavati Auditorium. All the seminars will happen here. Just across, there is the new exhibition hall. The poster sessions, lunch, dinner, and coffee breaks will all happen in the new exhibition hall. Regarding drinking water, there is a dispenser right outside this room, and there is also a dispenser in the new exhibition hall as well. So there is Wi-Fi available in both rooms. You can see the Wi-Fi details over there for this room, and we have the Wi-Fi details for the new exhibition hall posted outside that room as well. And poster boards are ready, so just find a free spot and put it up. There is no ordering of posters. And poster sessions, if you have seen the schedule, they're integrated into the lunch and coffee breaks. This is so that there's literally food for thought, and you can go and discuss posters while you're having your food. So so if you see somebody with a yellow tag like this, we are all volunteers, so you can reach out to any of us in case you have any questions. And there are about 20 of us, so it should not be too hard to find one. Okay, and just to let you know, the event is being live streamed as well as recorded. So the colloquium as well, which will happen later in the evening, will be live streamed and recorded. And in case you want to pass outside or inside the research park or into the campus and outside, just show your symposium badge at the entry and exit points if you are not from within IIT Madras. Okay. So restrooms are opposite the new exhibition hall. There are signs there, and you can just follow it. So so the colloquium will be given by our visiting faculty, Professor David DiVincenzo, and this will happen in the Central Lecture Theatre, which is inside the campus. It's in the Humanities and Sciences block. So it's a 15 to 20-minute walk to the Central Lecture Theatre, and you will have a nice opportunity to walk through our beautiful campus and see pictures like this with some interesting friends tagging along. In case you don't prefer to walk, we do have a couple of cabs, but you will go outside the campus and take a more circumvented route. Okay, so for the walking route, all the volunteers will show you the way to CLT and also back from CLT to the research park for the dinner in the evening. Okay, so I think that's it from my side. I hope that all of you enjoy the symposium and have a blast. So with that, I would like to invite our head of the department for the Department of Physics, Professor Santosh, to say a few words and inaugurate the symposium.
A very good morning to all of you, to all the participants of this conference. I didn't know there's a Leelavati hall in this research park. I went to Central Lecture Theatre for the meeting, and then nobody was there. Then I called Prabha and figured out that it's in research park. So in the morning, when I came upstairs, I saw our old security officer standing there. I asked him where the hall is, so he pointed me right here. So welcome to this meeting. Welcome on behalf of the Department of Physics. I will say a few words about my department. It's a fairly large department with 54 faculty members right now, with two distinguished visiting, two emeritus professors and one distinguished professor. And it's a fairly young department. A lot of youngsters like Atreya, Titas, Siddharth, and are hogging the limelight. So I feel too old these days. So anyway, good to have such a interesting conference here. As it's a large number of faculty, means as we also research on a very large number of fields, from experimental condensed matter physics to quantum sciences, string theory, and gravitational physics and cosmology, and to say a few. Please visit the department and the campus. As he says, the campus is a beautiful place. You can see them real. You can't, not just a photograph, as Arul says. I mean, you can see. Only thing is there's a speed restriction if you're going in a cab, 20 kilometers per hour, so that's the only thing you need to. We also have a heritage center where you can walk in and see, look at the history of the institute, etc. You see a lot of these wonderful pictures. You can also visit the department, various labs and teaching labs, etc. Come interact with the people. Hope all of you have a wonderful time here. Good interactions, new collaboration, etc. Very important for youngsters. So wishing a very good conference, 2 days of interactions here. Wishing all the best for the conference. Thank you.
So now I invite Professor Arul Lakshmi Narayan to say a few words about CQuick and also to chair the first session of the symposium.
Morning, everyone. Warm welcome. Thanks, Santosh, for the introduction to the department. Atreya has asked me to say something about the center itself, and then we will get into the order of the business for the conference. The center really started along with as a center of excellence, because the institute was funded through the one of the Institute of Eminence grants from the Government of India. And there were 2 phases for the Center of Excellence. So this is one of the centers which made it to the second phase, and so we are a bunch of people across various departments, from chemistry, physics, electrical engineering, management sciences, and biosciences, and so on. And that kind of reflects in our center activity. And later on, it kind of morphed also into with the partnership with the Emphasis Foundation, who fund us generously for that. And it's good to see that, being myself a theorist, I can see the range of applications which are coming out from this, not just in quantum computing, but in various related aspects of this. So the center is trying to enable work in these applied directions as well as, of course, more traditional quantum information and computing endeavors. So, as we all know, we are also in the midst of the beginning of a national quantum mission, and IIT Madras is the hub for the communications part of that. So we are very happy to be part of that. And so our very wide range, there is a spiel out here, but I won't go into that. But let me just say that it's applying quantum computing in logistics, finance, healthcare, and chemistry. So contributing to global SDGs such as quality education. So in fact, one of our major things is conducting outreach programs, NPTEL courses. We've already had 2 cohorts which aim at the general public as well as professionals from many industries who are getting into the quantum sphere. So we are doing that, as well as supporting students who don't have enough financial resources. So we are happy to be doing all that. And just personally, as an IIT, it's an educational institution. We are probably one of the first institutes in India to begin a quantum computing and information course. And good to see that the participants, the organizers of this conference, as well as the majority of the participants, are all from a later generation, from which, who have profited from actually coming through these kind of courses, which we began maybe around circa 2010 or so. So it's great to see that, and welcome again, and we hope that you young guys will enthuse us, and it'll be a great conference. So let's get started. Thank you very much. So the first session, before tea, has 2 speakers. So let me first invite Himadri Shekhadar from IIT Bombay. Himadri, please. And I request all the speakers of this morning, and actually for the conference, it's a 40-minute talk. Please stick to a 35-minute plus 5. I will get up and twitch nervously at the appropriate time. Okay. Yeah.
Hi. Yeah. Yeah. Mm, so let me begin by thanking the organizers, Atreya, Siddharth, Titash, and Prabha, and all the others who were involved for inviting me. It's always lovely to be back in Chennai and to IIT Madras. So my talk today is going to be about quantum error correction for unresolvable spin ensembles. And the focus here would be on the word unresolvable. You can't hear? Okay, the focus will be on the word unresolvable. And this work was done mostly by my PhD student Harsh, who I think is in the audience somewhere or who's attending this program, and also with my collaborator. Should I use this? Okay. Yeah. Can you hear me better? Yeah. Okay. Yeah, and my collaborator Hoi Kon Lau at Simon Fraser University in Vancouver, Canada. Yeah. So let me begin by what do I mean by spin ensembles. So spin ensembles are an integral part of quantum technology. These could be a lot of different kind of things. You could have nitrogen vacancy centers. You could have many of these nitrogen vacancy centers that act together. It could be rare earth spin ensembles. You can also have a collection of superconducting qubits, trapped ions, you name it. Like there are a lot of different ways in which you can define what a spin ensemble is. And they often form an integral part of what are known as hybrid quantum systems. So what are hybrid quantum systems? You could have, say, a particular quantum device where you have information flowing from, say, a qubit or a processor that can be transferred, and ensembles can act as memories or can also act as other kind of devices. And sometimes you have a synergistic advantage when you build a hybrid quantum system like this. So this is a famous picture from a review paper article by Gershon-Kuritsky, where you can see you have a qubit out here and you have a diamond, and they are all connected through a microwave bus, which allows information to flow from the qubit here to the nitrogen vacancy centers, which can then store the information and use it for later purposes. They also have a lot of other uses. And in the coherent, like if you're really trying to build quantum networks down the line, this is an integral part of those kind of setups. So often that happens is, like when you're using spin ensembles, there are often classes of spin ensembles which, if you're really trying to address them, you can't resolve them into their constituent particles. So supposing if you have a collection of spin, but the wavelength of light that you're using to actually interact with each of these particles, you can't really resolve them into their So you can't call this is spin 1 or spin 2 or spin 3. You can mostly just interact with them through collective set of operations, right? And of course, even those kind of ensembles will face all kind of local and collective decoherences. And you need some kind of quantum error correction code to be able to overcome those kind of decoherences or losses in the system. So again, to reiterate, if you have a hybrid system, you want information flowing from one part of the other, you would need to ensure that even the spin ensembles that act as memory have some kind of a quantum error correction code that can account for these. So this is the outline of my talk. I'll give you a very superficial and a very surface level introduction to what is quantum error correction, what is the theory behind it, how does it work in collective states, before going on to some very curious properties of unresolvable collective states that allow us to define the quantum error correction code that we are looking at. And finally, we will look at what is the quantum error correction code that I'm trying to say. Fine. So let me begin with I apologize to members in the audience who are already familiar with this topic, but yeah, I just did it for the if there are younger students who would be interested in understanding this. Okay, so what is quantum error correction? In the classical world, error correction is primarily achieved through the notion of redundancy, right? So if you have a qubit 0 and if you have a bit which takes values zeros and ones, you can actually encode them with many zeros and many ones. And in principle, if you have an error somewhere, you can always resort to some kind of a majority voting. And that should, in the crudest sense, work and allow you to recover information. But we know that this kind of redundancy is restricted in the quantum world because of the no cloning theorem. So you can't have arbitrary quantum states that you can just make multiple copies of and then use it for any information protocol. What you can rather do is you can actually increase the number of the space or the Hilbert space that you're using to create the orthogonal basis. So for instance, if you have alpha 0 and beta 1, of course the 0 and 1 states can actually be encoded over larger qubits. And since they're orthogonal, you can always clone and make many copies of these. Fine. And then you can try to repeat this kind of an encoding. You can have the state psi, which is now encoded in a logical qubit 0L and 1L, where the zeros have many more qubits. Fine. And what is the aim of error correction then? Now supposing if you have an error, so you can see one of the qubits has actually flipped. So the question is, how well can you actually measure it without really disturbing the information? So this is called syndrome measurement. And once you have the syndrome measurement, can you actually recover the original information that was encoded? Right? Of course, like this is, again, as I mentioned, the crudest examples of what a classical error correction code is and what a quantum error correction code is. Obviously, in classical communication, classical information, there are way more sophisticated error correction codes that get away with, have a lot of other advantages and encode in much smaller spaces and so forth. But the underlying fundamental area understanding is more or less similar. Can you actually detect that error? And once you have detected that error, do you have clear operations that allow you to recover that information, right? Okay, so let's start with an example that's textbook example of what is error correction. So let's look at the 3-qubit bit flip. In the 3-qubit bit flip, this is nothing but a small circuit to create the states. For those who are not comfortable with circuit or have not worked with it before, you can actually ignore it and just follow the algebra. It's just consistent. So I've just, if I have an initial state out here, which is psi 1, I've just encoded it using 3 qubits out here with alpha encoded in all the zeros and beta in all the ones. Yeah, so you can see in some sense, again, I'm going to a larger Hilbert space, introducing some kind of a redundancy. So supposing now I have an error in the information that I have encoded. And what is that error? You can see that the last qubit has actually flipped. Right? What is the easiest way to detect if there is a particular qubit that has flipped? You can actually set up these operators, Z1 and Z2, Z2 and Z3, and then actually measure the two. So if both of them have the same sign, you get back +1. If both of them have opposite signs, then you get -1, right? So detecting -1 in this circuit out here. So if you have 0, it will flip to 1 if it's -1. That will allow you to say which of these bits or qubits have actually flipped. And once you can detect it, you can, so this is the algebra, of the entire circuit. You can see Z1, Z2 on the error state will give you +1 if there is no error, will give you -1 if there is an error. And depending on the error, you'll get an outcome. And then you can use this outcome to directly correct for whichever qubit has actually flipped by just simply applying the X gate and flipping the qubit back, right? Okay, so those who are more familiar with quantum error correction, they'll realize that these are nothing but stabilizers for this particular code. You can write this in the stabilizer formalism, and stabilizers are states that have eigenvalues +1 and -1, and -1 corresponds to the error syndrome measurement, and +1 keeps the basis state as it is. So similarly, you can also write down a code which can detect a phase flip. Instead of a bit flip, you have the phase of one of the qubits changing. But importantly, at this point, I should highlight that this would not work for an unresolvable qubit. And the reason for that is, as I mentioned earlier, in an unresolvable qubit, you really don't have any mechanism to target any specific one of the qubits. All the operations that you're doing or detecting are all collective operations. You can't separate out any bunch to do any measurements. You can't actually target any one specific qubit to do any correction. Fine? Okay, so how does quantum error correction work? What is the theory behind it? And in the simplest sense, let us see what an error does to an encoded information. So if you have alpha and 0, and you could have 3 possible bit flip errors, right? So you could have the first qubit flipping, the second or the third qubit flipping. And what you need to demand is each of these states where the error has taken place, they remain orthogonal to each other. If they are not orthogonal to each other, if you're making a syndrome measurement, you really don't know which error actually brought you to that particular state. So this is a nice picture taken from Nielsen and Chuang. You can see a nice error correcting code is one in which if you have encoded your information in a particular basis and you have a whole set of errors, they actually take you to spaces. So it could be rotated in the space, but they all go to distinct regions in the Hilbert space that are all orthogonal to each other. Unlike the top picture here, you can see here they are not only twisted and the norms have changed, but they also have overlap with each other. In contrast to a code, which actually takes them. So now what happens is, if I try to make any measurement out here, and I can identify one of the errors, since it's distinct from everything else, I can always plan a recovery map that will take me back. And at the heart of any quantum error correction code are these set of conditions. And these are popularly known as Neal-Laflamme conditions, but David mentioned it to me a while back that he had partly worked on some of these conditions before the Neal-Laflamme conditions, so maybe, and other people, including other people. So it's also known as the PEEP condition. You can see that the projected code space goes to an orthogonal set here, right? So whenever you are coming up with any quantum error correction code, these are the set of conditions that you would ideally want to satisfy to ensure that you have a suitable syndrome measurement as well as a recovery process. Okay? So let us take an example. So the first example we looked at was simply a quantum circuit. We were encoding it into just zeros and ones. Let us look at a slightly more physical example. Say we have a harmonic oscillator, and I want to encode some information in the levels of the harmonic oscillator. So simple way of encoding would be is I encode the logical 0 in 0 and 4 and 1 in, say, the level 2, and I just consider one kind of error. So this error correcting code can only help you with a specific kind of error, that is photon loss. And when there is a photon loss, you can see that they all map to odd parity states, and they are all still orthogonal to each other. So in principle, you can always find some unitary that will take you back, right? So you can make it a bit more. So I've just noted down the algebra that shows that all the Neal-Laflamme conditions or the general conditions for the quantum error corrections are satisfied. So I can also make it a bit more complicated. I can say that not only photon loss, I also want to protect against, say, dephasing errors. I just need to come up with a different encoding scheme, and that encoding scheme would look a bit different. You can rework the Neal-Laflamme conditions and still check that they are all satisfied, which tells you that there exists some kind of a recovery map that you can think of. Okay, so this is my very crude and superficial introduction to quantum error correction theory. But the point I'm trying to get across is if I'm someone who's trying to come up with a new quantum error correction code, these are some of the entities I have to keep in mind that it is satisfied at any point. Okay, so next thing is what are some of the curious properties of unresolvable collective states that you need to keep in mind when you're designing a quantum error correction code? So what do I mean by spin ensembles? I gave you, let's look at a slightly mathematical perspective. So by spin ensemble, I just mean a collection of spin half particles. Right? They are all identical to each other. And for our purposes, if there is light interacting with it, they all interact collectively with the light. So I can always write it down in the up and down basis, right? Just the m values of each of the spins. And any arbitrary state would be nothing but a superposition of this. Okay? But I can also actually write it down in the total angular momenta basis. Yeah? So instead of writing it down as in this, so this is typically nothing but the computational basis if you think of plus half and minus half as zeros and ones. So instead of writing it down in the computational basis, this entire thing has a representation in the angular momenta basis, where J and M are the angular momenta and the magnetization. As we already know that J max is n by 2, where n is the number of spins that you have, and J min is either a half or 1 or 0, yeah? So, and each of these J's actually have a degeneracy, okay? So for each of the specific J's, so if J is maximum, you don't have any degeneracy, you get what are known as the decay states. But for any other J values, you actually have a degeneracy in the system. So let us look at an example. So if we just have 3 spins, the J can take values 3 by 2 and 1 by 2. So 3 by 2 is the maximum, the degeneracy is just 1. And then you have 3 by 2, half, and minus 3 by 2 as its magnetization states. But if you look at J half, you can see there are 2 states which look exactly identical in terms of J and M, but they are marked with degeneracy 1 and 2, because I need to keep the total dimension of the system the same. But for all purposes, these, in terms of J and M, these two look exactly the same. Okay? So what do these states look like? I can expand it. So this is the J 3 by 2 sector, and these are the degenerate J half sector. So the first part is nothing but the symmetric decay states, right, that we are familiar with, where you have like all states down, then you have one excitation, the W state, one excitation, which is across all particular possibles, then you have the 2 excitation, and then all excitation states, right? And then you have the non-symmetric states out here, non-symmetric space. Now, yeah, so before I proceed, one thing is all the J space, they don't really typically form, they are like irreducible representations. They don't form coherences between each other unless you really create coherence between them. You really don't have a unitary that would take your information and put it to different J sectors. They are like different blocks in your Hilbert sphere. The key thing that happens is, now if I have an unresolvable spin system, in any ensemble where you can't address any of the individual spins, there is no way for you to actually detect which of the degeneracy you've actually chosen. So for any light that you shine on it, all the J and M all the degenerate states would behave identically. Yeah? To separate out the 2 degenerate states, you actually need to manipulate the spins at an individual level. In the collective regime, you can't really do it. So you can rewrite all of these states in a different form. So if you have a general density matrix, that's actually lying in it. And you really want to maintain what is known as the permutational invariance. If you shift any of the spins, the permutational invariance should remain the same. The best you can do is you can actually write a density matrix, which is actually, the overbar means it's actually diagonal in terms of the I space that you see, right? So it's as if you're talking to it, all the I's would behave identically in terms of how it's behaving to any interaction that you're providing it. Okay? And this reduces, so this is helpful for a lot of us who study quantum dynamics, cavity QED, and things like that. This degeneracy actually reduces the dimension of the Hilbert space, say from 4 to the power n in the mixed state to order of n cube, right? Yeah, so again, yeah, you can write it in terms of blocks out here is the same thing. I'm just showing it pictorially. And another way of representing this would be, yeah, you have these different sectors corresponding to different j values, right? From j n by 2 all the way up to j equal to 0. Okay? And yeah, as I mentioned, these are irreducible representations, and typically any process, any unitary process would not create any coherences between them. Fine. So let me go to the final part. So how do we encode information in unresolvable spin systems? And the question you can ask is, why are you actually trying to do this? I'm sure people have already worked it out. Like collective states have been around for quite some time. So I'll tell you like what the issue was and why we felt it's necessary to redo this thing in the first place. So let us look at this diagram again. And this is a Lindblad equation. It looks mathematically complicated. People who do not know open systems, what I'm just representing here is, this first part here is just the unitary evolution of any quantum system, right? And the other things just represent different kind of losses that you can have in the system. So the top row out here represent losses that are collective in nature, right? So that act collectively on the ensemble. And the bottom ones are losses that can have individual losses in an individual spin, but nonetheless in a permutationally invariant way. So you really don't know which spin is coming out, but it's an individual spin loss. So these losses act on the collective space in different ways. So if you have a collective emission, if you have a state encoded in any one of the levels, all that will happen, you'll just come down. If you have, say, a collective pumping or an excitation, it'll just go up. And if you have a dephasing, you just stay within the same M sector, right? So there's something really nice here. So if I were to tell you that I really need to just work with collective losses in the system, then you really don't need to do all of this. You can just encode your information in Jn by 2, and you'll know all your processes. There is no unitary process that will take you anywhere else. There are no losses that will take you anywhere else. So you can actually throw away the entire non-symmetric space, and you can write a bosonic code or something only in the J into n by 2 space, right? But now if I have losses, yeah, so collective losses keep J unchanged. Yeah, and so you'll find a lot of QEC codes that use collective states, which are just limited to that particular sector. It'll look like a bosonic code similar to the harmonic oscillator code that we looked at earlier. But what happens if you have local emission? So if you have local losses, like the terms in the bottom, you can see that if you start with any one level, there's a possibility that your J can actually change, right? Again, if you have a local pumping, J can change. If you have a dephasing, even though M remains the same, you can actually move to a different J sector, right? So now you can see that the J is not really conserved. You can move to different spaces. So local losses, so these are local losses that still keep the permutational invariant intact. That can actually affect the way in which your J changes in the system. And these are integral part of most of the dynamics. Like it's very difficult to say, like you have systems where you've completely discounted individual errors in your system, okay? Yeah, so what are the questions now? So supposing the key questions that we want to address is addressing individual spins is practically challenging in a lot of setups. you want to have a setup where you can get away with collective. You shine a light that's shining on the entire setup and is doing all the operations for you rather than having fine structures which target anything. So there are a lot of setups where it's barely impossible to do it, or it has only been recently done. Again, in this particular space where you can have losses that go, coming up with a QEC protocol can in principle be a bit difficult. And again, a lot of the local losses are actually not corrected. Fine. So, yeah. So how do we go about defining a quantum error correction code? So one thing you have to keep in mind, the key information that I mentioned is, if I have to encode information not in Jn/2, but in any of the other J sectors, I have to deal with a set of mixed states, right? Because they are mixed due to the degeneracies being written in the mixed form to keep the permutational invariance intact. So I can encode a qubit in any one of the J levels, but this qubit has to be encoded as a mixed state, right? But nonetheless, you can always define a logical qubit. It's just that you have to make sure that you've not approximated it to a pure state and written the qubit down. You have to write it in the form of a mixed state. So in principle, there's nothing tricky happening here. It's just like a bunch of pure states that all act identically. Okay? So once you have done that, you can try to encode a logical qubit in any of the J spaces. So now I have converted the mixed state language into a pure set language by just writing a psi L. And alpha 0 and alpha 1 I can write. So where 0 and 1 can be superposition of any of these M states, right? But in the back of your head, you should say that this encoding is actually in the mixed space. Okay. Now the key question that I need to say is, if I do an encoding like this, do I get away and can I satisfy the Neal-Laflamme conditions that so if I can't satisfy that, then that would already give me a hint that I'm unable to perform any error correction in the first place, right? So supposing, what do I need to do? I need to write down the Neal-Laflamme conditions for all possible set of errors that could have happened. So all the errors that we looked at in the first place, I can write them in the form of some Krauss operators and try to see if I apply the Krauss operators to these logical qubits. So representationally, it looks like this, but it's a lot of algebra saying, looking at the mixed state structure and how error acts on those states. And then just say for an example where I want to use 2 levels for encoding 0 and 2 levels for encoding 1, I can try to find out what are the conditions which allow me to satisfy these, right? So doing a lot of the algebra, you can find out that the way you need to create the superposition states for the logical qubits, you'll get a set of relations. So these are just the set of relations that define how your logical qubit superposition should look like if you want to store, say, the information alpha naught and alpha 1 in the logical qubits. Okay? Then, yeah.
It seems to be a modified form of the connection because of this race, or am I?
No.
You have to know test for these mixed states.
Yeah.
So
Yeah. So these conditions are just to do that. So it's the expectation values that you have, you can just writing it as a trace. Right? You mean the Neal-Laflamme conditions? Yeah. That's easy to. That I think like people have done. Okay. So there are a few quantities that I get. So I have a J threshold of 9/2 because I need at least 4 levels which are all separated by 2. I need to keep this distance 2 because if there is an error, it will bring one of these M's down. And there could be another error that takes M2 up. So as long as there is a single error taking place, they should still remain in distinct spaces. And if I need to have at least 4 levels with 2 spaces each, I'll need at least 9 spins to encode that information, right? I can't go below that. Yeah. So the number of spins that I need has to be greater than or equal to 9. So how does the encoding look? So now once I know what the Neal-Laflamme conditions are, this is how I would go and write down what my logical qubit 0 is, and I'd write down what my logical qubit 1 is. So again here, the reason I get this relation is because I started by saying I'll just use 2 levels for 0 and 2 levels for 1, and I worked out these conditions. In principle, you can even say, oh no, I want a much more robust code. I would use higher number of levels to encode 0, higher levels to, and you'll get a different set of relations to do the same encoding. Okay, so now we need to find out what is the action of collective losses on the state and what is the action of local losses. So you can see, as we mentioned, we showed it pictorially before, if you are in any jm prime state, the action of a collective loss would take you to jm plus m or m prime plus m. You can see that for collective losses, the j actually does not change, and these are the coefficients you can actually just calculate. If you have local losses, your j can change, your m can also change, but once you have encoded the information, you really can calculate what all of these loss terms are. So you algebraically know what these terms would look like. So what I'm hinting it as, now that I know what the Neal-Laflamme conditions are and they are satisfied, and I also can estimate if there is a single loss error, what it would look like, right? So I know what the terms are. If I can successfully detect what error has taken place, then I can always come up with a recovery map that will allow me to do it. Yeah.
So you also said there is an internal index for less than maximal j, right? So the internal index is also changing under these processes or not?
What is the internal index? Sorry.
I label that you have.
Yeah, so what I'm saying is the I you can really get away with, because the collective will never address any of the I's individually. So they'll just, it can't touch any of the I's. So you,
Even the local losses,
yeah.
that doesn't change.
No. So you'll need individual addressing or individual errors. Individual in the sense that something that breaks the permutational invariance. Those kind of measures can actually detect the I. Because collective would only look at the J and M, right? And the J and M would always look the same for all the I's. Okay, so how would I go about it? So supposing I encode any information, alpha naught and alpha 1. Yeah, just think of it as alpha and beta, and I'm encoding it into some qubit. What does that mean? I have this logical qubit here, and then I choose this set of M1, M2, minus M2 minus M1 to encode the information, right? And say I now have a particular loss that takes me to a different j. So this is j minus 1. It could also be j plus 1. It has taken you somewhere else. Then I can make a syndrome measurement based on phase estimation of j square and jz. Like there are different ways depending on the platform you can try to do these measurements. You can do a phase estimation algorithm that would estimate this for you. And once you do it, you can actually then try to apply a recovery process. So this recovery process looks a bit complicated. I think Harsh has worked out a slightly simpler version of a recovery process, which looks physically way more neater. But I think in terms of implementation, it's equally difficult. But you can apply this set of unitary operators that would take you back to the original information. So I'm not highlighting what these operators are because it's nothing but algebra. If you pick up the paper, you can find out what these are. But in principle, you can always come up with some kind of a collective operation that would take you back to the original state. Yeah. 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 So for us, what happens is the idea is just to recover alpha and beta. So even if you move to a different j, as long as you can get back the original encoding that you had earlier, that should work for us. So, so in the next slide, they'll become a bit clear because, yeah, so the point that was raised is, what has happened is I've actually gone from j to a different j, but I've recovered the information in a different j prime. And since I encoded all the information in mixed states, this works for all possible j's that you have in the space. Okay? So now I can decode and get back what the original information alpha and beta was. Yeah, so let's look at some simulations of it. So this is a very just n equal to 20 spins. So j is equal to 10. And if I have an encoding like that and I compare it with the unencoded information, but at the lowest levels. So there is no excitation out here. It's just lying at the lowest levels. So you can see, if I look at a specific kind of losses, so the encoded state without any error correction actually does very, very poorly, right? Whereas the unencoded state, which was just done in the less excitation, because there is no excitation in the system, it actually stays fairly okay. If I now apply the error correction code, okay, so the same thing that I mentioned. If I now do multiple rounds of error correction, what I get is this black curve here, right? But the reason it drops off at a particular point is because if it keeps moving to a J value after which you can't encode it anymore, so after that the information just starts tailing off. So one way of coming out of this is, of course, you can really go to a high J, for which it will take really, really long for you to actually hit the threshold and lose the information. Or you can alternatively think of as, once you've hit the threshold, can you actually do a teleportation protocol that will allow you to encode the information back into one of the higher J levels. And if you allow for that, then you can see that you can satisfy all the conditions, and ideally you can have a perfect encoding that just stays in place. Okay, and you can also look at it for so you can also look at for other values, other kind of errors, and these are just quantum trajectories that have been solved for different kind of errors that could have taken place, and the calculations are done. Sorry. So, in conclusion, I'll end. So, what we discussed here is a quantum error correction for unresolvable spin that protects against all physical errors that you typically see in light-matter interaction, in cavity QED or quantum optics. Actually, this can also protect against particle loss in the system. Syndrome and recovery. So all of the processes that we've used here are all collective processes. We do not use any individual addressing. So it keeps the unresolvability part intact. And you can also use this formalism to extend it to something like sensing. And we think like, yeah, you can design, it's an important step in designing protocols for quantum information processing. Yeah, so I'll just take 1 minute. So since this is, I think, Atreya and Titash, you mentioned that one of the main aims for the conference was collaborations and to build. So I'll just take a minute to say what other work we do in our group. So what we mainly work is this cycle. So this is something I've been showing since my PhD days, I think, so, or my postdoc days rather. So our interfaces between quantum information and computing, many-body physics, quantum optics, and recently more on collective states of light-matter hybrid quantum systems. So I'll quickly flash the group. We are the PhD students, some EP students. So Harsh and Prakriti, they are here. And you can also talk to them and interact with them of the kind of work they are working on. Some funding agencies. Okay, maybe I'll skip this slide. And so some of the problems that we are working on, we are really focusing on how you can do quantum information with collective states and how they interact with, say, information that's flowing from a different part or a different physical system, and how do you work out, like use that for sensing or memory kind of operations. So if you look at the kind of questions that we are looking at in terms of projects, we work on quantum information dynamics, cavity QED. We use methods like tensor network and other kind of algorithms to actually simulate these systems, mainly to see if you have random information, how well you can store them, you can protect them. We also have one of my PhD students who's working on sensing and atomic BEC and hybrid optomechanics. And in both these projects, the main aim is you have a lot of physical systems in which the interaction can be broken down into quantum optomechanical-like interactions. And then once you have quantum optomechanical-like interactions, you can bring your entire toolbox of quantum optics and beat the problem with it. And that allows you to get some nice insights. For instance, this interactions in atomic BEC, also in magnons and other systems. And yeah, and another direction that we look at is what are known as continuous variable systems, and how you can look at protocols such as teleportation, telecloning, and other communication protocols in the continuous variable regime, specifically using non-Gaussian resources, and try to understand how these resources compare to similar resources in discrete level systems. And finally, the work that we are doing on quantum error correction. So with that, I would like to say thank you.
Thank you very much, Himadri. Maybe just 2 questions.
So for that, so the permutation symmetry is broken at the trajectory level, right? If you
No.
have single local losses, you're only thinking about the density matrix where the permutation symmetry is still there.
No, if it's so the losses that we've written down are, so if you see, it's a summation over I over all integers. So you really,
Yeah.
at any level, do not know which single loss has taken place.
Yeah, but in the actual dynamics,
No,
so
it would not affect. Yeah. So permutation symmetry would only be broken if you somehow identify one of the spins and separate that out.
at the trajectory
In the trajectory level,
happen
it will
for
happen,
individual spins,
because
right? So
individually
it's-
they are breaking. So, yeah. So exactly at the trajectory. Now, supposing if I'm trying to resolve something,
Yeah.
and I need to flip one particular spin, so that would mimic a system that's similar to a trajectory.
Yeah, but in a single
No.
trajectory in an experiment, if individual spins flip, you don't
Yeah.
know which one flips.
Which one flipped? Yeah.
But
so that
the
keeps
operator
it
is
intact.
there to flip individual
Yeah.
spins.
So that keeps it intact.
But the unitary that you're applying at the end,
Yeah.
will that have to be modified based on the
No,
trajectory, or
no.
you think okay?
So it's all collective. Yeah. Because I'm just detecting what the JZs are, right?
So when you initially encode the 0 and 1, because it's an unresolvable spin ensemble,
Yeah.
is it correct that you can only start in the j equal to n half space? You don't have a choice.
Yeah. So, yeah, I think I should have addressed that in the beginning. So we are working on a different project on that. So what we are trying to do is, you have these driven dissipative coherent schemes, right? Like where you can apply selective unitaries and dephasings to create a desired state. So in a different project, we are seeing that if you are in the permutational invariant state, how do you create an arbitrary superposition in any of this space? So it's a bit more involved. So you need to, so we can start with either with all the spins excited or all the spins bottom, and then selectively drive them and couple them and take them to different spaces.
Okay.
Yeah.
Okay, thank you very much. And
Yeah.
Next speaker for the morning is
Can I take this bottle? Thank you. Hey, thanks, Arun. Oh, sorry, yeah. I gave it to him on a stick.
keep an eye on that.
Yes. Yeah, I'll finish faster. Should we connect using on the other side? Oh, sorry. That's what I wanted to try. Right. Okay, yeah. So I would also like to start with thanking the organizers. This is my first time in Chennai, so I'm very happy to be here. I also want to see the labs in IIT, so very excited to also talk to other people. So, so the title of my talk is towards a microwave quantum memory based. So microwave quantum memory based on ensemble of electron spins. And Himadri has already introduced ensemble of electron spins. They are unresolvable. Yeah, sorry. So you cannot do operations on them on individual spins, if you like. That's not possible. But we can turn them into resources, and that's the thing I'm going to show you. So I'm an experimentalist. So I started 2 years ago in India. So that means I should have no results, and that is true. So I'm going to present most of the work which happened before I joined TFR Hyderabad. But I'm very happy to show you a few things. I think the USB for the pointer is missing. I think it needs to be plugged in. Yeah, I can do it. Yeah. Doesn't like it. Okay. Well, I'm not too far from here, so I'll just. Okay, so this is my lab. It's still in progress. We got our dilution fridge. You can see here. So most of the wiring we got it intact from Blue Force, but we have to do still plenty at the bottom. When this is done, I'll take a zoom in, but at the moment it's empty. We have already started few characterizations. For example, this is 3D magnet, which is the important thing about this dilution fridge. And you need the magnetic field to create states in the spins. Yeah, so the control rack is just in the next room. Through this hall, we can get all the coax cables, and yeah, now this lab is not empty. There are a few students who work there. Okay, so the first experiments that I have already started doing was we took some resonator from Collaborator and put them in this fridge, just do continuous wave measurements, and this is what we see. Just a bare resonator. This is on Sapphire, nothing special, just a resonator. You measure the quality factor, or kappa here. As a function of magnetic field, you start to see some features. And this is the idea: when you measure at very low temperature, 10 millikelvin, your sensitivity is very high using state-of-the-art amplifiers and all these things.
So in this case, there are 3 peaks that you should be able to figure out what they are. There's a central peak, which is spin 1/2, because this is G is equal to 2 spin, that you can find in almost all kind of substrates. So this one is sapphire, and you have, you can all sorts of dangling bonds and things. The special thing is this 2 satellite peak, and you see when you measure several of those resonator, you will see them. They're always separated by 1.42 gigahertz, and this is the hyperfine coupling of hydrogen, right? So hydrogen nucleus with electron. Okay, so this is not what I'm going to actually talk about. This is just one of the first things we have done in the lab. So now I'm going to switch gears and talk about quantum memory. That is the title of my talk, right? So I want to use electron spin ensemble, which I already introduced, as a modular quantum memory. So what do I mean by this? So quantum processor, for example, these days, based on superconducting circuits or spin circuits, or other kinds of platform, they're quite successful, and they're very good at processing. So the gate times are really, really fast. But the downside is their coherence times can be quite low. So our idea is, can we couple these systems in a modular way to another a system called quantum memory, for example, based on electron spins that inherently can support very long coherence times. So here are seconds, but can also go to minutes and even hours if you use nucleus spins. Right? So the idea is to combine best of 2 worlds. Again, this idea is not very, it's not original. Even in classical computing, you have different material platforms for processing and for memories. Right? You always want to have the best of things. Of course, Himadi also introduced quantum error correction, and a lot of people would also think, like, is this even needed? Because people have started doing quantum error correction quite nicely in the labs. So this is one of the examples of quantum error correction. This is called surface code, where each qubit has 4 neighbors. And you can detect these error syndromes, X and Z, by pair of these qubits. And this error syndrome must not project the qubits, so there are parity measurements that must commute. So all these things, they work. And of course, the idea here is, even if your qubit is very, very noisy, you can encode into larger and larger space of a logical qubit, and you should be able to achieve, let's say, like infinite lifetime of your qubit. But that's all good on paper. Like when you go to lab, when you start doing experiments, already scaling from 2 to 4 to 8, and once you go to 100, you say, okay, I don't know how to proceed more. Like, it's too difficult. So I'm not saying we want to eliminate this, but is there a complementary method, or can we work together, right? So just to give an example, right? So quantum error correction recently has been shown for the first time below the. Oh, now it started working. I'm going back actually. So below the surface, and so I said, like, what is this threshold, by the way, right? So I know that you are encoding into larger subspace, and you're trying to protect the fragile nature of quantumness of your qubit. But more redundancy you create, those qubits also should have errors, right? So that's why there's this break even, and there's this threshold that you have to always beat. So we think if we can do this, right, like we can couple to this, we can, let's say, not eliminate quantum reaction, of course not, because that's quite useful, at least at the very, very fast time scales. Maybe we can work together and, like, instead of having 100 qubits as one logical qubit, maybe you can have 100 physical qubits can make more logical qubits, 10 or even 100 logical qubits. Right. So the idea is to, again, couple such processing elements to a memory element, which is based on, let's say, electron spins in this case. And this memory, like that can be memory for all the qubits of the processor. Like, so if you have thousands of them, you don't need different qubits to couple to different memory elements, but all of them can talk to the memory element. So that way, you will reduce overheads, right? Also, these are going to be very passive, right? So you store states and get it back. So there is no like power handling kind of problem that you will have in larger processing units. You will also improve connectivity. And even if you say, let's say I'm never going to use quantum memories for this, what is definitely going to be useful is, for example, spins in solids, for example, they also have microwave to optical conversion. So if you have this, you should be able to interface different processors, because there's only so much cooling power that you have in one dilution stage, and if you want to connect several of them, this should be the way. Right. Okay, so that's the outline of my talk. So we want to realize this quantum memory based on electron spins. So what are the things that we need? Of course, we need to have long cadence times of electron spins. So we are going to couple those spins, very similar to how we do in magnetic resonance. So electromagnetically to a lumped element resonator. And this resonator itself is going to be connected to your measurement line, let's say with some capacitor. You're going to send in your states that you want to store. And by using a combination of control pulses, you can get them out, right? So your data pulses, you get them out. And this will go to your, let's say, the qubit processor. Yeah. Okay, so that means, like, yeah, we need to have a strong coupling to those resonators, ideal control pulses. And the most difficult things are the bottom two, random access of storage and retrieval. So once you store your states inside, sorry.
Sorry, the electron spins, so where are these in the material?
Yeah, so yeah, I have worked on a variety of systems. So in few cases, we have them directly inside the substrate. So for example, you take silicon, not sapphire, but silicon. You can, for example, you can implant bismuth in silicon. That works. Like that's a group 5 and sits like a dopant, right? And it's a solid state dopant that sits perfectly, bonds with other silicons. The other way you can do is you can have your resonator chip or any chip, and then you flip chip your spin where you want it, where the active area is. You can also do that. Yeah. So this is just the circuit diagram of how they couple. Yes. Yeah, and again, the difficult thing is also the unit efficiency. So you want to do all these operations. So you want to, when you get your state, they should be stored like at 100% fidelity, and also the other way around. Right. Okay. So there are several flavors of quantum memory. At least in optics, it's quite different from how it's done in microwaves. In microwaves, we do memories based on Hahn-Echo protocol. So I thought I'd just show you what Hahn-Echo is. So in pulse ESR or pulse magnetic resonance techniques, you have this sequence where you apply a pi/2 pulse. You wait for a duration tau, then you apply a pi pulse, and then after the same duration tau, you see what you call an echo because your spins they rephase back. So that's shown also here in this cartoon. So you start from this north pole with 90 degrees, you bring it to the equator, your spins are dephasing, right? Then after a time tau, you flip all the spins, and then the spins again continue to evolve, and then after the same time tau, they come back in phase, and this is when they detect echo. Right? So when you increase this time tau, you can see that this echo will die, and this is what we call decoherence time. So what's happening in this kind of experiment is you're rephasing the static inhomogeneity of any field or any other things experienced by the spins. But anything that's dynamic that you cannot rephase, of course, then the echoes will die. Right? So in our memory experiment, what we do is typically just replace this pi/2 pulse with your input pulse, and then the idea is that just with the same sequence, you can get this thing back in the echo. Okay, so when we started this project, or when I started working on this a long time ago, so one of the first questions that was challenging at the time was, how do you couple to low-loss superconducting resonators? So the field was still evolving, and you see, like, you have to put all those spins in a magnetic field. Superconductors don't like magnetic field. Also, spins, they couple rather weakly to electromagnetic field, right? So we started working on niobium titanium resonators, which turned out to be very robust to be magnetic field, especially for the fields. If you just apply parallel to the plane, you can easily reach fields in Tesla. And for electron spin resonance measurements, anything of the order of half a Tesla is good enough. So one of the first experiments we did was using a diamond, mostly because we had the diamond somewhere in the lab. And this diamond was full of these impurities called P1 centers. So I know a lot of people know NV centers, but P1 centers, they're just the precursor to the NV centers. So you need these impurities first, and then you can create vacancies, and then you get NV centers. So basically, if you're working with NV centers, you should also have these ones. Right? Except these are not optically active, so you cannot detect them optically, but in microwave, you can do it. So these kind of impurities, they have spin half, and they also have nuclear spin 1/2. So this is, in the Zeeman basis, it will just look like that. You have 3 transitions. So this is exactly what we get. So we sweep the magnetic field and also the frequency, and especially exactly around when the resonances are supposed to happen, you start to see very beautiful avoided crossing. This is the reflection of strong coupling between your resonator and spin. So the magic we did was nothing. We just took a lot of spins. That's it. There were lots of defects in this crystal. This was of the order of 200 ppm. When you use a lot of those spins, you get enhanced coupling, and this goes as, I forgot to put it here. This G ensemble is one coupling strength, G naught, multiplied by square root of n. This is the square root of n improvement that you get with ensemble of strings. Right. So it was nice to see that things work, but coherence-wise, we didn't see anything. So we did an echo experiment, and actually we couldn't actually find the echo, right? And the reason is the following, and this is again down to the spin concentration, or like the number of spins that you're using. If you're using lots and lots of spins, the problem is that the spins that you are talking to, let's say the pink spins, and there are lots of neighboring spins, they can still flip-flop. This flip-flop, right, it conserves energy and takes nothing. They can do this all the time, right? And that's going to create a fluctuating magnetic field for your spins. So this flip-flop doesn't even need to be the same spins as you're measuring. It could be even nuclear spins or any kind of impurity spin, right? This flip-flop is always going to destroy the coherence of your spin. Even with the same spin, you can have direct flip-flops. This is more like a T1 process, so that spin goes out of the Hilbert space, right? You can say you can avoid these things by going to lower concentration, but then you will not even measure anything. Even the worst problem is so-called instantaneous diffusion. Yes?
So in a lot of recent experiments, there is this critical density before to have sufficient N so that you get strong coupling, but not dense enough so that you don't get spin-spin interaction. So is there some number that you can?
Yeah, so actually my flow of talk is to just avoid this thing altogether. So you will see in 2 slides how we can circumvent all these things. Yeah. Okay. So the second thing is, this instantaneous diffusion will be hard to avoid. So you always need control pulses, right? Especially pi pulses, and pi pulses are not good for the spin evolution. So what happens is, for example, in this Hahn echo sequence, so after pi over 2 pulse, you apply a pi pulse. So what this pulse does, like this flips like all the spins, right? But for the central spin, it will see, like the first half of the evolution, it saw that the spins were all up, and it saw some magnetic field, but for the other half, it saw flipped spin. So it's seeing different spin environments. Of course, the evolution in this case and that case cannot cancel out. It sees different spins. So the way to check this is just vary this angle. So instead of applying pi poles, just apply different thetas. For example, if you apply a smaller angle, you only flip few of them, then the central spin doesn't really see much change in magnetic environment. So if you plot 1 over T2 as a function of sine squared of theta, you will see this linear response, which is exactly what is predicted for this instantaneous diffusion model, right? So C is the concentration. So here I have plotted for different gyromagnetic ratios. So gyromagnetic ratio is really the slope of the frequency with magnetic field, d omega by dB. And different curves here are for different bandwidths of the excitation. Basically, what I'm simulating is different concentrations. So that's the slope you get, right? Everything is fixed. So this thing you cannot avoid. And you want to have pi poles. I mean, there's no other way. Yeah. So how do we avoid this? And of course, we have to avoid this. That's why there's the next slide. And that is by using so-called clock transitions. Right? So this is the nice thing about spin systems in solids. So how do you find them? So what are clock transitions, by the way? So clock transitions are these sweet spots in transition frequency. These are the sweet spots. So where the first derivative becomes 0. At least to the first order, the derivative of frequency to magnetic field is 0. That just means it's, at least to the first order, blind to any magnetic noise, which is around those central spin. So it will be blind to any indirect flip-flops or instantaneous diffusion. Right? How do we get this transition? So you have to look for a system where you have strong hyperfine interaction. So luckily we have this bismuth spin, which is quite heavily studied. It was studied back in 1959 in ESR context, and has a large spin number, and also hyperfine coupling is like 1.47 gigahertz. So it gives you two very nice things. It gives you a large zero field splitting, which you can use if you want to, but the most important thing is it gives you a bunch of clock transitions. So basically your large hyperfine coupling strength is competing with Zeeman splitting, and then of course you will have a turning point, right? So this we can check experimentally. So this is the same transition, electronic transition as a function of magnetic field. I've just plotted the zoom in. This is the transition that I'm measuring. This is the resonator. And as you can see on the right axis, I have plotted the echo time. This is single pi pulse echo time, coherence time. And as you go across the clock transition, which is here, you see the coherence time goes up, reaches a maximum, and then comes down. Right? This is what we expect from clock transition. And then the value can reach, in this case, reached as 300 milliseconds. But we can we further showed that by using dynamical decoupling, this kept increasing, to at least a second, till we couldn't do more experiments because phase cycling is a very difficult thing in ensemble of spin. Right? Basically, what I wanted to say, that was not limited by indirect flip-flops. So Himati, I think that was the question that we can just totally get rid of that question about what should be the density that we should be using. So as long as we're not limited by, let's say, direct flip-flops, I think we are already good. And also, the samples that we prepare, they have surface states. Those are also very difficult to avoid. But in this case, we have gotten rid of them because it's just blind to magnetic impurity, at least to the first order. Right? Okay, so I said echo-based quantum memory. So the kind of experiments we first did, you can send like a train of pulses. In this case, it's not coupled to any qubit. So these are all proxy states, so low power coherent states. We send with different phases. You just apply one refocusing pulse, you get all of them back. Sorry about the noise. But you have to appreciate that all the states that are back contain only 0.03 photons per echo. So although it's noisy, actually it's a very difficult measurement to do. So these are all done using quantum parametric amplifiers. Otherwise, you'll not be able to see anything. So that was not the problem that we had a lot of noise. The problem was the retrieval efficiency was really still rather poor. So in this case, the efficiency was 0.04. Again, that's just related to the number of spins we use. It's not related to concentration. So the spins we used in this case, there were only like 50 to 100 nanometer implanted below the surface of silicon. So if you can just extend it to a micron something, you should be able to get unit efficiency. Okay. So this was nice to see. It preserves the phase. You're able to do the experiment to show that there are multi-modes in the spins. That is also very essential, right? Like spins. If you use ensemble of spins containing millions and millions of spins, you have those million modes. Okay. So what is the other bad thing here? So all states are retrieved as first in, last out, right? Look, so this one comes here and the two. This is just the retrieval is just in the reverse order how you put them in. I mean, this is good for demo, but it's practically useless. Right? You want to store all of them, and you want to get them as you want. Like I want to get, let's say, the fourth state first, and then the first state, right? You want to get them in a random order. Right? This is one of the challenges that we want to work on. The second thing is, see, one thing I didn't tell you: refocusing pulse. Of course, refocuses the spins. But refocusing pulse puts all the spins in the excited states, and that's an inverted state, right? So now you have problems. There are two problems. First, you can have superradiance that Madhuri briefly touched upon, and then you can also have some mazing effect, because that is going to fall exactly on top of your echo, right? Any spontaneous relaxation, and that's going to cause mazing. Right? So this you don't want. And the solution to both problems is to start doing so-called echo silencing. So we don't want to get rid of high pulses, but we want to get rid of the emissions. So generally, you would have emissions right after this time, tau. But by echo silencing, if we can manage to get rid of this, for example, by detuning the resonator, another pi pulse, you should be able to get back the same state, except now after application of 2 pi pulses, the spin ensemble is no longer in the inverted state, now in the ground state. So you cannot have a superradiance or mazing problem. So yeah, in the Hahn echo protocol, generally we talk about this spins coming to, the equator and then flipping, and they come back in phase and they emit an echo. But one important thing that we always miss is the role of cavity. So echo itself is a superradiance effect, right? It needs to be coupled to a common mode. So if we remove that mode, removing that mode is detuning the resonator, then the spins will not emit at all, right? That's the idea behind echo silencing. It's not to just get rid of the emission. The coherence needs to be preserved. So this needs to still evolve and then come back, right? That's the idea. Okay, so for this project, then we had to start working on different kinds of resonator design. So yeah, don't worry about these fractal holes. These are mainly to people now have started making this so-called holy resonators, where these holes help to improve the tolerance with magnetic field because they help you pin magnetic fluxes. Yeah, but the idea here is that you can pass some bias current through these resonators, and these are made out of superconductors with very high kinetic inductance. You also have to worry about geometries. So you have to choose a right geometry to allow decent kinetic inductance. So if you pass a bias current, your kinetic inductance is going to increase or the frequency is going to decrease. And this is what is plotted here. But the important thing is you can do this very dynamically, really fast. So you can check this in your experiment. Just a simple Hahn echo experiment, but just at the time of echo, you detune your resonator, and more you detune, your echo is suppressed. And the suppression is exactly how you predict. Okay, so far so good. So now that we have the tools of echo silencing, we want to check, can we do on-demand retrieval, right? So let's say I put in 3 states, and then I want to get them back using a pair of refocusing pulses, right? So what I do is apply 2 of them, 2 detuning pulses to silence 2 of the echoes, and then apply a second refocusing pulse. So then I will be able to get the first one and the third one, right? Just to show. Okay, so we did all of that. we actually did all kinds of all permutations of silencing. So first case is where you do no silencing. So I'm missing the input states here. You have the first refocusing and the second refocusing pulse. So you silence one of the echo, one, and here also one, then two of them. So that was all good. It worked as we liked, except after refocusing pulse, we always saw the same thing. Right? It's like we still saw like 3 pulses coming out. And this is actually not so surprising if you remember what I told you. Efficiency in our experiments is still pretty low. So this diagram I had shown, this was for efficiency of 1. That means that, of course, if you whatever you put in, and if you get it all out, right, then of course it cannot come out again because that coherence is gone. But in the low efficiency case, like you're not able to release all those coherence at once. So in classical sense, you can call them there was no perfect impedance matching. So you could not take it out. So of course there's some coherence still stored in the spins, and with the next refocusing pulse, you get them out again. Right? So this is this is still one of the problems that we have to work on. The other one was, which I actually didn't tell you, was inefficient pulses. So ensemble of spins is very difficult to work with because they are located differently in the sample compared to, let's say, your drive line. Right? That means each spin has different Rabi frequency, and that's really, really bad. Right? So your pulses are not ideal at all. So we also worked on this thing. How do we create ideal pulses? And one thing we got in our experiments by accident, especially in the experiment of bismuth spin in silicon. So because of the inductor that was sitting on the substrate, it imparted some strain. And because these bismuth spins, they have very large contact hyperfine between with the nucleus, this strain shifted the energy of each spin. So in that way, what you're doing is you're creating local pockets of localized strain with certain frequency. And then when you drive those spins, you will see very nice Rabi frequency. Well, this is not nice if you talk to qubit guys. I mean, it's really bad. But for people doing hybrid circuits with very inhomogeneous Rabi angles, this is quite nice. So we know what to do. Typically, I mean, this is the point. We know what to do. We have to localize our spin pocket. So again, this is something we can work on. All right. So this is one outstanding challenge, right? And the main challenge still is unit efficiency. And the one thing I didn't tell you, so unit efficiency you will get if this cooperativity, 4g square over kappa and gamma, is precisely equal to 1. Right? And this has to be precisely 1, not like 1.5 or 2 or 3. That doesn't work. It has to be 1. This is the perfect impedance matching. It's like what you put in is what you get out. Right? And how do you control this so that it's equal to 1? It has to be done in situ, right? You take some bunch of samples and some resonator with kappa, some spin with gamma. This is very difficult. You have to have some tunability to make it 1. So there's some tunabilities that do exist. For example, ensemble coupling strength. You can, if you have a spin resonance line, which is very broad, you can sweep across. You can get different cooperativity using that. But I think the better method is hyperpolarization by driving nuclear transitions. So I've shown you like this zoo of transitions that happen in bismuth, and a lot of those lines, they are populated to some degree, but are not used. We are only using the desired transition. So if I want to reach 1, we can create a scheme where I can take some of the population from the nuclear state to the state that I want. Right? So that's all fine. This is something we can working on. I would say gamma is also to some extent can be tuned if you have very anisotropic G factors and all these things. You can work with angle submagnetic field. But the important thing is kappa. Kappa has to be dynamically tunable. Right? And this is something we can actually work on in circuits, superconducting circuits. Now you have kinetic inductance. It's a nonlinear element, and you should be able to do this. So this will allow us to do also catch and release. So you store the spin and release it exactly at the time we need. So I have only 2 minutes left. So and actually we had started working on this. So I call it one resonator to rule them all. it has plenty of elements, this resonator. So we have, these are Bragg mirrors. I will tell you what these are. So basically, this resonator with two-couple resonator, one of them is coupled to spin. This resonator is coupled to the other resonator with the kinetic inductance. This has lots of capabilities. It's very hard to, on paper looks nice, but it took a really, really long time to get this working because there's so many elements and they all need to be optimized. But the good thing is that it does work and we can make it again. Now, this kind of resonator allows RF and microwave simultaneously, so we can work on hyperpolarization. It has frequency tunability because we can pass bias currents, and it has kinetic inductance. And it has two resonators, and we can drive some three-wave mixing to get some copper tunability. So I will not talk about these things. It's a talk by itself, but I will just tell you something about these Bragg mirrors that we have started working on in my lab. So these Bragg mirrors are very similar to the Bragg mirrors that optics has, right? You have, these layers with different refractive indices. If you make a series of them, then you can create a band of very highly reflective, where this band is given by the difference of the refractive index. So in superconducting circuits, you can do similar things. Where instead of refractive index, like you can change the impedance of your transmission line. So you see, like in going from here to here, I have just changed the gaps and the widths. So that sets you different impedance. For example, here is 70 ohm, here is 35 ohm. So if you just make a series of that, you should be able to achieve same functionality. Right? This is exactly what we see. So this is a simulation done in FSS. You can also do some simple ABCD matrix calculation. So this is what you get. This is the band. So you're going to put your resonator in the middle, so it still stays protected as you like. And this will also allow you to pass DC current, RF frequencies, and you can also have pumps which are generally at twice the frequency. So this kind of resonator really will help in the long run. Okay, so finally I come to the outlook, which is really short. So again, I have to keep working on this, and very soon we want to couple these two transmons in a modular way. Right. Okay, so that brings me to acknowledgements. I would like to thank everyone who I work with and also my team, and thank you for your attention.
Have you gotten fabrication going in Hyderabad, or are you relying at the moment on your CEA collaborators?
We have started doing etching and all these things. So, and sputtering, we still have to rely on collaborators. We have in-house sputtering system, but they use a lot of nasty materials that we don't want to mess with. So they're using ferromagnets and things. So, yeah, we don't have dedicated sputtering for, let's say, niobium. But I think once we have a film, that keeps you busy for several months, so it's not a problem. Yeah.
Mm-hmm. Okay, good luck.
Thank you.
So I was a little confused by the sequences of pulses you sent in. So if I understand correctly, the memory that you're developing is an unresolvable ensemble, like what Himadri discussed. So when I send in states to encode, I don't have control over which spin is taking up the input state. So then
but they are encoded in the time space. I know when they were encoded.
But can you only encode one at a time, or can I have more than one state?
No, absolutely. You can have several excitations in one place. It doesn't distinguish. So you have to treat the spin ensemble as a harmonic oscillator. It is a harmonic oscillator. So
because it's a very big spin, is that?
Yes.
Okay.
Yes. Yes.
Okay.
So with one spin, you will create a W state, like one excited, superposition of one excited, and then if you have two, that's the same thing, like two excited and the rest unexcited, right?
I see. Okay. Yeah. And the input pulses you're sending in, like you showed 24 pulses.
Yeah.
I mean, are they right now just classical? They're just classical.
They were proxy pulses. Yes. They were just weak coherent pulses. Yeah.
Okay.
Yeah.
Thanks.
So the dephasing that you see in after bismuth doping, are those because of the bismuth's hyperfine coupling, like the nuclear spin flip-flop, or are those because of the electron-electron coupling, as you described earlier in the NVP1 case? So is it NV13C kind of interaction or NVP1 kind of interaction that is causing the dephasing?
No, so at clock transition, you mean? At clock transition, the T2 that we found was not limited to any magnetic interaction. So we thought it was probably related to charge noise. Yeah.
But then how this, because you use these pulses, by microwave pulses to invert the electron spins.
Yeah.
The question is coming from the fact that could you use a nuclear spin flip and then could you see the elongation that would confirm? Like could you irradiate on bismuth nuclear spin a pi pulse, the Haneko that you are using, while you leave the
So
microwave?
your question, if I understand, if I could flip the nuclear spin, and would that change the?
Yes.
I'm not no.
So we can discuss later, because this is usually in the case of if it is by a hyperfine coupling, then if you flip one of the spins, it should work, whether it is electron or nuclear. So
Yeah, so only recently we have we have this capability of driving nuclear transitions, and we're still studying. So we can, but I think we are in a coupled basis, right? So we are in the nuclear electron coupled basis, right? And the transition is also a coupled transition. So I'm not sure which nuclear transition you want to excite to see the change in coherence property of this. But at clock transition, I can tell you, no magnetic noise is playing part.
okay.
So this we have already proven.
Yes.
Yeah.
All right. Thank you all so much. Thank you.
Okay.
So we break for coffee and be back in 15 minutes. No, it's fine.
So it's better.
I have created on barcode, or I have created a Google form so they can upload their file.
Sure, but I'm saying that not everyone is going to go and.
John likes it very much,
Yeah, so you have
as you might know.
no, right?
Yeah, but then the problem of actually
Google form টা কোথায় দিয়েছেন? কোথায়?
লিঙ্ক আমাকে কাকে পাঠিয়ে এই আমাকে পাঠিয়ে তো আমি ওদের ফরওয়ার্ড করে দিচ্ছি, ঠিক আছে? মানে গুগল ড্রাইভে আপলোড করে দেবে তো? ঠিক আছে, পিপিটি আর পিডিএফ।
So most of the experiments I already had. But again, if we have a localized, I mean, we understand. Anyway, silence is the first step, right? Yeah, I know that word.
I know. No, but I was not sure if some of I went over your papers. I was not sure if it was squared.
So I had invited them to come to Satellite. So when we did this, I want to do something else. No, I want to do this kind of silencing. I see. The correct way of silencing is better. Because wood doesn't help you with the noise and significance.
And in most cases they are so long. Things get complicated. I know exactly what.
So that's what I mean. Like, I would like to avoid.
And then the other issue is that these beer pulses, right, pi over 2 pulses, are even more complex. So those sometimes you can do, but beer pulses, so you are stuck with the same problem of having misaligned feedback. Anyway, we are working with NV Center.
Sure, we can do it. I mean, we should.
Let's talk. We have to discuss. So now I have got. I have found 2 people who are closest to what I do actually. You 2 guys should meet.
So my definition of hyperpolarization was. So also I did not mention because we are in the first. So we
question was when you showed example that you turned on the field and there was shift, you said. This one is for the pole.
Yes. So but that's quite big. But yes, we have seen this. And that's the electric field noise that I talked about. So my coherence time is actually
limited because you are in this regime of decoherence free species.
Well,
Clock
magnetic field.
magnetic field.
Yeah, that's the reason. I think that's the number we have calculated from dynamical decoupling. When we did dynamical decoupling, we improved and we calculated the slope and all. So we saw that this was Gaussian noise kind of thing. And then we took some density of electric charge noise and we calculated back. So this will have like 1s to 2s transition. And for that we got very reasonable values. Like electric field noise on silicon could produce something similar for this. But for magnetic field, there was no problem. So actually in the next experiment we even got has gotten better. You know, the sample that I showed like was 500 same kind of influence. So yeah, that's the good thing is, you know, in different continents it works and it keeps working, you know. And these kind of things you solve, you know, you want to solve problems which are independent of the spin and independent of the circuit.
So you should take a look at the poster that my student had.
Yes.
It's about clock-like transitions, but in hexagonal more on nitride. So they have got very strongly coupled nucleus with nitrogen close to the base.
কানেক্টই হচ্ছে না এলজিএম এর এটা উবুন্টুতে পাওয়ার পয়েন্ট কাজ করে না আবার খুলতে হবে তাহলে আবার চাপ প্রথম ল্যাপটপটা এমনিতে সেকেন্ড আছে না অসুবিধা নেই হ্যাঁ না
এটা পাগল
এটা কার ল্যাপটপ এটা ওই ল্যাপটপটা অন্য কোনো ল্যাপটপ ওটাই
না এটা অন্য ল্যাপটপ
হ্যাঁ
এখান থেকে টাইমারটা রিমুভ করছি
ওই ল্যাপটপটা কি জোয়াল আছে
এটা অ্যাড করি
বালিয়া মাইন ইলেকট্রিক কি এটা 2021 এর জিনিসটা what is the password for file it's written there events@2020 E21D20 double key হ্যাঁ তো 21D আর PH24D আমাদের তো আলাদা হবে PH24D তোমার তো মনে করি না
সেমই সবার তো একই ফার্স্ট ডিপার্টমেন্ট রোল নাম্বার
ও হ্যাঁ 007 তো 201
না যারা আপনাদের অন্য হয় অ্যাডমিশন ওই উবুন্টুটাকে আমরা ইউজ করে দেবো এর জন্য টাইমারের জন্য
উবুন্টুটাকে দিয়ে দাও পার্সোনাল ওই ওটা প্রতিটা পার্সোনাল
উবুন্টুটা দিয়ে দেয় তাহলে ওই বিকাশটা ইউজ করে নেবো যে দেখ পিপিটি কাজ করছে না
বিকাশেরটাতে তো না এইটা আমি করলাম যেটা নেভার
এটা নেভার করলে ওইটাতে
এইটা নেভার করে ওটাতে নেভার করে দেবো চাপ নেই ওটা হয়ে যাবে
এখনই করে দে টাইম নাই
দাও করে দিচ্ছি
next conference? Okay, I'm also planning, but I haven't decided. I was with Direct for 3 years. Then I was in College Academy. Then I was like for 3 months and then I got the position and I have to come back. So. Okay, but I also have a plan because in Toro we have a conference. Probably after that also in yeah. So I think this could be 5. Yeah. Maybe you can just close it and then open it again. The record plan.
It's working, but should come full screen. Okay, just I think maybe full screen. Now we can do this calculation. Alright, everyone. So we are. Yes, just put it. I will not log in.
Our next speaker is Anindita Bera, PIT Mesra.
Am I audible? Oh. Shall I start? Okay. Good afternoon, everyone. So before going to start, I'd like to thank the organizers for giving me this platform to present my work here. So in this session, the topic that I'll talk about, which is like completely different what you have heard in the first session. Okay. So this is the title of my talk today. So it will be based on the entanglement witnesses. But I don't think today all of you do need the introduction of what do we mean by entanglement. So this is just for the. Yeah, so it is spooky now. Oh, okay, we have this one. So just for the completeness of the talk, so if we have a mixed state regime, and if we consider it like, if we just think of a two-party system, then the state you can say it will be entangled if you cannot represent the state. The pointer is not working, right?
The last button is the pointer.
Okay. So if you cannot represent the state as a convex combination of the tensor product of their local subsystems, okay, then the state you can say the state is entangled. But this detection of entanglement is difficult. Why I am saying this one? Because suppose you are preparing some state, rho AB, and you can think of the state is as a resource, but how you can check that state is entangled? Okay, because this question is very much important from both the fundamental and application point of view. Because we know that quantum entanglement is a very useful resource in several quantum computation tasks, also in the quantum communication as well. For example, quantum teleportation, quantum dense coding, cryptography, more and more. But unfortunately, after this 2 or 3 decades long research, till now, given a quantum state, it is still not easy to say whether that state will be entangled or separable. Because from the direct definitions, you cannot say always that you do have that kind of decomposition. But definitely we do have some measures in our existing literatures that, for example, the partial transposition criteria, which is very much well known to all of us, which is also known as the Perez-Horodetzky criteria, which says that if you have an entangled state, if you have a quantum state rho B, take the partial transposition of that one, and then you need to find the eigenvalues of that partial transpose state. And if you find at least one eigenvalue is negative, then immediately you can say the state is entangled. And this is a necessary and sufficient condition, only the dimensions 2 cross 2 and 2 cross 3. Only this dimension, the separability problem, you can say that is solved. But beyond that dimension, you cannot say it is not easy to say whether the given state is entangled or not. It is not easy to say. There are other criteria as well, for example, the majorization criteria and the cross norm or realignment criteria, I think. Okay. Okay, I should stay here then, probably. I don't know what is the connection. Yes. Or the covariance matrix criteria. So there are several criteria as well, but most of them are like precise to a particular kind of state or some small dimensions also. So that's the reason what we introduce here, we consider here the entanglement witness. So so this is kind of, you can think of the entanglement witness mesh where you have some quantum state, where you have separable state, some undetected state, and through this mesh you got the entangled state. Okay. So one can witness the presence of entanglement just by measuring the mean value of the physical quantities. Why we are considering entanglement witness in the first place? 2 reasons. One is the very much fundamental, because for every entangled state we have an entanglement witness. Okay. Yes. So for every entangled state we have an entanglement witness. Not only that, if you have the entanglement witness, it provides the insights into the structure of the entangled states. And from the application point of view, it has immensely helpful, because this entanglement witness, it corresponds to the Hermitian operator. Okay. So you can realize this entangled witness in the experiments for the verification of entangled states. Because for all the time you can write this entangled witnesses in the decomposition of the local observables. Okay. And that you can realize in the experiments as well. Now what is the proper definitions? So the central concept of this entangled witness, it is based on the Hahn-Banach theorem. What it says, that suppose you have a SBI, you can think of a convex compact set in a Banach space, and rho be a point in that space such that rho does not belong to S. Then there exists a hyperplane which separates this rho from S. Okay. So this is the Hahn-Banach theorem. Now you can think this S as a set of separable state. Now this W, you can think of this W will be an entanglement witness. So this is an Hermitian operator, or you can think of an observable. This will be an entanglement witness if and only if you can find at least one state rho such that the distance between that state rho to this witness, which is trace of W rho, which will be negative. However, for all separable states, the distance will be either positive or it is equals to 0. Okay. Now we need to know the few stuff of entanglement witness, because throughout my talk I will talk about the decomposable witness or the non-decomposable witness as well. So what do you mean by that? So an entanglement witness is said to be decomposable if and only if you can find 2 operators PQ, positive operators, such that you can decompose the witness in this particular way. P plus Q partial transpose. You can take partial transpose with respect to any party, A or B. Okay. The thing is that if you have decomposable witness, it cannot detect the PPT entangled state. It is not possible to detect. So then you need to consider the non-decomposable entanglement witness. So for the non-decomposable witness, you can always find at least one PPT state which will be detected by that witness. Okay, so in the non-decomposable witness, you cannot decompose in this A plus B transpose form, But also here, all the time, you will find at least one PPT states, okay, which can detect more entangled state, which will be detected by this non-decomposable entanglementness. So this PPT states means that this is positive partial transpose state, because beyond 2 cross 2 and 2 cross 3, beyond this dimension, if you want to calculate the entanglement, then, this partial transpose state, the eigenvalues can be positive as well. And in that case, the state can be entangled as well. So those states are called positive partial transpose state. So this is kind of a schematic view of the Hilbert space you can think of. So here you can think that you have a state rho 1. Here you can think of you have a state rho 1 and rho 2, and you have two witnesses, W1, EW1 and EW2. So here I am saying that this EW1, this is an decomposable entanglement witnesses. Okay. So it detects only the NPT. So NPT states are always entangled. Okay. And I am taking here the EW2. So this is, you can think of this is a non-decomposable entanglement witness which detects some PPT entangled states. But none of them can detect all the entangled states. Okay. Now these are the research directions that I will be talking about today. So one direction is the optimality. Another one is the entanglement witnesses with the mutually unbiased basis. And the third one is the kind of entangled witnesses that we have defined, which we give the name as entanglement witness 2.0 or the mirrored entanglement witness. So let's start with the optimality one. Okay. So what do you mean by the optimal entanglement witness? So we have a set of separable state here, and we have supposed considering two entangled states, rho 1 and rho 2. And we are considering two witnesses, W1 and W2. Okay. So here you can find that all the time the witness can detect the states which lies in the right hand side. So here the witness W1, it can detect both the states rho 1 and rho 2. However, the witness W2, it can detect only rho 2. It cannot detect the state rho 1. Okay. So therefore here in the way we can say that the witness W1 is optimal. Optimal in the sense that in this side you cannot find any other witness which can detect more entangled state than our W1 does. Okay. So all the time, when it has to be optimal, it has to be tangent to the set of separable states. Okay. So in that sense here, the witness W1 is optimal. Now why we are searching for the optimal witness? Because if we have the knowledge of optimal entanglement witness, then it is sufficient for the full characterization of the set of separable or the entangled states. Now, to find this optimality, how we can proceed? So in the literature, we have only the sufficient criteria for finding this optimality. And that criteria is known as the spanning property, which was given like 2 decades ago. So what are that criteria? Criteria is that if you have a set of product vectors, you can take in this way, you can take in this way that psi k tensor phi k in this way, where the averaging will give you 0. Not only that, these vectors will span the whole space. What I mean, that suppose if you consider the dimension 3 cross 3, in the dimension you need to find 9 product vectors which will be linearly independent, as well as which spans this whole space. Okay. Then if you can find that, then immediately you can say your witness is optimal. Okay. And this is just the sufficient one. This is not the necessary. In the literature, we do have the witness. That is very much well known to all of us, which is the Choi map. Corresponding to Choi map, the witness is optimal, but without the spanning property. Okay. But if you have the full spanning property, then immediately you can say your witness is optimal. That is one way to approach to the optimal entanglement witness. Now, if it is not optimal, then what you can do? So can it do, yes. No, which lies in that side, because it's not possible to scan the whole space, which lies in that side, yes. So if it is not optimal, then do we have some optimization procedure to make that witness optimal? Yes, we do have. So suppose here the witness W2, what we have, that is not optimal. But how we can make that W2 optimal? To make the W2 optimal, we need to look into the orthogonal complement subspace. Okay. And then in this orthogonal complement subspace, we need to find which vector you can subtract from that witness, so that now the witness that will be constructed, that will give you the optimality. So there are two things that you need to find. In that orthogonal complement subspace, which direction, so which vector that you need to find, and how much you can subtract. So these are the two things that is important to get that optimization procedure, so that you can have your witness optimal. Okay. Now the kind of witness that we have, constructed for our work, which is known as the covariant Bell diagonal in n cross n dimension. So covariant Bell diagonal, so in the name you can understand that Bell diagonal will be, we mean that it will be the diagonal in the Bell basis, and for the covariant it will satisfy some covariance property. So the way we have constructed as follows, that suppose we are fixing the computational basis in n-dimensional Hilbert space, and then we introduce the family of Weyl unitary operators, and we know that this Weyl unitary operators, it satisfies some properties. Then, operator it can say x you can think of is said to be Bell diagonal if you can represent in this particular way. Okay. So then the operator x you can say this will be Bell diagonal. And the covariant it will be when it will satisfy this particular relation. So these are the two relations that needs to be satisfied. So the kind of operator that we have constructed is like this. So this operator is covariant and this is a Bell diagonal. And we have two coefficients here, AKL and BKL. What are those? So we consider that BKL, these are the constant. So you can take this BKL is some constant beta. And for AKL, these are the, you can think of this is circulant. The matrix can be circulant. And the elements you can take off like alpha 0, alpha 1 like that. Okay. Now this is the operator. So we need to make this operator as a witness. So what are the conditions needs to satisfy for this operator to become a legitimate witness? So these are the conditions that needs to be satisfied to become this operator. This operator, this will be witness under these two particular conditions. Okay. So now another thing, because all the time we know that by using this Choi-Chaminsky isomorphism, every entanglement witness corresponds to a positive map. So here the kind of witness that we have here, so which is like this. So what are the kind of positive map that we can get from this witness? And that is here. So for this witness, these are the map that we can get. These are the positive map. So witness will always correspond to a positive but not complete positive map. Okay. Now let's discuss about the 3 cross 3 dimension, because we know 2 cross 2, 2 cross 3, this Perez-Horowitz criteria would be enough for us. Now let us discuss on the 3 cross 3 dimension. So the witness that we have constructed like this. So here this alpha 0, alpha 1, alpha 2 that we have parameterized by ABC, and then it needs to satisfy these conditions to become a witness. So the conditions will be here. So these are the two conditions that needs to be satisfied. So these are the two conditions that needs to be satisfied to become this W a valid witness. Now this is here you have 3 parameter family A, B, C. So you can parameterize this 3 parameters by a single parameter which is phi. Now what is the optimality of this one? The optimality is that when A is less equals to 1, then this witness is always optimal. And when A is strictly less than 1, then it has the spanning property. For A equals to 1, it does not have the spanning property, but still it is optimal. So for A less than 1, when I am saying that it has the full spanning property, so I need to show that, okay, 3 cross 3 dimension, so 9 linearly independent vectors should be there, which satisfy the averaging. And here are those 9 vectors that we have found, that already, these people have done in their research. Okay. So for A less equals to 1, it has the spanning property, so it is, and it is optimal. Now for A equals to 1, it corresponds to the Choi map. Okay. So if you take A equals to 1, then BC can be 1, 0 or 0, 1. So both corresponds to the Choi map. Note that this Choi map is the first map in the literature which is the non-decomposable. So which detects PPT entangled states. Okay. And for the Choi map, we do not have the full spanning property, because for the Choi map we have only 7 vectors. And how the 7 numbers is coming, then I will talk in few slides. And if you take A equals to 0, then it corresponds to the decomposable witness. So usually when you have decomposable witness, the witness is not optimal. But here it corresponds to the reduction map. And reduction map is decomposable, but it is always optimal. And it does not depend on any dimension. For any n cross n dimension, for the reduction map, you can immediately find what will be the spanning vectors for the reduction one. Now let's come to the 4 cross 4 dimension, which is our result. So in the 4 cross 4 dimension, again, okay, that should be ABCD. We have 4 parameters. So ABCD here we have. And again, it needs to satisfy these conditions to become a valid witness. So the conditions is this one. So these are the 4 conditions that needs to be satisfied. Now once you calculate this conditions, then you can find here you have 2 class of entanglement witnesses. So class 1 satisfy a different set of conditions, class 2 satisfy another set of conditions. So for the 3 cross 3 you have single class. Now for the 4 cross 4 you have 2 different class of witnesses. Now let's focus on the class 1. For class 1, the witness we can parameterize by again a single parameter, which is theta. So for theta range from 0 to pi, so the 0 range is when you have 0, then you will have the generalized Choi 1. And again for theta equals to pi, that is also a generalized Choi 1. Okay. Now we need to find the optimality of this witness. Because at theta equals to pi by 2, this is decomposable. For the decomposable, it will not be optimal. So we are just removing that point, and we are trying to find whether in this 4 cross 4 dimension, we can get 16 linearly independent vectors which spans the whole space, and then immediately we can say the witness will be optimal. So what we have found that, so the kind of witness that we have, for that, if we take the vectors from the random phases, so if you take psi k in this particular form and the product vectors, if you consider psi k tensor psi k star, and psi k has the phases, random phases, then these vectors all the time, it spans the space n square minus n plus 1 dimension. So that's the reason when you consider 3 cross 3, for the Choi map, the vectors are coming only from this random phases vector, which is 7, for the Choi 1. Okay. Here for the 4 cross 4 dimension, so now since you know this one, so immediately 13 vectors you have. So your job is to find the another 3 vectors. So only you have 13 1, so you need to find another 3 vectors. So theta equals to 0 pi corresponds to the Choi 1, so for them only you have this 13 vectors. Now what are the other 3 vectors? So we found the other 3, but if you consider this one along with the random phases vector, what we found that it does not span the whole space, whole 16-dimensional space. Rather, it spans the 15-dimensional. So still one vector is missing. So from the class 1, what we got to know that it spans only the 15-dimensional space. So one vector is still missing. And we found that we do not have that vector in that space. So now we need to apply this optimization procedure that I have mentioned before. So you need to look into the orthogonal and complement directions in which you need to find a vector which that vector should be the orthogonal to that subspace. And not only that, you need to find how much you can subtract so that the witness will be optimal. So these are the kind of vectors that we have found. So this psi, this is orthogonal to this 15-dimensional subspace spanned by all the previous vectors that I have shown. And then we prove this theorem that if you subtract a lambda amount of this projector, of this vector, okay, then the witness that you are forming, this witness is optimal. And it will be optimal when you will take lambda equals to 2. Okay, so it means that what we found that optimal means here with full spanning property. So after doing the subtractions, you have full spanning. So what are the other vectors that is missing? It's missing that after subtracting the kind of vectors that we have, so here it has a very particular property that mod of psi 0 should be equals to mod of psi 2 and mod of psi 1 is equals to mod of psi 3. With random phases. With random phases vector, if you incorporate this one, it will span the whole 16-dimensional spaces. Okay, so this is now the optimal. You got the optimal witnesses. So class 1 is done. Okay, now let's look into the class. Okay, before going to the class 2, so let me give the example of PPT states. What are the PPT states is detecting by this, both the witness W and the W prime. So witness which is not optimal and the optimized witness. Because the optimized witness should detect some much more entangled state. That's the reason we are getting that one is optimal, right? So these are the kind of PPT states that we have considered. And what we have found that if you calculate the, trace of this W row of this state and this optimized one, trace of W prime row of this one, then we found that this state is detected by both the witnesses. So you have a witness, you have a PPT states, PPT entangled states, which is detected by both the witnesses and the optimized one. Now if you twisted the state by adding some more noise, then what we found that you got a range where, the witness which is not optimal, it cannot detect the state. But the optimal witnesses that you have, that optimized one, it can detect because the trace distance is negative. Okay, so that's the reason. So always, if you have the optimal entanglement witness, then you have the full classification of the set of entangled or separable states. Okay, now let's come to the class 2. Again, class 2, we have this set of conditions and it can be parameterized by a single parameter. So again, we know that 13 vectors will be there from that proposition that we have. Now what we have here, so for this, okay, here at some point, theta equals to 0, it will be decomposable. But the main thing that I want to say here, for the class 2 states, we already have these conditions. So the product vectors that you choose, it already has this, it already satisfies this one, that mod of psi 0 equals to mod of psi 2. And mod of psi 1 equals to mod of psi 3. So you have the 13 vectors, along with this, you have 14 vectors for the class 2. So 2 vectors are still missing. So what can be those 2 vectors? So we actually found 2 vectors which will be orthogonal to this subspace spanned by these 14-dimensional spaces. But the problem is, you cannot subtract here. What we have shown that class 2 witnesses will be optimal with only 14 linearly independent vectors. So it does not have the full spanning vector. So you do have the optimal entanglement witnesses without spanning property. Because though we found 2 vectors which lie in the orthogonal complement subspace, but if you want to subtract, any small amount of any linear combination of that 2 vectors, it will immediately give you that it will not be a witness. Okay, so you cannot subtract here. So this is a witness without the spanning property. Optimal witness, but without the spanning property. So then, our idea is to go to the beyond n equals to 4. And what we found that, okay, because of the very complicated structures, for the odd dimensions we do have the result, but for the even dimension, most of the time it belongs to the 2 classes, and then finding this optimality, it's a very difficult task, and we are still investigating that one. So let me go to the next one, which is the entangled witnesses. Yes. So here for the even dimension, so because the structures we have, the conditions that we are showing. So all the time those conditions for the even dimension, leads to a single one. And for the odd dimension, all the time it is showing the 2 different classes. So it's based on the structure of the Bell diagonal coherent Bell diagonal witnesses, because of that structure. Now let's come to the entangled witnesses with mutually unbiased basis. So many of you know about the mutually unbiased basis, that if you have a pair of orthonormal bases B1, B2, then it is said to be mutually unbiased if it satisfies this particular relation that we all know. For example, here, this schematic one, that here this basis B1 and B2, so this is B1 and B2, these 2 are mutually unbiased, but here this B3, the B3, it does not have the equal overlap with B2 or B1. So B3 is not mutually unbiased with B2 or B1. Now if you take the dimension, so if you consider the larger collection of measurements, then we can say that a set of bases are mutually unbiased if the bases are pairwise mutually unbiased. So in a d-dimensional Hilbert space, maximum D plus 1 mutually unbiased basis one can have, which are pairwise unbiased. Now for the dimension 2, we know that, okay, these are the mutually unbiased bases. So 3, you have 3 mutually unbiased bases. Now what are the, we know definitely this, whether for a D-dimensional system, whether you have D plus 1 mutually unbiased basis in all dimensions, I mean it's still a long-standing open problem. Mainly the problem is what is the maximal number of MUBs in any given non-prime power dimension D. So for the prime power dimension, that we know that maximal D plus 1 MUBs one can have when D is prime or it has the prime power. But this classification of subsets of MUBs is an open problem for D greater than 5. Because D equals to 6, it is conjectured that only 3 MUBs exist, but no proof is there till now. But very little is known between the connections between the entanglement witnesses and the mutually unbiased bases. That, how many PPT entangled state, how many measurements are needed to detect this PPT entangled states. So that is our idea, that how many mutually unbiased bases one can have to detect the PPT entangled state. So in a D-dimensional system, you can have maximum D plus 1 MUBs to detect this PPT entangled state. So our idea is, can we reduce this number? Can we have the less number of measurements? Because if you have the less number of measurements, it will be beneficial for the experiments as well. So what we did, we construct the entanglement witness by using this mutually unbiased basis. And how we have constructed that, suppose we are considering a M MUBs in a D-dimensional Hilbert space. Okay. And then we constructed this two operator. So S is a shift operator here. You can take any shift here. So we have constructed these two operators. And these two operators, it has an, if you calculate the trace with separable, it has a upper bound of this one. So then, we have incorporated this one and we constructed this operator, WMMS, in this following way. So these are the kind of operators that we have constructed, and it satisfies always this greater equals to 0, and for if you take the partial transposition of this one, then also it will be greater equals to 0. So therefore, whenever this W and W partial transpose, whenever they will have a strictly negative eigenvalue, then immediately you will say this is an entanglement witness, right? For the entanglement witnesses, it must have at least one negative eigenvalue. So whenever they will have a strictly negative eigenvalue, they will be an entanglement witness. Now what are the theorem that we have is that suppose 2S is not equals to D. Now if you take M is the number of MUBs. If M is greater than D by 2 plus 1, then this W partial transpose, it defines a non-decomposable entanglement witness. Means that this witness can detect the bound entangled states. So what is means that, so previously we have D plus 1 to detect the PPT entangled state, you have, for a D-dimensional system, you have D plus 1 MUBs. Now from here, you can say that you do not need the D plus 1 number of MUBs, rather than D by 2 plus 1. So the number of measurements are very less. So that this number of MUBs are sufficient to detect the PPT entangled state. Okay. So let me give an example. So if we take the example for D equals to 3. So for D equals to 3, so maximum MUBs you can have 4. You need 4 MUBs previously. But according to our theorem, you do not need the 4 MUBs. Rather than here, so if you just look into this theorem, so here you need only 3 MUBs for the 3-dimensional system, which will be enough to detect the bound entangled state. So let me give the example. So for D equals to 3, you have 4 MUBs, 4 Heisenberg value MUBs, where the form will be like that. Now we are constructing these witnesses. So you can take any 3 MUBs, any 3 operators you can take, and you can construct these witnesses. So the form of witness can be this one, or this one as well. And all of these witnesses are non-decomposable. So means that they will detect some PPT entangled state. So what are the kind of PPT entangled state it can detect? It's this one. So therefore, in dimension 3, you do not need the 4 MUVs. Rather, 3 MUVs are enough to detect the PPT entangled state. Okay. Now, if you take the 2 MUVs, you can think, okay, can we reduce much more? For the, d equals to 2, d equals to 3, can we reduce more? No, you cannot. Because now if you construct the witness by using 2 MUVs, then whatever the witness that you will be constructing, all of this witness will be decomposable. It means that it cannot detect the PPT entangled state. Now we do have a conjecture. That conjecture says that if you take the dimension d equals to 2 to the power r, in this dimension, the minimal number of MUVs required for bound entanglement detection is that d by 2 plus 1. So here we have shown, for example, in our work we have shown for the d equals to 4 dimension. So again for the d equals to 4 dimension, 3 MUVs will be enough to detect the PPT entangled state. So how you can construct that, how you can construct the entangled witnesses by this dimension d equals to 4. So here you can take 3 MUVs, B0, B1, so B0 is the common canonical basis, B1 you can take in this form, and Bx you can take either for the extendable basis or from the unextendable basis. Okay, and you can construct the entanglement witnesses by using the 3 this MUVs. And then again you can show that they are the non-decomposable because they detect some kind of PPT entangled state. For example, if you construct from the extendable basis, then this is the corresponding witness, and this witness can detect this family of PPT entangled state. And if you consider from the unextendable basis, and then if you construct the witness, then it can detect also this kind of PPT entangled state. Okay. So now for the last few slides of our work, which is entanglement witness 2.0. So these are the kind of witnesses that we have defined in our work. So the idea to define such kind of entanglement witnesses, we got the idea from the structural physical approximation, SPA. So the idea of SPA is that you need to mix a positive map with an amount of completely depolarizing map as small as possible so that it will be a CP map, because our positive map is not physically realizable. So once you have the CP map, then that can be physically realizable. So, equivalently, one can define the SPA to an entanglement witness W. It can be defined in this particular way. And the SPA conjecture that we know that SPA to an optimal entanglement witness always will be a separable states. So this was the conjecture. But this conjecture already disproved by these people. I think Ha and Kie disproved this conjecture by considering the optimal non-decomposable entanglement witness, and later on Dariusz Kruszyński, Niewko Sarwicki, they disproved this SPA conjecture by considering optimal decomposable entanglement witnesses. So this conjecture has been already disproved. So based on this idea, what we defined that if you have an entanglement witness, the negation of the entanglement witness will not be a witness. So then how much you can subtract from, the identity so that, in the other side of the state space, you can get another entanglement witness. And that one we are defining as a mirrored entanglement witness or entanglement witness 2.0. So these are the kind of definitions that we have provided. And again, if we have an optimal entanglement witness, so how can we characterize the mirrored entanglement witness? Yes, I'm almost done. So what we give the conjecture in one of our work that if the witness is optimal, then the mirrored operator of that entanglement witness will always be decomposable, or it will not be a witness also. It will be just a positive operator. So that was our conjecture. That if the witness is not optimal, then the mirrored one can be non-decomposable so that it can detect the PPT entangled state. But if the witness is optimal, then the mirrored one will not be non-decomposable. It will be either decomposable or it cannot be a witness also. So that was our conjecture. But surprisingly, and in the beginning of this year, we found few examples. So, I mean, when we provided this conjecture, I mean, most of the examples that exist in the literature, we checked for all of them, but we couldn't find which, I mean, disprove our conjecture. But in the beginning of this year, so this paper came today on the archive, I mean, where we have disproved our conjecture. So we provided the conjecture and we disproved the conjecture. So you can go through the today's archive link. And there we have shown that if you have, so here if you have W1 and W2, this pair of witnesses, so previously it was if W1 is optimal, then W2 will be non-decomposable. Now what we found a pair of witnesses, W3, W4, where both can be optimal. I mean, witness and its mirror operator, both can be optimal and both can be non-decomposable as well. Okay. And that one, we found for the dimension 3, d equals to 3, d equals to 5, d equals to 7. For the even dimension, still we couldn't found, but for the odd dimension, and we found the witnesses, and again, those witnesses, again, we have constructed by using the MUBs. So, that's all. Thank you, everyone. Yes.
Hi. So optimal in what sense? Like if the first part of your talk. So can
yes. Do you have some chalk? Or can I write there? So you have a set of separable states. Okay, so optimal means that when I am saying the optimal, so it has to be tangent to the set of separable states. Okay, so you can have another witness this side as well. Okay, which is touching. So this witness can be optimal, this witness can be optimal. So what I am saying optimal means that in this side you can have several other witness also, but still you can get one entangled state which cannot be detected by this one. So when I am considering this witness as optimal, all the states which lying in this side will be detected by this.
And
witness.
can you do this in an experimental setup? Or
yes,
do you
yes. Witness people do. I mean.
No, in the sense that do you need to know the full density matrix to compute your W or?
Not necessary. Not necessary.
Okay.
Not necessary, because the good thing about witness is that always witness you can write in terms of the linear combination of the local observables. So you can think of xi tensor yi. So in this way. So in the experiments you can actually change this local observables and you can find what will be your witness. So that's the main importance of considering witness. Yep. It is experimentally realizable.
Can't we find out you're writing straight lines? Okay.
Yes.
Instead of that, the whole circle.
Yes, that's the nonlinear witness. But there you cannot have the Hahn-Banach theorem. So Hahn-Banach theorem will not be satisfied there. What you are trying to say that can I take a witness like this?
Not only that, there's a full circle itself.
It's very difficult. Yes. Okay. So this is a nonlinear witness. Okay. That concept is there. Okay. So for the mirrored witness, we do have the nonlinear witness as well. But then, showing that it is optimal, that.
No, what I mean to say is that take the set of optimal witnesses and will it provide the circle? That's what I meant to ask you. That's what I meant.
When I'm drawing this one, it looks very easy, but
maybe see, this is difficult because you don't have the curvature.
Yes,
of
exactly.
you don't know. Okay.
Just drawing this one, it seems very easy, but unfortunately, it's not.
Okay, thanks.
So maybe just as a follow-up, is there a notion of a volume of PPT states that can be measured by a given? Sorry, thanks. I violated my rule. Yeah. Is there? For a given witness, this is the volume of PPT states that can be.
Yes, I think there is. I remembered one paper by. I think the title is only this one, the volume of PPT states. I don't know.
No, that's a different thing. But given a witness, this is the volume of PPT states, because then you have some comparison between these optimal
okay,
witnesses.
we haven't tried that one.
Maybe
that will be a nice thing. Okay.
All right. If there's no further questions, let's thank Anindita
Thank
for
you.
an interesting talk. Hi, how are you? Okay, well, so we're happy to have the next talk, Bodhaditya Santra from IIT Delhi.
Can you hear me now? Okay, thanks a lot. So I would like to thank you, the organizers, for making such a very nice gathering of beautiful and innovative minds together. I'm also very sorry for my throat. So I'll be talking about what we are doing in our lab using cold atoms and high precision lasers. So I am working here at IIT Delhi for last 5 years or so, and this place IIT Madras is very special from many point of view, and I have been visiting here from 2007 or something. So the beautiful pictures what you are showing, so I'm a bit used to it. So now, so this Prenisk is actually a startup which came out of our lab's work, and some of my students, Kamal Kant and Hemant, they are also sitting here, who are actually the main reason why we could make it happen at our lab. So this is a vacuum chamber. As you can see, this is made of very high quality glass, because this is where we are going to trap and image single atoms, which we are going to use for qubits. And there are a lot of electronics, and we are also making our own lasers. So a lot of things which are going into, which are not interesting when you look into quantum computing from a Hamiltonian point of view. This is also our motivation. So we are not sure that we really want to make a quantum computer, but we are definitely want to make all the components and make sure that we can control the atoms to the best possible coherence level, which is needed for quantum computing. So now, if we look into a little bit what is the numbers, so we talk about qubit fidelity and so on, and quantum computing research is very, very expensive. So when we think we try to get money, but can we also generate money? Because how long can we rely on government money? It's also a lot of uncertainties and so on. So this is a report, rather recent report from McKinsey, and they have been analyzing. So there is a huge economical value from quantum computing around 2035. So it could reach like 1 to 2 trillion US dollar. Now, what are those sectors which will be benefited from quantum computing? Here are some lists. So like the financial sector, travel, transport, and logistics, pharmaceuticals, sectors, so like a targeted drug design and so on. And there are many more, like quantum, so like a telecommunication and so on. I'm not going to that much detail. Now, if you look into the number of top 10 startups in terms of deal size, you see the number one is Pascal, which is the startup from the group of Anton Broes, and they are working towards making quantum simulator mostly using neutral atoms. And there are also other startups like QCTRL. This is an Australia-based startup. They are also making quantum sensors using neutral atoms, so like atom interferometry based. There are many others like this Oxford Ionics is a startup who are working towards making ion-based quantum computer. They came out of the University of Oxford, and there are many more. There are also nitrogen vacancies. So if you look into these startups, you will realize that almost 70% of the this quantum technology enabling devices are at the heart of this technology is a very, very high precision laser. And it's happened to that, its name is external cavity diode laser, which was first, brought to the this community by Theodor Hunch and then also Wolfgang Ettmer and so on. So now whether we could, at all cool atoms or ions and whether we could address this for fulfilling the requirements of quantum computing depends on whether we can have a very high quality lasers. When I'm talking about high quality, it's the control of frequency and power stability and so on. So now how does a quantum computer made of neutral atom look like? So I'm just going into how the atoms look like. So this is a picture from the group of Manuel Andres. So in the last year he did some work, and that's in archive. So here you can see this single dot. So these single dots represent fluorescence from an atom. So you cannot see an atom, but when you make a light atom interaction, so there will be scattering coming out of these atoms. That is something you can measure. So that's a photon statistics. If you have this quantum optics courses, and this is one of the important things, how to measure, how to count photons at few photon levels, to measure few atom level. Right. So, and if you look some numbers, so this cesium atom, so it happened that we are also working with cesium atom, and this is using cesium atom. So they have trapped about 6,100 cesium atoms in a total tweezers of roughly 12,000, because this loading process is a bit of a probabilistic in the first place, and the coherence time is beyond 2.6 seconds, which is much longer than what is needed, like few microseconds for operating CNOT gates and single qubit gates using neutral atom qubits. There are a few other very nice properties because these atoms are like nature's qubit. It is not a fabricated one. Either it's an atom or it's a, like in the atomic system there are two types. One is a neutral atom, and another one is a charged. So that's a, if you take out of one electron out of the last orbital of an atom, it will have like plus, so it will be an ion with a single charge, and this is also an atomic system. So these are the two types of qubits. If you do it in, doesn't matter in IIT Madras or even somewhere else in Europe, US, and even if you go to Mars or Moon or any other planet you can think of, it will be a cesium atom or it will be a that atom. Because if you change even one electron, then it becomes another one. So that's a nice thing. And there is also very high precision lasers with ultra high vacuum chambers and all those things which were needed, and we have been working on this high precision spectroscopy based measurements on atoms and ions for optical clocks and other things. And this is a very scalable system because in this community we have been working with optical lattices which could hold many 1,000 atoms even in 3D. But there are some problems which I will try to shed some light on this, which have been overcome around 2017. And what happened is actually the case with this, as I was showing you, this this is a probabilistic loading. That means when we load atoms from a very cold atom reservoir, so it's basically its name is magneto-optical trap, and then you trap into single atom loadable tweezers. So these tweezers are basically optical dipole traps. If you just put a lens and then if you send a collimated Gaussian beam, you will get a very small beam width. That is something where the trapping potential is very large, and if you are able to make this beam width at this focus point like a micrometer or something, then the trapping volume will be very small, so that only one or few atoms will be loaded, 1 or 3 or 5, because there is another thing called light-assisted collision, which will remove all modulo 2 atoms. So you can trap only even number of atoms there, and that's how these things are done. So now we needed to, for quantum computing, we need to have defect-free arrays. So that work was done around 2017 to making a transition from an array with a 50% roughly defect to an array with nearly 100% there's no filling. Okay, so all those things are quite interesting, and that makes neutral atom platform as one of the interesting platform for exploring quantum computing. And keep in mind that these have been happening only in last 7 to 8 years. Before that, in the community, I should also mention one thing, because Professor DiVincenzo is here. So I was a postdoc at University of Kaiserslautern around from 2013 to 2016, and I was working with a group of with Harry Gott, working in this single site addressing with scanning electron microscope, and many eminent scientists used to visit. So one day, Professor DiVincenzo visited, and to my ignorance, I was only looking into quantum simulation. I didn't know about quantum computing at that time. So after he left, so my mentor told me that, do you know him? So I told them no. So he said that if you ever do quantum computing in future, his work are going to be one of the thing you will be following. So it's happening so fast. It's less than 10 years time, and then I'm now. It's a bit of a don't you call this also kind of entanglement, that my mentor predicted something, and then we are seeing this today, and it's a very nice coincidence. So okay. So now going forward, so what is the architecture for neutral atom quantum computer? So I have already introduced this array of atoms. So besides that, also we need microwaves for addressing this clock transition, and Rydberg lasers and Raman beams, and lot of other control electronics for trapping, cooling, qubit shuttling, and magnetic field controlling. And once we have all these things in hardware, we need the quantum algorithm. This is a very important part, because I think, to my understanding, this is a part where we have a quite good progress over last couple of years and decades, if I consider all platforms. And now it all depends on how good we can make these algorithms, and these algorithms has to be made in a way that we can map these Hamiltonians to this physical systems. And even there is an error, we should come up with an idea like how many ancilla qubits we need in order to make a logical qubit which is needed for a practical purpose and meaningful quantum computation. And in our setup, so as I was telling you, this 9.2 gigahertz clock transition, this is the qubit transition. So this 0 and 1, these are the two hyperfine ground state of cesium. So these are the two states we'll be using for qubit realization. And for 2 qubit or any other multi-qubit operation, we'll be using Rydberg state. So so another laser from the 6s state to 7p, and then another one. So at a higher, very high, like somewhere between 50 to 100, of this principal quantum number. So using this 2 photon transition, we'll be going into the Rydberg state. So what is a Rydberg state? So just for there are so many experts in this audience, but there are also some students. So Rydberg state is something where the principal quantum number is very, very large. And what happens if you excite the atom to a very large quantum number, principal quantum number? So basically, the wave function of this atom becomes very large, and it actually becomes few micrometer. It becomes really macroscopic. Now, if you have two atoms which are trapped at a distance of few micrometer, they can interact with each other. And this is exactly what we need in order to make a 2 qubit gate. And so this is some summary of what I was telling. This is just a cartoon of how this atom can be written, and I think I do not understand much of this, but my other theory, lot of theory friends are here. They really love it, and this is how you could write this superposition. This superposition and entangle, which is just a linear equation. So if you have these two states, so our target is to take care of this alpha and beta at a best possible level. Can you really make in a deterministic way that this alpha and beta? So this is very important, starting from the state preparation. So we have to prepare the state. Can we really prepare the state really with 100% or nearly 100% fidelity? And then after the circuit operation is over, we need to know what happened. So that means the readout. So in readout also you have to do it in a good way. And then at the heart of this is, atom-photon interaction, because as I was telling you, we do not count atoms. We count the photons which are coming out of atoms. And that's, and then we try to do some, reverse calculation and characterization to estimate the number of atoms. So this photon counting is a very important thing here. So this light matter interaction, and there are a lot of Poissonian distribution and a lot of other things which needs to be taken into account. Okay, now just to give you an idea how a magneto-optical trap looks like, you need to have 6 laser beams. So if you think of a Cartesian coordinate, so what is a laser cooling? So if you feel that you know this, just let me know. I will just skip these things. I think there are a lot of students and so on. So okay, so at any time if you so what happens is that what is a cooling? So if you know this dilution refrigerator, what we are normally used to know, how does a quantum computer look like? We know how does this what one of the previous speaker was also showing, this blue force dilution refrigerator. So dilution, please correct me, but if I understood it correctly, then this dilution refrigerator works like ambient cooling, right? So this is the way, maybe not exactly same, but maybe in a similar the way if you put your food in a freeze, it will be sitting in an ambient environment where the temperature is cold, and then your sample, whatever it is, will be cold. So laser cooling is fundamentally different. In laser cooling, we send some lasers which are near resonant to an atomic transition or an ionic transition, and then there is a direct interaction between the atom and the photon. So there is some absorption of energy, and then this absorption is decayed in all directions, and then this atom gets a momentum kick, and as a result, the kinetic energy of this atom becomes smaller. So by doing this process, we what do? We slow down the atom's speed from the speed of a jet plane, which is more than 300 meters per second, to the speed of like few millimeter or few centimeter per second. So what we are doing, we are reducing the kinetic energy by a huge amount. Now temperature is just a measure of total energy. So when we are reducing the kinetic energy, so the total energy is also getting smaller, and as a result, the temperature is getting reduced by a huge amount. And by laser cooling, we could reach a temperature of, just by Doppler cooling. So this is a Doppler cooling. We could reach, let's say for rubidium or for cesium, something around 100 to 150 microkelvin. Okay. There are other methods for doing subdoppler cooling, which could bring us to, let's say, microkelvin regime and something. And then after that, evaporative cooling to bring to nanokelvin and sometimes picokelvin. And then if you reach there, then it would be not a, you cannot describe this using a Maxwell-Boltzmann distribution. You have to use neither Bose-Einstein statistics or Fermi-Dirac statistics. But for our work, we will be using this magneto-optical trap. We will go one step further using a subdoppler cooling to get a temperature somewhere around 10 microkelvin or something, which is needed for quantum computing. So okay, maybe I skip few of these slides. Just this is an analogy. So how this works, this was first actually realized by Artur Askin and Steve Chu, and then this is something happening because of the radiation pressure. So isn't it amazing that you can control the motion of an atom, which is traveling with the speed of a jet plane with few photons, right? So it was really cool to see that, and then that time the people were thinking how, and then they found some analogy. So if you think of a picture of a comet, its tail is always opposite to the sun, and it happens because the tail consists of some collection of dust particles, and the light which is coming from sun, that gives kind of a radiation pressure that makes this tail of a comet always towards the opposite to the sun. And this is actually the first picture of, see, we report the first observation of optically trapped atoms. These were sodium atoms. And there are really a lot of other experiments which have been, leading to Nobel Prize. So you can imagine so many people were working worldwide, and most of them were starting with a laser cooling. And one of them is in particular very, very, landmark in my opinion, and the reason why we are talking so much. the origin of this was kind of starting. So there are so many, experts who are also my teachers level. So, so if I'm telling wrong, just correct me. But I think around 1935, when Einstein was not kind of happy with the quantum theory, he was telling that something is missing. Then I think this is where this all origin of these things were. And then around 64, John Bell came up with the idea that, okay, so what Einstein is saying, if you do this kind of proof, then it will give an answer whether this is right or not. So this Einstein-Podolsky-Rosen paradox, and then this so this Bell theorem. And then around 68, this Clauser came up with an idea how to test these theories in an experimental setup. And then around 72, he did this experiment. Think about, this is a time when there was no laser cooling. There was no single atoms or ion trapped in a nice setup, and lasers were just invented. So he got some first results around 1972. So then after around 10 years or so in 80s, so Alan Aspect did this experiment with the good lasers with the calcium atoms. They were using actually atomic beam and so on. And then finally, Anton Jellinger did this experiment in Innsbruck with Jianhui Pan with entangled photon pairs to really get an idea of this, what Einstein was questioning about in 1935. So I'm just trying to give a message to all the, of course this is a young, innovators meet, but there are also people who are going to be young. So just set one thing in your mind, that don't try to achieve things in a year or something, because I'm also now as a faculty at IIT Delhi, so I find it quite, not so nice when these SRC members and other, presentations, they try to see some results. So not everything will give you result in a 6 months. You see how much time it took. So 1935 to 1997, 98. And then even it took another more than 25 years to understand this is really important, and then they got the Nobel Prize. So the time scales are really huge. So you cannot, this is a domain, quantum mechanics, quantum computing, where you cannot expect that you just run some code and get some great results. So give a patience, try to enjoy the beauty of the journey, and then one or the other day will really do something great. And this is what I think we need in our country, because our ecosystem is slightly different from what I have seen in Europe or in US. Okay, so now after talking so much things, so I have started with this chamber, and now we have very nicely cooled, so about 10, 15 microkelvin. Temperature, so about 1 million of cesium atoms. And yeah, as we have designed this thing by us, so my student Kamal Kant is also sitting here, and you have also filed a patent because everything is designed and set it up by us. Some of the components we get it manufactured, and so on. So now one more thing. So when we have such low temperature, how to measure the temperature? Because the normal thermometer doesn't work. So again, we take help of physics. So this Maxwell-Boltzmann distribution. So what we do is just switch up all the traps, and then we measure how the cloud size expands as a function of time. So it's a time of flight measurement, and by fitting this Maxwell-Boltzmann distribution, we can extract the temperature of the cloud, which is somewhere around this. This is one of the temperature measurement. Now, okay, so this is very nice. So once we have all those things, what can we do with this? So this is taken from one of the review paper, and you see there are so many things which can be started from what I was just showing you in the last slide, right? That would be the starting point. And and our field was mostly doing most of the things starting from 2002, because the first experiment in optical lattice was performed in Munich in the group of Theodor Hunch, Immanuel Bloch in 2002. Is very famous superfluid to Mott insulator quantum phase transition. And there have been some discrete efforts towards working quantum information, but in 2017 there was this very nice work of making defect-free array that was giving a second boom in this field. And you see there are a lot of calculations and so on, and there are also colleagues here, so like Prasanna or something, so who are now trying to do how to do many of these calculations, what they have been doing in past in standard computer, but using a quantum computer. Just to give some ideas, so what great thing can be done, so you see we could study topological phases of matter, we could study Bose-Hubbard model really at a single atom level. Fermi-Hubbard model. Fermi-Hubbard is especially interesting for many scientists, and because it has this, the phase diagram of Fermi-Hubbard model has the superconductivity and so on. And then finally, this is a defect-free array which is needed for universal quantum computing. So as a bottom line, so cold atoms in optical traps offer a versatile platform for quantum simulation and computing. So so we very recently, we wrote a review article on that. So in this article, we have tried to show how this cold atom in optical traps field has evolved, starting with optical lattices and then slowly moved towards defect-free optical tweezers for universal quantum computing and quantum optimization. So now, how to detect an atom? Whether it's a single atom or multiple atom, when we are trapping them in optical tweezer. It's actually, if we do it correct, easier than counting many. So as I was telling you, we have to count, right? We have to count photons. And then we have to make an estimate of how many atoms were there. So if we have millions of atoms, then the question is, can we really say that this is 1,000,001 or 1,000,002? I do not know yet, but if it is like a single atom, then you see there is a noise level, and then if you have one atom, there will be a little bit more scattering. So it's a very clear signature. If you have a 2, then there will be one more step. It's like a kind of a step kind of thing what you have to see. So if your setup and everything is really done in a correct way, alignment and everything, then it is very clear signature whether you get a single atom or you don't get a single atom, right? So it's not in quantum computing, not everything is very complex. There is also a lot of nice things what you will see and realize if you reach at that point. Okay. And there are a lot of other things you can see, this histogram and so on. So for example, this histogram is showing when there is no single atom, because you see this is the level of scattered photon. This will be, of course, at a smaller scale, but now when there are more photons coming due to the presence of a single atom, you will get another histogram at a second place where these numbers of scattered photon is slightly more. Now, as I was already mentioning, in the first place, we will be getting a probabilistic loading. So how to get from this picture to this picture? So this is roughly 49 single atoms. So the problem is quite similar if you think of, you have a glass of water and you want to move it from one place to another, because these atoms in a single atoms in an optical tweezer potential can be thought as these are like a wave function. So if we move too fast, there is a chance that these atoms will spill out and we'll lose it. And if we move too slow, then it will be the coherence time will be gone. So even if we move it, then we cannot do computation. So this is a very tricky process. So some active research is also going on this, how to improve this. And think about when, for a practical purpose, universal quantum computing, we need like more than 10 to the 5, 10 to the 4, 10 to the 5 qubits. So it's not about only moving few qubits. So moving really thousands of qubits in a coherent way. And if we miss one of them, it will introduce an error. So I think a lot of AI and other things can be implemented here. In order to make even this process optimized, even before applying to quantum circuits and so on. Yeah. So okay. So then those other state like we could also get this atoms to the motional ground state by using some Raman sideband cooling and so on. So if we think that these traps which are made by optical tweezers are like harmonic oscillators and so on. And a lot of nice study can be done using this also, including this quantum walk and so on. And this is kind of a cartoon of like once we have these atoms, then if we excite them to Rydberg state, their wave function will be large enough so that the two neighboring atom can interact. And I think this is also a maybe, if I'm not too wrong, unique thing about neutral atom platform, because in this platform we can switch on and switch off these interactions. Just by switching on and off the Rydberg lasers. So this is a picture from our lab. Here you can see the optical tweezer. We just used some near resonant light. This is inside a vacuum, and then we imaged the CGM vapor what we had. And this is actually the 1 micrometer size, optical tweezer, optical dipole trap. So when we looked using a high resolution microscope objective, it looks like this. So if we zoom on this, then we see this pixel level resolve thing. So this is what is required for detecting single atoms using the photon detection. We have not trapped atoms yet, but we are working on this. And we also made an array of like 10 by 10 optical tweezers. And here you could see, for example, if you look into the surrounding, you will see the point spread function, right? You will see a lot of point spread function, and you will see that if you go to the extreme right, some places this is still good, but in some places, they have been distorted. So this is happening because of the this field of view of the microscope objective and all other things which are not uniform. And so, why I'm showing you that, because if we want to make a 1000 qubit system, we need to make a roughly 32 by 32, actually 2 times of that because of this probabilistic loading. So, a lot of things are also needed from, just classical optics point of view in order to get this quantum optics domain. I think I don't have much time, so I will skip this part bit, and I will talk a little bit of this, because here we tried to get an idea of what kind of decoherence we could have when we were addressing this f equals to 3 and f equals to 4 hyperfine states, which are our qubit states. So this is a 9.2 gigahertz state. So we used our laser, and then we used the EIT protocol, and then this is the EIT signal we had in our setup, and then this blue line is just a theory with the inputs from, there's equation. If you plug in this number, you will get this from the experiment. And what we did, we actually did some analysis on how this line shape changes if we change the power of these 2 lights. Because these 2 lights are like, one is pump and one is probe. So for any kind of a quantum computation, we have to use multiple of a series of pi by 2 and pi pulses. And that means we have to expose our qubit many times, right? And normally qubit doesn't like that. They would like to be isolated. But if we do not interact with them, we cannot either embed any information into them, or either we can get any information out of them. So this is something, although qubit doesn't like, we have to do it. And what we wanted to do, can we find a regime where this decoherence is kind of stable, so that when we are using like one circuit to another circuit, so the number of photons, because the pi and pi by 2 pulses changes the number of, and with that number of photons interacting with these qubits per circuit run changes. So can we have some kind of a steady decoherence thing, or can it changes? Because if it changes and it becomes non-equilibrium, we cannot make a trustworthy computation. So we tried to extract that. So this is a full width half maximum of EIT, and this is the Rabi frequency of control field. We did it for different probe or probe field and so on. And then we use this formula, for extracting the decoherence. This is the ground state decoherence between f equals to 3 and f equals to 4 level. And the more details about this theory you can find in this paper. This is not our paper, we just cited it. And then this is our result. So this is the decoherence rate we found for a quite a large range of this omega p is the Rabi frequency corresponding to the the probe field. And it was nice because it was also a good test for our lasers that whenever we had, the frequency stability, power stability, and everything, that we can keep the decoherence in a certain level, so that in this range we can do a lot of operations, and we can trust them. Okay, so this paper was also this studying decoherence in hyperfine ground states of cesium atoms was recently published. And in the same setup, we have also observed some slow light. Using this EIT full width half maxima, we can calculate that, and this light speed inside this atomic medium was somewhere around 4,000 to 5,000 or 6,000 meter per second. You see the light speed of light is 3 times 10 to 8 meter per second, and in order to reach achieve a quantum memory, we have to slow it down to a 0 level. And then you have to deterministically retrieve this. So this is one nice thing, and we may do this experiment in cold atoms. This was done in atomic vapor based on like the which measurement we are going to do next and how much time we get. We may do this in cold atoms and may try to move towards zero of this group velocity, and then retrieve it on demand. But I have to see like. Okay, so now I have been talking about a lot of things. So now I hope I have convinced you that these lasers are at the heart of this quantum computing with neutral atoms and ion. But lasers are also at the heart of many other technologies, starting with this photons for quantum communication. Here you see this is a picture from this China to Vienna. So satellite-based quantum communication with the lab of Anton Jellinger and Jianwei Pan. And you see, if you see it carefully, it starts with a laser, and there is a entangled photon pair generated, and it was sent. One was sent to China, one was sent to Vienna from the misuse satellite. And there are also a lot of other things like this sensing and metrology. And if you talk about the systems or platforms, these are photon-based systems or ions, atoms, or diamonds. Diamonds means diamonds with nitrogen vacancy or something similar. So they all need very, very good quality lasers. So if you would like to really set up a very strong quantum technology ecosystem, we need to set up a very strong line of laser production of this high quality. And this is what we have been doing. So in the all results, what I was showing with the lasers made at our lab. So we don't buy lasers, we make lasers, and then we control all our atoms' motions to their quantum states and so on. And we have also recently filed a patent for that. And yeah, just to show you a line width measurement. So you see the line width of this laser is about 64 kilohertz with an uncertainty of 4 kilohertz, which is quite good. Especially we made this measurement with an integration time of 20 milliseconds. That's the sweep time if you look into the spectrum analyzer. This is important because the time required for a CNOT gate using this neutral atom qubit is few microseconds. Sorry. So in 1 millisecond you can make maybe few hundreds of such CNOT gates, and then in 20 milliseconds, it would be a lot of gates. So with this, we could actually study a couple of circuits. Yeah, so it's a good. We are even working towards making it even smaller to get a high quality, because at the very core, to achieve 99.9999 level using Rydberg, you need a laser which is actually free from any kind of noise. It's not only about the noise here, but also there are a forest of noise in the background. Those things needs to be removed. There are certain ways to do that. We are working on that, and we are hopeful that soon, maybe in a year time or so, we'll be also successful in making those lasers and finally demonstrate some high quality gates. We also make a lot of electronics. That's very important because this laser. Okay. So I'll be then summing up in 2 minutes. So this laser is actually coming from a semiconductor radiation. So the current and temperature of the semiconductor has to be very stable. And this all work would have not been possible. So all these people are actually making it happen. So I just tell them what to do, what not to do, the designing and all these things. But in the real lab, I think in the previous speaker was showing these minions. So they are actually this full set of people. They don't go to sleep if it doesn't work. I think some of them are also here. They really work hard, and I'm really happy to work with them. And so we have 2 positions. So we have IIT Delhi. We have like University Queensland and IIT Delhi joint PhD program. We have a position with Matthew Davis. This is a theory position, PhD position, and this is the experiment position with Taylor Neely. I think deadlines are soon, so if you find this interesting and really want to jump into this exciting world of quantum computing and sensing, do this. So one exciting thing about this PhD position is that these are completed within 4 years, and you get a 10,000 Indian rupees top up when you are at India, and your all funding for you will be staying 1 year in Australia and 3 years in India. When you are in Australia, all things are taken care. And despite all those things, you will be completing your thesis in 4 years. We supervisors take care of that. So, yeah, that's the mandate of this program, and I'm also the theme lead of this quantum technology from IIT Delhi side. So I have to do some advertising. So okay, so I was mentioning this Prenisk, our startup. So this is a core team, and I would like to point out that our CEO, Dr. Suranita Kanjilan, she is an alumni of IIT Madras. So we are really fortunate and thankful to IIT Madras for giving us such smart people. And we have also people working in our lab which are coming from, let's say, BTech in computer science, in electronics and communication fields and so on. And some of them, so Kamal and Hemant, they are also sitting here. And so in the startup, we have this product line. We are making this narrow line with laser and few other things. And these are our set of users. We are also very thankful to DST for selecting us as one of the quantum technology startup. And you see, we got this in quantum computing vertical for developing high precision lasers and system. And this was possible just because we could show that we could make lasers and we could cool atoms to below 15 microkelvin and so on, which is really needed for loading atoms into optical tweezers. And there are a few other incubation and other funding agencies. And if you would like to join our team as a researcher or in our startup for making electronics, mechanical, or other laser related things which are needed for quantum computing, please write to us in these numbers. And thank you very much.
Sorry, in this tweezer array, so do you always have 1 by r cube type interaction, or can you also control sort of interactions between pairs of sites? How much control over interactions do you have?
So I will give you an answer from laser's point of view, technical point of view. So it depends on at which principal quantum number we are exciting, right? So if you excite to, let's say, n equals to 50, so that this wave function will be distributed over a range. And now if you go to n equals to 100, it will be even more. So I mean, for sure, we can extend it to couple of few sites, but exact numbers I cannot give you now. For that, I need to do the calculation, or some of my colleagues. It's not only confined to only the neighboring, but also few next neighboring. But when you will go to next neighboring, so the interaction strength will be decaying. So the interaction what you will having with the just neighboring will be reduced for the next neighbor and next neighbor and so on.
Thanks for the very nice talk. I was wondering how far are you in your lab from performing an actual quantum simulation experiment?
So it's, I think I should redirect this answer to my students, because you see, we have really cooled the atoms. This is the reservoir, and we also have the tweezers. So they are now in the lab trying to load these tweezers with a single atom. And our setup is, I was showing you these pictures, this high resolution objective and everything is in place. And it's not a very simple thing, so I hope very soon it can happen at any time. And the Rydberg lasers, we made the design. We need to lock it to the cavity, so we are talking with these manufacturers. So we also, and hopefully soon, but I hope in a year or so we could get our first result. And
so just one more question. Yeah. Will you be able to do it for a two-dimensional array as you showed, or one dimension is also accessible?
So we have a spatial light modulator in the lab. So we can make 1D or 2D. And we can make also in an arbitrary. For example, various optimization problem for, let's say, transportation in globe. You need some kind of a randomly, so an arbitrary. So you need to place the qubits in an arbitrary array. So those are the things also we can do, but it will be at the moment in 2D.
Okay, thanks.
Yeah.
Hello, sir. Sir, all these experiments are being done at very low temperature, like almost 0 Kelvin, if you say.
For us, it is at the moment we are working around 10 to 15 microkelvin.
Yeah. So I mean, these are very costly, and I mean, the practical purpose of any experiment at kind of room temperature like that, like superconductor, like right now that superconductors at room temperature, that kind of research, that because for lab purpose and all these things, these very high precision machines and all everything. But if you think about in practical purpose, let's say like at higher temperatures, because temperature, if you those kind of things.
So
so at higher temperature, any kind of research on that or not?
If I understood, so actually what we are doing, this is at a room temperature. If you visit my lab, I can even show you this glass cell. And what we do, we cool atoms using lasers, the way we take out energy. So we can think it as the physical setup is sitting in a room temperature, but when we are talking to atoms, we are cooling only the atoms. The chamber and everything is at an ambient temperature, right? Of course, the room needs to be a little bit, temperature stabilized, but it's around 20 degree or something. Those requirements are there, which are possible to address. Yeah.
That way, it's actually more economical in some sense than the superconducting junctions.
I don't want to make any comment. He's sitting there.
David, I mean, it would seem that way because you need to cool. Right, yeah, exactly. I mean, cool. Right. All right. Any further questions?
Hi, yeah, thanks for the nice talk. So one question I had, as far as I know, the kind of experiments being done in the look-in lab or manual NRES, they need to actually shuttle the atoms around in the tweezers to apply the gates, which then makes it really efficient. So
Yeah.
I just wanted to know, how easy do you think will it be for you to do it, or are those set up, once you have this array, is it also easy to apply the gates by shuttling them around?
Yeah, so shuttling is needed for two regions. One region we cannot avoid. This region is to make a probabilistic defected array to defect-free array, and we have already worked on it. So there is something called Sexberg-Gexton something. Sorry for my pronunciation. SG algorithm in short. So with this algorithm, we have to shuttle some traps using the spatial light modulator, and then we can make this defect free. Now coming to the second question, so this is more like, can we bring two atoms together and then entangle them for making multi-qubit gates? So the first one was demonstrated in the group of Cindy Regal, where Adam Kaufman was a PhD student actually. So now he is leading the group at Zila. So it is possible. But there are two ways of doing multi-qubit gates. One is the way you said. So this would be like a collision-induced gate. Collision-induced entanglement, spin exchange using spin exchange interaction, which is slightly slow. But if we do for like a Rydberg way, then we don't have to do shuttling for making 2-qubit gate. But I think now it is not the time to make any big predictions. So what my focus is to make the machine ready so that we can start getting into the interesting thing, and then yeah. But it should be possible if there is a need.
All right, let's thank Buddha's and that concludes the morning session. It's time for lunch. So we'll meet here back at 2 o'clock.
আমরা ওই ইমেজ প্লেনে যদি আমরা ইমেজ করি তাহলে তো আমরা দেখতে পাবো, আমাদের তো ক্যারেক্টারাইজ করতে হবে না। ধরো পোটেনশিয়ালটা আমরা ক্যারেক্টারাইজ করবো, তাকে যদি পোটেনশিয়াল ক্যারেক্টারাইজ না হয়, ওই যে তোমাকে ওই হারমোনিক অসিলেটরটা দেখাচ্ছিল, কিন্তু তুমি ট্র্যাপও ইমেজ করতে পারো। তুমি যদি ইমেজ প্লেনে দেখো, ধরো আমি যে এতগুলো ট্র্যাপ বানাই, সেগুলো যদি আইডেন্টিক্যাল না হয়, দেন না, যখন আমরা ট্র্যাপ করবো এখন, এটা আমরা এই 52 তে ইমেজ করবো, ইমেজটা করেছি টুইজারের যেটা লাইট ওটা, যখন আমরা অ্যাটম ইমেজ করবো এটা আমরা ফিল্টার লাইটে করবো। এবার ধরো এটা যদি সেম না হয় তখন কেউ তুমি ধরো জোসেফসন জানতে যদি ভাবো দুটো ওয়েল যদি সেম না হয় ইট উইল ক্রিয়েট এ প্রবলেম, রাইট? পুরো হ্যামিল্টনিয়ান চেঞ্জ হবে। তো আমি ডিটেলে বলিনি, কিন্তু মানে ক্র্যাব আইডেন্টিক্যাল বানানো ইজ ভেরি ভেরি ইম্পর্টেন্ট, আদারওয়াইজ ইউ নো এভরিথিং উইল বি স্পয়েলড। দ্যাট উইল বি লট অফ ওয়ার্ক। না এটা তো জাস্ট টুইজার, তুমি যদি ইমেজ প্লেনে দেখো ইট ক্যান ইমেজ দিস ফটোস যখন হচ্ছে, মানে জাস্ট ইউর ইমেজিং সিস্টেম হ্যাজ টু সি দ্য ইমেজ প্লেন। Actually, it would be very interesting to work on those things because it would be really great. I mean, I'm actually looking for someone who could, because I'm not an expert in this algorithm. I think he has applied for a PhD. I'm not eligible. I did a bachelor's. Okay. So I have completed my master's from that university. Okay. He has applied to this two. Which one he has applied? Okay, that will be theoretical with mathematics. And even one more, I have not applied yet for this. Okay, or any inspired fellow? Okay. You are in which group? Here? Oh, here I work with SR Hassan. Okay. So we are helping him develop quantum simulation algorithms for foaming Hubbard structures. Alright. So basically, how do you represent fermionic algebra on a two-level system? Yeah. And so essentially, my work has completely been information theory and algorithm structures. So my background was in physics, and I worked with Arun after that. And then I worked with again I went to JNC. Okay. So I've been working with algorithm structures. Okay. So but predominantly it is annealing and adiabatic combination. Yeah, it's a very interesting thing because annealing you don't have to use gates, so you can. I think there is a nature paper that tries to implement it. I think it is done on a very small lattice size also. So maybe that is something that you should replicate because that would be quite an interesting approach. Sure. You just write to me. Yeah. I'll be very happy to once the machine is. The nice thing about annealing is that you don't have to make gates. So the errors in gate you can bypass. So no, I mean there are errors. That's a different thing. Yeah. But not the gate-based errors. Also, you don't have to worry too much about the missed parameters that you have to replicate. So it's a critical thing. If you are smart, you can tweak. So because there is this paper that does number partitioning using this QED system. So they have a cavity and then they do this. Our system is not in a cavity. Yeah. So they use tweezers also. So there are two versions. So one uses Rydberg atoms to share across the literature if you want. That could be quite a nice thing because then that will show actual feasibility. Yes. No, we also need to understand what we have to do from experimental point of view. What is the requirement, right? Okay, thanks.
Sir, you mentioned something about quantum communication. Yeah. So I'm here working with Andrew and appreciate. So I'm setting up on these ways of
Anil Prabhakar. Yeah. I met him in a conference sometime ago in Delhi. Please give my results. I told him that when I will come, I will send him, but I got so sick. It would be great. How far is your lab?
It's in from here 1 kilometer, inside the campus.
Okay. It would be really great. He's in the department, right?
Yeah, he's in the department.
I got very bad and then I have to, for a meeting I have to leave tomorrow very morning. Okay. So I was not sure whether I'll be able to make it. That's why I didn't write, but it would be really great to see. I think I met him in Bangalore. There was this IISc, there was a quantum conclave, I met him there just a couple of days ago.
Yeah. So, is there, are you working in this FSO quantum communication?
See,
Okay.
so I am not
Hello?
so adulting what I was trying to say, that we are doing this just to so that our lasers are doing good and so on. So if someone tells that, okay, someone tells that they need it, then of course we will try to see this either from our R&D or from a startup. So So our main focus is not to do, really not to make a full-page computer and so on, but to make everything ready, which will be needed.
Which can be used as finally somebody.
Computing, no, we are assembling this. Otherwise, we cannot test it, right? If we don't have qubit, we cannot test it. But we are working on this, how to make a very good laser and so on in that level. But from that point, once we make this system, someone has to tell that, okay, I would like to use it for this and that. And we are making everything ready so that this requirement is fulfilled. And of course, communication and sensing. So if you have anything, just write to us, we will think can be done. This setup I was showing you, I was not sure what I will do. And it depends on what other things we have in hand and so on. But our setup for quantum memory is still everything.
I'll write you.
Sure, sure. Thanks a lot.
Hello.
Hi.
My name is.
Hi.
Wei.
Nice to meet you.
Very nice to meet you. I think you
Sydney?
from Sydney. I happen to be visiting this week.
Okay. I also supposed to go to Australia this summer. Let me see.
Oh, right. Which? Where?
To visit my collaborators in Queensland.
I see. Okay. So you are working with Matt Davies and
Taylor.
That's right. That's
We
right.
already have a student with Matt Davies.
Okay. Right.
He's about to submit in this end of this year.
I see. Okay. Yeah. I'm Trevor.
Oh, cool.
Yeah. So actually, I think someone.
I see. Okay. So you are visiting physics department?
I did my best, yeah. I was sitting here this week, yeah.
Okay, that's very nice. Are you giving it now?
I gave a talk, yeah.
Okay.
Wednesday, yeah.
I see. I just came yesterday night and I have to leave tomorrow early morning. Meeting at physics.
Okay, right. Okay.
But I will definitely look into, what are you doing with iron?
I do the GKP stuff, bosonic quantum computing.
Okay.
Yeah.
Which iron you are using?
Deuterium.
Oh, that's cool.
Yeah, deuterium is one of the simplest.
Yeah, indeed.
Simplest iron.
Yeah. You're using this hyperfine qubit.
Yeah, hyperfine.
12 gigahertz or something.
Yeah, 12.6 gigahertz. Oh, actually, since you mentioned this, so you on the slide you mentioned there's this 12.6 seconds or something like that.
Yeah.
12 seconds.
Something like that. Yeah.
This is which atom?
Cesium atom.
Who has
recently this Manuel Andres, they have this paper in archive. Couple of months back.
12 seconds.
Yeah. One of the longest.
10 gigahertz.
9.2. That's the cesium this clock transition.
Did they do anything special? Because I found that.
Yeah.
Yeah, because
they didn't wrote too much detail about this particular transition.
Because I would think that you need to have a very good microwave source to do that.
Yeah,
because the phase noise is.
Yes, it has to be very good. I'm not sure whether they have done it with a microwave or two photon laser. I cannot remember it at the moment. But if you just search with 6,100 atoms and then Emmanuel Andres, you will find it. They have written a lot of things in that paper. So it should be there. I think they have some measurements.
Okay. Do you want to grab lunch?
Yeah.
So
let me just keep it here. Yes.
All good to the mind. Yeah, because the phase time is
questions during the talk are okay, right? Sorry. Questions during the talk. I got it right.
How many mics are there?
We have 2 mics. Are you the mic in charge? Keeper of mics? Holy keeper of mics?
Supposed to be a volunteer, but I don't know what I'm doing.
Yeah, so it can help me in the that's been the story of my life. Yeah. Oh, very nice. Yeah.
She pointed out that there is something that we discussed earlier. This is actually not 3 people, it's 60.
Okay. So is there any way you can make it 3 people? Okay.
Then you have more noise.
Yeah. You can put a correction below that. I heard, but I heard that looks too good.
It is true.
It is too good to be true.
It is true and it is too good.
It's true? Okay.
Yes, it is true.
We should start. Then a minute. Call 2 minutes? Okay. 5 more minutes.
Yeah, max. I'll make one more announcement.
Yeah. Clap.
Yeah, I have a mic there.
Good. Very good. Really? Shall we start?
Take this one. It's the same thing, but it's a timer.
There's a timer here?
No, I'll control the timer.
You're controlling the timer. Okay. Should I start at 2:05?
Hello.
So welcome to the post-lunch session. of this lovely conference. So the first talk today, talk now is by Professor Sheetal Kumar Jain from IISc Bangalore. So the timing is from 35 minutes and then 5 minutes questions. What we will do is we will see to it that only if there are clarification sort of questions then we ask during the talk, and at the end we can ask the questions. Okay? So, please, the floor is all yours.
Thank you for the introduction, and thanks for giving. I think I'm audible. So, and thanks for giving me this opportunity to present my work here. So, I'll talk about nuclear spin hyperpolarization using diamond defects. Now, hyperpolarization is now broadly used in NMR. Specific mechanism that I'm going to focus on is something called dynamic nuclear polarization, which many of you may be familiar. I'll briefly introduce that, and then I will come to the point that instead of using the standard kind of DNP, we can now use NV centers as one of the polarizing agents that we call in DNP community. So the idea is that in NMR we are in a very low sensitive regime because of the weak Zeeman splitting. So signal to noise ratios are poor. We need long signal averaging time, and there are multiple solutions, and one of them, which is probably the most popular one, is nowadays is DNP. And the way it works is that at the same field on same temperature, if you see electron spin polarization, then because of this higher gyromagnetic ratio, it gives a factor of 2, order of 2 enhancement in sensitivity. But the point is that we need to be able to transfer the polarization of the electron spins to the nuclear spin. Now, most of the NMR samples we deal with are diamagnetic samples. So we need to have a paramagnetic source inside. And the way currently DNP works is we make a solution of nitroxide or carbon-based radicals that are stable. We solubilize them in water and glassing agent. Glassing agent can be glycerol, can be DMSO, or depending on the NMR sample. So we make a glass of those, and we mix, and then we mix our NMR sample in this mixture. So total NMR sample becomes the mixture of 3 things: the target sample, the paramagnetic center, and the DNP solution. And then we make use of the coupling of this paramagnetic center and the protons that are present in the DNP solution. So before going, so for that we need these different kind of DNP mechanism. So if the 2 spins are coupled, suppose the radical concentration is low enough that we can ignore the paramagnetic coupling, dipole-dipole coupling between 2 electron spins, then it's a 2 spin system with 1 electron, 1 nuclear spin, and you can irradiate on these one of those 2 forbidden transition, which becomes allowed because of the coupling between them. And then depending on which condition we irradiate, we get this kind of field or frequency profile, and this is called solid effect DNP. And we know by this mechanism, I'll go into the details of it, but if we increase the field, this transition becomes more and more difficult, so its efficiency goes down with the magnetic field. And in NMR, we need chemical shift resolution, so high magnetic fields are desirable. So this mechanism has that a problem that if you go higher in the field, then the efficiency goes down. The other mechanism is known as cross effect, and actually this is the one that is currently being used in most of the DNP experiments. It uses 2 electron spins and 1 nuclear spin, and when you have this system, you have these 8 energy levels, and if the 2 electron spins, their Lama frequencies or their net frequencies are, there is a difference between the two, and that difference matches to the nuclear Lama frequency. In that condition, you hit this kind of matching condition, where this transition of flip happens, almost these energy levels get fully mixed, and we get a very efficient polarization transfer. So the condition for this is that the 2 electron spins Lama frequency should be different by a nuclear Lama frequency. Okay, so these 2 mechanisms are well understood. I will talk about both of them a little bit, and then we will try to see can we use the similar mechanisms in NV center. So before going to that, one key point is that we are not only interested in polarizing one spin or one carbon or one, we want to polarize the bulk of nuclear spins. So the way it works is that we mix this little bit of paramagnetic center, we irradiate so that this polarization transfer happen, and then the protons, they are because of their high coupling network, their strong coupling network, basically there is something called nuclear spin diffusion that takes place, and then we can do finally cross polarization, which is well known in NMR community, from proton to the target nuclear spin, which can be carbon, silicon, aluminum, or whatever. So we transfer that, and that's the normal procedure with which we can do the DNP, right? So that's why the glassing agents have an optimal number of proton density, and there is a lot of research on that. Design of radicals is another research area, so that I'm not, those parts I'm not touching in this talk. Now, the experimental setup looks something like this for DNP. We have the standard NMR, but in addition, and the console. So these are the standard NMR parts, and then we need to have a microwave source with high power, because we want to target these solid effect or cross effect. So we need like few watts of microwave power at 263 gigahertz if we are at 9.4 Tesla. So it's in millimeter wavelength regime, and that becomes tough. So that's why we need these kind of sources. This was proposed by Bob Griffin at MIT. He was the one who in the beginning showed that gyrotron can be combined in NMR to give high signal enhancement using DNP. Additionally, we need these cooling system, because in solid state NMR we spin our sample while and we spin at in normal conditions we can spin up to hundreds of kilohertz, but in DNP conditions nowadays people can spin up to 40 kilohertz. So we want to spin the sample at 90 Kelvin. So the way it works is that we use 3 kinds of gases, bearing and mass gas, to drive the spin, and then we use a VT gas. So we use this heat exchanger. We make nitrogen cold enough but not liquid, and then use those gases to spin the sample, and that way we achieve this 95 Kelvin temperature. The other kind of setup which are now coming up but not that common, those are called pulsed DNP. So in gyrotron basically there is only this continuous microwave, and you don't have much scope for frequency change either, it's fixed. But this kind of setup, you can have a low power microwave source, solid state diode based source, and then we can get this amplifier multiplier chain. So we start with low frequency microwave, say 9 gigahertz or something like that, and then we multiply it till we achieve the desired frequency range, and then we use this quasi optical setup to transmit the microwaves, and then there is a corrugated waveguide that takes the microwaves all the way to the sample. And in the advantage of this setup is that you can actually detect EPR also. So you can do NMR and EPR both simultaneously. This is the zoomed in part of the probe here. So basically, because there is low power, it's in milliwatt regime, we need even lower temperature. So we go to liquid helium temperature 4 Kelvin, and in that case the RF circuitry becomes simpler because we can live with this inductively coupled setup here. So this is our detector in a way, the coil, and this is our sample coil. So we just vary this. This is homemade capacitor which we can control even at low temperature. We can vary so that we can tune and match the frequency. Okay, so this is the second kind of setup. This is cheaper. Disadvantage is lower power, and advantage is you can play with the pulses. You can do spin dynamics. And now I joined IISc 3 years back now, and what we currently have there is this. So we have half part, which is the standard NMR part with DNP written on it, but it's not DNP yet because we don't have a microwave yet. So we currently we have this 9.4 Tesla magnet. It's 89 mm bore size. It can spin 42 kilohertz at room temperature, triple resonance, and we can go to we can use cold nitrogen gas, but only 1 out of 3 flows. But then we have plans, and those are almost approved now, that we will get a microwave source, but the cheaper one, not the gyrotron one, and a DNP probe with microwave guide inside, and then the cooling unit, so that we will make the setup soon. So if there are some interesting samples for that, yeah, please contact me. So then now I want to go into the details of the microwave, into the mechanism of DNP, because that will lead us why I think that or why many of us now think that NV centers probably will be better for DNP. So the idea here is this is the Hamiltonian of a coupled electron nuclear spin system, and if we radiate microwave, then this time dependent part is there, and it's for this audience should be quite straightforward, that we go to the rotating frame and then we make the Hamiltonian time independent, and then the Lama frequency part goes away with the offset. And then to make the life slightly easier, we go to the tilted frame, so that this and this becomes resultant SG, and then we get this omega effective here. Now this is important because omega effective is now microwave amplitude and the microwave offset, nutation frequency basically, and then we have this kind of Hamiltonian. Now we can use something called average Hamiltonian to deal with this. So the way to do average Hamiltonian is we again make this doubly rotating frame, because these are the two large, under the assumption that these two frequencies are larger than the hyperfine interactions, which is mostly true for high field cases. So we do this frame transformation, and when we do the frame transformation, we can see here that if we, before doing it mathematically, we can see that this term will modulate with none of them because it commutes with this. These two terms will only modulate with S part or I part, right? So they will modulate only with one of them, and this term will modulate with both of them. Now, if we want to take, after modulation, if you want to take the average part, there is no way we can have this time independent because there is only one time dependency. However, this part, because it has two time dependencies, one can think that if we make the right matching condition, this can become one of these or multiple of these kind of operators. These are called zero quantum and double quantum operators. So what happens is that if we go to that doubly rotating frame, and if you only look into this term becomes 4 terms, and they have kind of time dependency, obviously, the difference and sum of the two. So when we match the two, then this part becomes time independent. And this is the Hamiltonian that drives the polarization transfer. because it mixes that, it drives the double quantum transition which I mentioned in the beginning. So if the double quantum transition happens, polarization transfer works. Okay. So then the matching condition from that theory turns out to be this, that the omega effective of electron spins should be equal to nuclear Larmor frequency. And that's exactly the solid effect condition if we assume that this part is very small. The microwave amplitude is very small, then you have two conditions. When your offset is at plus or minus of nuclear Larmor frequency, you get positive or negative polarization transfer, which is exactly what that field profile was showing in the beginning. So one can now move one step ahead and do the evolution of density matrix under this Hamiltonian, which is effective Hamiltonian. I haven't shown the Hamiltonian here, but it was there in the last slide. And then what we can see here, that there will be these modulations, polarization transfer from S to I spin, and they will have this, the first maxima will be at this time. So the B here is the pseudo-secular hyperfine coupling between the electron and nuclear spin. This is offset, and this is basically effective nutation frequency, and this is the microwave amplitude. Okay, so basically stronger coupling leads to faster polarization transfer. No surprise there, but we can just see it exactly mathematically like this, and then these are the experimental data collected on 6.4 millimolar trital. It's a carbon-based radical. Okay, so again, this I should have been careful. They call DNP juice, but it's basically a mixture of glycerol, water, and D2O. So they call that DNP juice because it works best. And then at 80 Kelvin at X band. So, and then when we do, these are experiments, and this is what theory predicts for different microwave amplitudes. And I did not introduce novel here, but it's just like solid effect. Only thing is that instead of having just one irradiation, we use X and Y, two irradiation. So the theory remains exactly the same. The spin locking or the spin locking efficiency goes much higher in this case. That's the point. Then again, using the same theory, we can now use the powder averaging also by putting the powder dependency of the hyperfine coupling, and this is the formula that we obtain, and we can simulate. So we plot this, and then these are the experimental data for different combination of the offset and the microwave power, and the rates are in order that the theory predicts. Okay, so this is for one electron, one nuclear spin system. Now with this, I want to come to the NV center. So now when we see NV center, this I don't have to explain here at all, but the point here is that we can optically pump it, and even at room temperature we can get large polarization in these if we focus here, right, in this part. So the DNP community's attention is on this part here. So that will be clear in the next slide. Basically, if we zoom in this part, then in the quantum sensing or magnetometry, they use the fact that the +1 and -1 are 2 times gamma E B naught apart. So if you change the magnetic field, then you can detect the difference between the two, right? And if there is no magnetic field, then they are just zero field splitting apart from each other. So you see the dip in the fluorescence here because of this transition that you have. So if you have your microwave irradiating on one at around 2.8 gigahertz, and then if you sweep the magnetic field, you get this kind of thing, right? From there you can predict you can determine the magnetic fields. However, what we want is that after optical pumping, everything is in this level, right? So it's already hyperpolarized. The electron spins are not at thermal equilibrium anymore after optical pumping, and we want to harvest that at room temperature to improve NMR sensitivity. And so if we see, I saw multiple recent reviews on NV, and all of them are focusing a lot on its sensing applications. It can sense the orientation, it can sense temperature, static magnetic field, fluctuating magnetic field, electric field sensing. But now probably things are changing, but hyperpolarization, this is not that commonly used, at least at high field, where NMR sensitivity and NMR based characterization becomes important. So how do we do that? Now we know the previous analysis. So now we focus on the ground state, and now I will assume that it's a optically pumped system. So the population is here. So a coupled system, then we have these 6 energy level because it's spin 1, and the nuclear spin we are assuming is 13C for the time being. So for NV 13C system, these are the 6 levels, and if we can somehow make this as a pseudo spin half system, then our theory should work, and we should be able to find out the right matching condition at which, if we irradiate the microwaves, we should be able to transfer the polarization. So we worked out the theory. Shubham here, who is in the audience, and he is also presenting the poster, this is his work. So the first step is same, we went to the rotating frame, but now the microwave frequency we can select, because we can select only one of the 2 transitions. The 2 are separated by the magnetic field. So if we choose this transition, the green one, 0 to 1 transition, now we can use these basis sets. So now we can use sigma x for 0, 1, sigma y, and identity, and sigma z. Those matrices will look something like this. So if we use that, then we rewrite the previous Hamiltonian so that it has this -1 state separate, and then this part separate. But now if we see this part, because we are irradiating at this channel, and we are not touching at all this transition here, then one can work out the same theory. And to save time, I omitted the theory, but this work is published. Actually, I didn't put the citation, but this work is published. We work out the theory, and it turns out that the polarization transfer has this profile with time, where this BXX, unlike the previous case, it was just the hyperfine coupling, pseudo-circular hyperfine coupling. But in this case, because of this change here, we have that it depends on both type of couplings, the secular and pseudo-circular couplings. And these angles, sin phi, sin theta, they depend on factors here. So it's basically, it is a function of zero field splitting, the Lama frequencies, so the magnetic field, where we radiate the microwaves, and the hyperfine couplings. But we know how does it depend upon those. And with that, we did the simulations. So at X band, at 9.4 Tesla, which is our target field. Okay. So we see here that these numbers are here the microwave amplitudes. So if we increase the and the couplings were assumed this. Now here I'm assuming the hyperfine couplings in 1 megahertz, 2 megahertz regime. The reason is that if the hyperfine couplings become strong, then something called spin diffusion barrier inhibits the hyperpolarized carbon to transfer the polarization to the next carbon. And if that does not happen, it's of no use from NMR point of view, because we want the whole polarization. The spin diffusion process basically doesn't happen. So that's why these are the carbons that we are interested in. And in these carbons, we see that if we increase the microwave amplitude, we get faster polarization transfer, but we don't get as much as the low power. So there is a trade-off. You go slow, but then you are fighting with relaxation process, or you go fast, but then you cannot achieve that as much polarization transfer. At 9.4 Tesla, because the field is now quite large, the Zeeman interactions are large, so we always are in weak microwave regime, right? The microwave frequencies are very small compared to the nuclear Zeeman interaction, so we do not see this effect, but we do see the change in the rates. And then these numbers are realistic numbers because even with the gyrotron, we do not get more than 5 megahertz of microwave amplitude because of the losses that happen during the transmission from gyrotron to the sample. Okay, so then we did the numerical simulations using the brute force, like giving the Hamiltonian and just evolve, and our analytical simulations, and compare the two. And here what we are doing is that this is the offset. So we know that in 1D offset there should be two conditions, plus and minus, at plus Lama frequency and minus Lama frequency, nuclear Lama frequency. But then if we vary the hyperfine pseudocircular hyperfine coupling, we see that, and this is not surprising because at very low pseudocircular hyperfine coupling, we do not see polarization transfer, because that is the interaction that drives the polarization transfer. We saw that it depends, the time depends on this. The polarization transfer rate depends on this interaction. Okay, so this is what happens here. But if we vary, what we see here, that in this case we vary the RF amplitude, and we see the shift here. We see the shift in the NV case. Okay, so what we predict by the theory here at the two fields, it matches with the numerical simulations, and we additionally we see this little wiggle here, which is, we are not absolutely sure what it is, but it looks like that in the theory, if we are slightly away from the matching condition, there is a sink dependency comes in, and that leads to wiggles, and it's because of that. But we are still investigating, because this has been observed experimentally also, that there is some wiggle here. Okay, and then I'll see the last part, and this is not published part now, which is the cross effect, which I mentioned earlier, and how can we use cross effect for NV-P1 system. So the cross effect Hamiltonian, now we will have the green part which is for say NV, and the yellow part which is for say a coupled P1 system. P1 is spin half but not optically active, and it has been mentioned in this conference before. So that the two are coupled now. So there is a coupling between them, and these two terms define the coupling between NV and P1 centers, and these are the hyperfine coupling of NV with 13C, P1 with 13C. Okay, so now in order to use the similar kind of formalism, what the first step here is to go to a zero quantum double quantum basis of two electrons, so NV and P1, and in this case, in this calculation, they both are spin half for now, right? So if we do that as a first step, we can rewrite sum and difference of the two. Okay, and then we can do this to all the terms, right? A1 and A2, sum here, difference here, sum here, difference here, right? Now what it turns out is that this part commutes with this part completely, because this is complete zero quantum, this is complete double quantum. So the two commute with each other, and if they commute with each other, we can treat them separately. So then we did so, and if you look at it closely, it looks exactly the same Hamiltonian as the spin one, two spin half coupled that we did solid effect theory. There is SG term, IG term, secular hyperfine, pseudo-secular hyperfine, and without any microwave, there is inbuilt drive like term. In principle, that means you do not need microwave drive to achieve cross effect, and the match remains exactly the same. So the matching condition becomes this, and actually this matching condition, if you ignore this coupling, if you assume that electron coupling is very small, then it's exactly the cross effect condition. That difference between the two electron frequencies should be equal to the nuclear Lama frequency. So it matches there. And then the time turns out to be that it depends on the so the polarization transfer rate, it depends on the difference of the two hyperfine couplings. So NV to 13C, P1 to 13C, those two couplings, how different they are, the polarization transfer happens with that rate. So that means if the 13C is coupled equally to both of them, there will not be any cross effect. And there is a scaling factor. I did not cover this, but I just want to see that we actually wrote the whole theory part for NVP1. This work is in progress now. We are writing it, but the exact matching condition turns out to be that this part should be equal to this part. And here two important things. One, of course, this D and J are the coupling between NV and P1 that play a role. This is the difference between their two Lama frequencies because of the G. And then only the NV13C hyperfine coupling comes into the matching. Okay, yeah, this is almost done. So this comes into the matching condition. The polarization transfer rate or the time that depends on the difference here, and it turns out that it basically it depends on the difference of the two hyperfine coupling as we predicted in the last slide. But because these terms will depend on the orientation, so basically the matching condition for cross effect in such cases will depend on the orientation as well. And one key part here is that one motivation of doing this kind of cross effect is to bring the NV center polarization out of the NV lattice. Is a big challenge because it's nuclear spin free kind of environment. There are 13C, but not enough so that the spin diffusion can bring the polarization outside the NV, outside the diamond. And until it comes out, we cannot use it for the sample material characterization or proteins. So we need to hyperpolarize those. But what this mechanism tells us is that if there is a paramagnetic center located outside the diamond, but it is coupled to the NV, there is a non-zero coupling, then NV center does not have to be coupled to the nuclear spins located outside directly. You don't need that because it only depends on the difference of the hyperfine coupling. So one needs to work out on this part because there is no relaxation taken into consideration, and that is our next step. So yeah, with that, the novel and the solid effect part I did when I was a postdoc with Bob Griffin, and Jennifer was involved in that project. Thanks to them. And the NV and P1 part, most of the work I shown today is done by Shubham, and he has a poster here. All the details he can tell you. And Suraj is also involved in a decoherence project where we look into the decoherence time of the NV center caused by the P1 and 13C both, and we work out the similar theory. And because NMR decoupling is routinely used, there are many techniques that we think are promising to increase the NV coherence times. And IISc for funding, and this is my group, and thank you.
So we are open for questions.
Thank you for your talk. I wanted to understand what the prospects are for using this in applications, and I just wanted to decode things that you were saying near the end. Suppose you wanted to, first example, where you have a diamond with a substantial density of NV centers, and you wanted to use it to hyperpolarize all of the carbons, in the carbon 13s in the entire crystal. Is there really a prospect for doing that?
So the focus was that if there are these nano diamonds with low NV density, so that NV coupling we do not assume. If NV are not.
Okay, so you're saying you just don't want to answer that question because it's not the kind of thing you've been studying.
No, so basically I can say that if all the NVs, if there are multiple NVs present, and if you want to hyperpolarize using multiple NVs, then the field profile that I produce here, they will not work because they all will have different orientations. So the matching conditions for each will be different.
Okay.
So that part is true that it will work for one of them. We need to work out the powder averaging or the distribution of NV orientation and then modify the theory.
Okay. Let me ask an even more tangential question. There are popular paramagnetic color centers currently in silicon hosts. is there prospect for silicon-29 hyperpolarization via those modern NV centers, not NV centers, but carbon, what are they, die vacancy centers in silicon?
The problem is that the coherence times of these defects in those materials are not long enough for, there is a competition between the polarization transfer and the decoherence. And it turns out that we are not in the sweet spot yet. So that is a bigger challenge, and that way that's why NV is better because.
Okay, but you don't say absolutely no.
No, no, I don't say no.
Okay, no. Thank you.
Thanks. So the matching condition corresponds to having the XX plus YY effective Hamiltonian, or what? Okay. So if I alter that condition, I can also produce some combination of XX plus YY, XX minus YY. I mean, any combination of those four terms you had.
No, not any combination. You have to have a particular combination. Sorry, where did I show them? Okay, I can show it from here. Yes. Okay, now I'll go. Sorry. Basically, you have to have either 0 or double quantum. You cannot do both because then then they will cancel each other. You can see from here, you can either do this transition or this transition. So XX plus YY and XY minus YX, those are fine combination. Or XX minus YY and XY plus YX, those are fine combination. If you do the other way, then it's a problem.
So can I vary my parameters to interpolate between XX plus YY and XX minus YY?
That's what you do.
Okay, that is the XX.
That's what you do.
And so just a quick thing, so what is the initial condition for the nuclear spins?
We assume very small polarization, so we ignore the polarization of the nuclear spins.
So it's like a mixed state, is it? Or?
It's a mixed state.
Okay.
Are there any more questions?
So same question as with the matching condition, like you have 4 levels.
Yes.
Like, so, yes. So what exactly happening? Like you have 2 levels fixed, and you are driving 2 of the levels such that it matches in rotating frame, the energy levels matches, kind of like that.
Yes, I did not show this slide, so I will show you this. Basically, what happens is what happens is this is the 2 density matrix. This is SG. Suppose this is electron spin density matrix, right? And this is nuclear spin will look like, right? By this logic. Now, if you drive either this transition or this transition, so basically either you make this operator or you make this operator, right? So if you make this one, then you are in this regime, okay? So then you will create, okay? So you write your SG as this, right? Your SG alone, it can be written as sum and difference of SG and IG, right? But if you have only these terms working, then what will happen? Only this part will change the sign, this part will remain as it is. The moment you see this, now you convert it back, you get IG. So you started at SG, you ended at IG. The way you did it is that you made sure that your Hamiltonian is these 2 terms survive. Or 0 quantum, then the Hamiltonian, these 2 terms survive. That's how it works.
So we'll have one last question.
So at one point in one of the Hamiltonians you wrote, you immediately looked at the Hamiltonian and said, this is a 0 quantum part, this is a double quantum part.
Yes.
Hence they commute,
because double quantum part is these 4.
Okay.
0 quantum part is these. They will always commute with each other. If you break this matrix such that only these are non-zero and only these, if you can do that, then they will commute with it.
Okay.
Yeah.
So if there are no more pressing questions, we can move to the next talk. So the next talk is by Professor Arvinda from IIT Tirupati. Just because you are from here, we are not going to give you an extra.
This is yours, right?
No, it's okay. Okay, so first of all, I would like to thank the organizers for this wonderful conference or workshop where the intention is to meet the young investigators to discuss what they are doing and to collaborate and other things. So, in basis of this and whatever the mails I received from the organizers, I thought of presenting something which not one topic, instead of that an overview of what are the things which I am doing, and I am focusing on one aspect. When I am trying to look for what is the thread in which some of these works which I am doing, and what is the thread or the central theme which is running in my mind over the years, which is motivating to work on these topics, led to, okay, so this is what I am, the central figure in what I am working is what I call it as a quantization. So the quantization is not the regular type of quantization which we think like h cut tends to 0 or reverse kind of things. Instead, I am looking for, there exist some classical structures or the structures, and what type of, how do I quantize those structures essentially. Then I have to define what do I mean by classical structures. Essentially the classical structures, what I am defining is nothing but probability theory and the commutative structures. Shall I use my system? If you No, I can use this. Just give it. No, again it will disturb the flow. That's why everything will be, I will be going in some flow and everything will be changed, which I don't want it. Okay, sorry. Yeah, you can connect. Still works? Yes. No, that is there. That is not there. Chalo, if it. Okay, leave it. Hey, wait. Yeah. Thank you. Okay, let me learn this up and down. So this is the central picture which I am looking into, in the sense that there exist some structures on the classical probability or the structures lying on the commutative structures, probability theory and the commutative structures. Moving? Okay. Oh, sorry, I don't know why. No, I didn't do anything. No, full screen? Achha. Okay. Sorry, I showed everything. Okay, so then I don't want again the commutative and non-commutative structures. Let me go. So in this thing, what I am looking is the three aspects, at least in this talk, which I am focusing is three aspects. One is, the first aspect is entanglement in the dynamic, which again got motivation from the teleportation. When we some 4 or 5 years back, maybe 5 years back, Nicholas Gison wrote an article saying that the entanglement theory, which has originated in some sense that in the teleportation protocol or the paper, had an entanglement in two aspects. One is in the entanglement in the state, and another one is the entanglement in the measurement. So his claim was that we were understood a lot of things about the entanglement of the state, whereas we lack entanglement in the type of measurements. So he began to understand or look into the what type of entanglement in the measurements can be associated, etc. So at that time, I was thinking into there is one more aspect of entanglement which is in the dynamics itself. So which is there are different ways, and there is no unique way of defining the entanglement in the dynamics, because it also relates with the entanglement with respect to state also. So that was the one of the question which I started trying to understand. How does the entanglement in the dynamics has some importance in the overall dynamics or overall the studies we are having. And the other one is I will try to give some way how these two are connected in the same thing, and the 2 points which I am looking is thermodynamics and the complexity. Again, the thermodynamics, the reason I was looking into is that the thermodynamics is the one way to define it is a set of constraint on an operational theory. Let us define an operational theory which I was motivated from the axiomatic quantum theory, and once if I define the thermodynamics in the axiomatically, and the laws are nothing but the constraints on the set of transformations. So the classical thermodynamics can be defined in that way entirely. If that is the case, how does the entanglement, if I do that quantized structures, what and all the changes is going to evolve. So this is the one more thing which I was worrying, and these two led me to try to understand the notions of complexity in quantum, and based on these notions I will try to explain what the work which I have been doing, and then at the end I would also like to say what are all the current works and the future works which I am doing in this direction. So let me begin with the dynamics. My dynamics is the simple unitary dynamics, is also called the circuit dynamics. So here you can think that there is some 4 spin-half systems or the qubits, and these are the unitary operators. I don't know what color it is looking into this one. At least in my slides it is a green color. Okay, so this color is a unitary operator, and then this is the half of the unitary dynamics, and then this is the 2 layers constitutes the whole unitary dynamics, and here I represented the unitary dynamics of 2 time steps. It is nothing but the discrete evolution. So one of the interesting quantity which I am looking, okay, this red is red. Okay, so the interesting quantity which I am looking into is the correlation function between these 2 operators. So here and here, so red is the U diagram. So I am looking into I am starting with some operator here, and I am evolved into this many body circuit, and then I am looking into another operator, and then I wanted to calculate the trace between these 2 operators, the correlation functions, and just being the unitary. So these are the tensor network diagrams, and the contractions nicely produces the unitary dynamics. If it is just the operator is unitary, this and this constitutes and just gives you the 2 lines. Because of that, I can get a nice diagram, but still it is more or less unsolvable for the many body case. So what was the idea is that if somehow this and here and this one is contracted, so can we somehow erase these pictures, and if somehow erasing this picture we might make the things very nice to solvability, provides the solvability. And this was mathematically what one does is that, let us consider that picture is actually representing, take the unitary operator and do the realignment. Realignment is nothing but changing the indices. It is another form of partial transposition. When you are doing the partial transposition, you will change alpha to I, whereas here you are changing alpha to j. So this is one of the matrix rearrangement or reshaping. If you do that, in the tensor network contraction picture, it nicely gives this structure. So, and because of that, one gets very nice circuit which is calculatable, in the sense that one can easily calculate, because the entire correlation function depends solely on this operator, and this operator, the important thing is the correlation function of the many body system is depending upon a function which is acting only on the unitary operator on the 2 particle. And this is nothing but this m plus and m minus are nothing but CPTP maps, so that what happens, the entire dynamics is governed by this CPTP map. And let us study what this CPTP maps and how does it, what it is interesting and other things. And so that previous CPTP map can be easily written as a matrix form. These are the matrix form of the map. Okay, so that's where I stop. I give a, that means what I mean to say at this point is that there is a many body circuit and I want to calculate the correlation function of the many body circuit, which can be easily calculatable by just a function under 2 particle unitary operator. So that's where I am standing it. Now I'll just deviate a little bit and I would like to go for classical dynamical systems theory, especially what is called classical ergodic theory. So let us consider, just we can see it here, mu is some measure, we can any measure, probability is a good measure, and T is a measure preserving transformation in the classical. So they have a hierarchy of how the system's behavior, ergodic, weak mixing, strong mixing, Bernoulli. Rather than in this way, I would like to say it in this way, which is much more easier for the physicists to understand. Let us define the correlation function, and the system is set to the ergodic if some kind of average tends to 0, average tends to 0 at an asymptotic limit, and there is a weak mixing where there is a mod tends to 0, and a strong mixing which says that instead of some kind of average, actually the correlation function itself vanishes, tends to 0, vanishes over the asymptotic time limit. And the final one is the Bernoulli, which is a correlation function vanishing kind of immediately, means after one time step. So this is the classical ergodic hierarchy, and hierarchy is a hierarchy in the sense that Bernoulli implies strong mixing implies weak mixing, but converse is not true. We have an example, and weak mixing implies the ergodic. So this is the classical structure. So now we have a many body system, and since the correlation function is easily calculatable and just depends upon a channel defined on the 2 particle system, what is going to happen is that the eigenvalues of the channel determines more or less entire ergodic hierarchy. So whether just the eigenvalues, whether it is a unique one, and okay, the spectrum of the channels is such that all the eigenvalues are less than or equals to mod 1. That's a property of the channel. And so you just look into the eigenvalues and you can find out what is the nature of the ergodic hierarchy of the many body system. So this is about the this is what the ergodic hierarchy within the Hamiltonian dynamical system. Now what is the relation, and why I am thinking about how I am bringing the entanglement into these things is that so I defined something called the operator, which was showing to be I showed some picture, and then if it is realignment is also unitary is what I called it required, and those operators are now called dual unitary operators. But the interesting fact is that if I define the unitary operator and with a Schmidt decomposition, and one can define the operator entanglement associated with the entangling with the unitary operator, it turns out that this operator entanglement is maximum if and only if the unitary operators are dual, in the sense that whatever they are calling the dual unitary operators are maximum operator entanglement operators, which is giving some kind of solvability. So there was the structure up to mixing, okay. So and then there is we try to add one more layer, which we call it as a T dual unitary, that is in the sense that we just define the unitary operator whose realignment need to be unitary, and let us put one more condition saying that unitary operator whose partial transposition is also unitary, partial transposition is also unitary operator. Let's take a unitary operator and do its partial transpose and look for whether it remains to be a unitary. In general, it won't be. And if we can able to construct such unitary operators, and those operators are called a T-dual unitary operator. Now again, I will bring one more feature of the dynamical entanglement, which is entangling power, which is an average entanglement produced by an unitary operator and acting on the product of R random distributed product states. And if the entanglement measure is considered as a linear entropy, then this has this entangling power has a nice closed form expression. And the important thing is that if the unitary operator which is used, if it is behaves both as a dual as well as T-dual, then it is called T-unitary operator. And the most important thing is that this serves as a Bernoulli, in the sense that the correlation function of a many-body system constructed from this unitary operator, the correlation vanishes instantly. So that's how these two connections are being connected, and this is and also we provide a sufficiency condition for a system to be mixing in terms of entangling power. Whenever the entangling power of these 2-qubit unitary operators or 2-particle unitary operator is greater than this quantity, Q is the dimension of the local systems, and then it is guaranteed to be mixing. So sufficiency condition. This is all about what we did it in the Hamiltonian dynamics. Now let us define it on the channels, in the sense that let us consider a CPTP map is a CPTP map which itself acts like a dynamics. So then rho prime is acting on this, and then you can have the matrix form, the operator form of the unitary of the channel. L represents the operator form of the channel, and the spectrum of this channel, we wanted to look and then say that whether the dynamics is ergodic, mixing, or Bernoulli, or whatever the ergodic hierarchy of the transformation. Here the transformation is the channel itself. Can we construct an ergodic theory of the most general quantum dynamics, and what it will be and how it behaves, and what are all the constraints and associated with these things. So let me define in terms of channels. So there are ergodic channels and mixing channels. These are the two things which I have focused more. So the channel is ergodic if there exists a unique state such that there is a state. Okay, so also the properties of channel says that there always exists one state, one unique state. So one unique state which is an eigenstate of a channel. Now whether it is unique, that means in terms of spectrum there is only one eigenvalue whose value is equals to 1. That defines what is called the ergodic in terms of the channel is ergodic in terms of the dynamics. If I see it in terms of the trace norm and how it is approaching, it's something like that average. This is I've already defined in the previous slide. This is the one. This is like an average action of the channel. So this average action of the channel tends to 0. Similarly, we define the mixing as that. So how the distance between the fixed state versus the asymptotic iteration of the channel should tends to 0 for all states. If we define it in terms of spectrum, actually this is the definition of mixing, and in terms of spectrum, the channel has only all the eigenvalues of the channel is mod less than equals to 1, except the first one. Means one, always there will be one eigenvalue whose eigenvalue is equals to 1. So, sorry. Okay, some of the results in the Hamiltonian system, the sufficiency condition is obtained with respect to whenever the entangling power of the 2-qubit unitary operator is at certain level, whereas for the channels is being constructed from the unitary operator. So here the mixing nature of the channel is guaranteed whenever the operator entanglement is greater than or equals to this one, and one can bound how fast the channel can what is the convergence or the rate of mixing. In fact, this result and some of the results is interestingly at least I started working with one of the paper by David and Barbara on the thermalization of a quantum computer. So that actually maybe most of these results were there in mathematics books maybe, but they have worked out in detail of spectrum and everything. And in fact, this bound is also kind of taken it from that and then extended it to. And one of the problem which I am currently working is also to tighten this bound and look for the certain other aspects. Okay, so in this, so these are all the few, and then you go on constructing whether the possibility of construction of those operators and other things, and also look for other, and also we looked for many body quantum systems and other details. So this, when I am studying in the hierarchy, there is the one point which is missing is that there is something called Kolmogorov-Sinai entropy is sitting in between. One more thing, within the quantum domain, weak mixing and strong mixing is equivalent. There is only mixing. There is no weak and strong. That has been also well proved. So there is one more layer which is sitting in some way, which can be characterized in some sense using the Kolmogorov-Sinai entropy, which in some sense requires what is called the partitioning the system and then doing the entropy of calculation of the partitioning of the system, which I am still trying to understand that. But that motivated me to look for what is the entropy which can capture some properties of the system if I wanted to look it at a large. So that is the one motivation. And the second motivation which I was looking is that if I wanted to say something as a quantum thermodynamic second law, so what is the suitable entropy which I call it, which I can call it as a thermodynamic entropy, because the von Neumann entropy is invariant under the unitary dynamics. So these are the two things which motivated me to look into what is called the observational entropy, which is originally, I think I found it on various occasions is this definition. So in fact, the author says that von Neumann himself was given this definition. The definition is very simple. You have a rho, and then pi I are the project set of the projectors, and Vi is the volume of the projector, and you have written Pi log Pi by Vi. So this is the Shannon entropy. One is the Shannon entropy, and this is the averaged Boltzmann entropy, if you think that it is an average Boltzmann entropy. So these two combination is what they are calling observational entropy in the recent literature, but actually you can find it in various places in the literature. So we took that as our starting point and try to look into the certain things. The first one is, what do I mean by coarse graining? So for example, if I have a three-dimensional system, one is having the full projectors like Ket1, Bra1, 1, 2, 3, and then look for 1 plus 2 together versus 3. So when I am looking into this one, I am doing a coarsening of the measurement. So I am not looking into the details. Instead of that, I am looking into the coarsening. So one of the proof is that this is what the refinement, or if the measurement is a coarse grained measurement, what I have said that, so just like you are going into the larger subspaces. So that coarsening, the entropy is always greater than or equals to the refined or the fine-tuned coarse graining. So, and another interesting connection is given by Bujemi, where he used the Pet's recovery map and the retrodiction properties, which one can define the entire entropy using the classical quantum channel and the relative entropy in this form. And what is interesting is that the difference between the observational entropy and von Neumann entropy can be bounded between a relative entropy of this state and this coarse grained state. This state is called the coarse grained state, and this quantity in some sense represents the possibility of how difficult is to retrodict the state. So one is a prediction, another one is retrodiction. How difficult is the retrodiction? So that they also created using the Pet's recovery map, and the other interesting stuff is that even if the state is unitary evolving, one can show that the entropy is always greater than or equals to 0 for unitary dynamics, and also a lot of interesting open quantum systems dynamics and everything is being studied here. So I just showed 2 plots just to say that worked on for few models. One is a kick cutoff, where how that as you change the kicking parameter, the chaoticity increases, so that you can see how the observational entropy is changing. Where essentially what happened in that system is that the slope of the growth of the observational entropy provided some type of witness for the chaos. The other one is Anderson localization, where we want it as a coarse graining. How the observational entropy changes was the coarse graining, where there is a sharp transition between the localization and delocalization at point 2. One can see the clear difference if I have a suitable coarse graining and look into the entire system. So these are the 2 systems which we worked, and these are the whole work in those domain, where we have also extended it to alpha observational entropy and Renyi entropy and what are the properties. So we studied in the 2 systems and some details on that, what is happening there. Sorry. So that is the Kolmogorov-Sinai motivation. Tend to that, which I have not reached anywhere actual Kolmogorov case entropy or other things. So the related one which I was thinking is the complexity, essentially, which capture circuit complexity. If I define the circuit complexity, which actually captures what is the amount of minimum number of 2-qubit gates required to simulate this unitary operator. And actually, sorry, there was a paper mixing, Isert actually I should say that Isert very recently pointed out that you can have an entanglement production in some sense, so and that this entanglement production can lower band the circuit complexity in certain way. So that is what the thing, and that is what we used in for some systems in tight binding model, and to study with also quasi-particle prediction how whether it is good or bad. Actually, the entanglement entropy generation is not the tight bound for the circuit complexity, but it can give a certain bound. But so that's the one thing which we have studied, and I'm still continuing to look into this complexity scenario. Just recently wrote a work on Krylov complexity, which is some kind of complexity measure which captures how well the information is spread across in the basis, in the sense that what is the minimum information spread in the basis, some kind of definition if I vaguely say, and the result is basically it depends upon the initial state, and it doesn't give a good measure of chaos or other things. So that's the one thing which we were able to say or present it. So these are the few work which I have been doing, and the current work and the future work. Yeah, so I'm focusing more on quantum ergodic theory, which I've already told. The speed of convergence, mixing rate, and other dynamical. The speed of convergence. So the bound, I have a dynamics which is specified by the operator. I act on the state, and then how fast it can go to the fixed state. So, and how can we, it is exact calculation may not be possible, but can we bound it, and what is the tight bound? So one of the bound is what David, as far as I know, what David and Barbara has given, but I wanted to make it a little more tight and then find out any physical basis and other understandings, because that bound is basically depends upon the first eigenvalue, mod of first eigenvalue of the dynamics. So, and other one is, yes, these are all the collaborators whom I'm working. So Ranjan, more or less in many of the work, and then case entropy. Shilpak is a mathematician specialized in ergodic theory, which I am still working with him to define it, which is not able to do much success. And recently with Gaurav and Sunil from IIT BHU, have been working on focused on only in the mixing. So the mixing regime of the multipartite system. There are a lot of interesting stuffs because whether how fast the correlations are decaying, at least numerically we can able to predict it, and also there is some indicator using the entangling power. So using that we were able to come up with some multipartite entanglement characterizations and how does it is influencing. So we wanted to study that entire window of the mixing, where slow mixing, fast mixing, is there any physical reasoning with respect to one can see with that one. So that's the one important thing. And also the in between classical ergodic theory, there are many other regimes within the ergodic hierarchy itself. So I'm just looking into those things also. As I told you, complexity, I'm working with Sriram, and yeah. So the one work which I've just started with, I've been working and started, is quantum network information theory with an electrical faculty in our institute, where I'm looking into multiple access channels. So there is the 2 inputs and 2 outputs, as well as many inputs and broadcasting channels. So one input and then many outputs, many inputs and one output, or many inputs and many outputs. So these are the 2 systems, and then how does these 2 systems work, and calculating the capacity regions of these systems is bit tricky even in the classical, and how can we see anything improvement using especially the 2 things. One is entanglement and another one is the non-signaling correlations. If we share with these things, anything improvement which one can see that. And so I did my PhDs in the quantum foundations. So I am working on one thing which is called theory of composition. Normally the tensor product we kind of assumption, it's a postulate within the quantum theory. There are results that can we go beyond the tensor product structure of the quantum theory. There are many such possibilities are there, and then if many such possibilities, what is the best possibility, and is there anything to do with that thing? Is it interesting? So what will be information theoretic possibilities or achievements if one goes beyond the traditional tensor product. So that is the one thing which I am looking. And with the students, I am looking into the multi-party entanglement theory. So especially 4-party and beyond, a characterization of multi-party entanglement, and the computation as well as the measurement, and finding out some kind of bounds which can be computable, lower bounds which can be computable, which could detect the genuineness or other type of the entanglement structure. And that is with one student, Rahul, who is here, and other one is understanding foundations of quantum computational speedup. So we all know that certain things we can see that there is a difference with the classical computation, but where is the origin? So why does some things why does the quantum computational can perform better than the classical computation? So people is not able to pinpoint out. There are many ideas. Entanglement is not sufficient, and one point is contextuality, which people thinking it in measurement based quantum computation. So student Rupendra is working using the category theory and shift theory to understand these things. And so some of these things are my musings. So entanglement theory of dynamical operators itself has some many interesting opening questions, like extending the operator, just like there are multi-party entanglement, the not sufficient understanding on the multi-party dynamical operator entanglement. So that's one interesting features which we are looking into. And the quantum stochastic, so other two things which I'm looking into again with the students and Ranjan is that the quantum resetting or quantum stochastics, and then looking into the renormalization from the quantum information theoretic perspective. So these are all the few works which I am doing. Thank you.
Thank you. general question about the first part of your talk, the framework you were discussing for ergodic and mixing and so forth. Have you given consideration to cases where the Hilbert space dimension is infinite rather than finite?
No.
Okay.
So I'm still fixing into the finite dimensional studies.
Mm-hmm. Okay.
Thank you for the nice talk, sir. I have two questions. One, your initial in the initial part of your talk, you said you showed one circuit diagram. That circuit diagram appears very relevant, very related to what people do with Gaussian boson sampling. So, can these unitary operations be can this study be used in the case of Gaussian boson sampling to show quantum advantage? Like with photons and beam splitters as...
Okay, so at least these systems, whatever we are working in the finite dimensional spin systems, if it has a duality and other things, one can show that there is some quantum computational advantage and other things. So Rosendorf also has put up some work. But with respect to bosonic modes and other things, we don't know how to define those dissolvability, how it emerges, or duality and other things. At least we don't. We thought about that. We didn't get any answer to that.
Okay. And in the second part of your talk, you said that you bounded it by relative entropy. So was that also Rene, like alpha generalized?
Actually, we generalize it to alpha. But when the
bound itself was also generalized?
This one, right?
Yes.
When the Boujemi gave it, it is a regular one, the omega key relative entropy. Okay. In one of our work, yes. So the left hand side is also alpha generalized. That means it's alpha S alpha chi minus this is Rene entropy. Instead of von Neumann entropy, you have a Rene entropy. Then it is greater than or equals to d alpha, means alpha generalization of relative entropy.
So, when you, on the right hand side, what kind of relative Rene entropy, there are Pet's relay and sandwich?
First when we worked on Pet's and also sandwiched. Okay. But in the paper we reported on the Pet's.
Okay. Thank you, sir.
So the question I had might be related to the already asked questions. So are there any sort of classical models, classical maps or something like that which could be analogs of these dual unitary circuits?
I think Arul just wrote.
Okay.
He's asking what is the classical analog of dual unitary maps. He's last year. So he has come up with.
There and then have classical Perron-Frobenius operators or that for the you can do that.
So he worked out that.
Well, not just me actually. There's also a group of Prosen who have written on
related. So you talked about the Kolmogorov-Sinai entropy. So
no, I didn't talk about the Kolmogorov. That was the motivation. That's all. The entropy is very different.
So there's already a definition of that, previously by some authors. There's one Aliki Panis.
Okay. Let me say. First reference to the Kolmogorov entropy is in 1970s by Professor M.D. Srinivasan. That is where I got some of this. In fact, he defined that there itself the mixing and then ergodic of the channels and then mapping, very nice mapping between the classical studies, and then I think he also defined their KS entropy. Okay. But somehow I am not yet satisfied with any of those definitions. There are some technical issues of taking the infimum and then iterating on all the possible partitions. Okay, so those technical problems are there. That's what I mean to say.
So if not for supremizing or optimizing our partitions, then do you have an agreeable entropy
but
just for
in the classical they have this supremum and then for all partitions and other things. So I am still wanted something which is very close. There are two things which I am looking. One is very close to existing classical approach, and then second thing is that it should be computable. I can define it. Okay. So, but in the classical there exist some models where they have actually compute it. I don't know how. Still, I am not able to capture it. The computation part of that one, because it involves the maximization kind of things. Okay.
Any more questions?
So, how different is the observational entropy than just a Husimi entropy over the phase space and doing chaos?
Can you define me? I forgot Husimi entropy.
Well, Husimi entropy is just the overlap of the state with covariant states and making a probability out of it. So that's also a coarse graining.
I don't remember. I mean, I don't know. Okay. I mean, if I can able to put it in, it may be. I don't know. Okay. One can see that because this structure is there in different papers, previously papers also. So it may be a possibility that may be the same, or I don't know, but because I immediately am not able to see it. So.
Yeah, I can probably, I think in that case the VI will be like a H bar, because that's like the, you know, yeah, that's the coherent state volume, so to speak.
Okay,
right?
okay.
Yeah. Well, you have to put that in your H bar, yeah.
Are there any more questions? If not, let's thank Arvinda for a nice talk, and let's thank both the speakers for a very lively and entertaining session. Thank you, everyone. So we have, so we have Atreya, the boss, now announcing.
So now we'll have a kind of extended coffee break that's also meant to double up as a poster session. So the colloquium is at 5 in CLT, and like I said, we encourage you to check our campus and take the short walk there. But in case you prefer a cab ride, please let one of the volunteers know, and we will, arrange it for you. So we do have 2 cabs to take you there. Yeah.
Hey, yeah. Thank you.
So I was wondering that talk about this mixing, right? So interconnection procedure is also a CPTP band.
But if it becomes mixing, you cannot correct it.
Oh,
Yeah. You lose every input. So you need somehow non-mixing
Hello, hello.
Good afternoon, and welcome everyone to this very special colloquium, which is part of the Physics Brahmagupta Colloquium series. It's indeed an absolute honor and pleasure to introduce Professor David DiVincenzo. As the cliche goes, Professor David does not really need any introduction to much of the audience here. But nonetheless, I have been tasked with this job, so I shall do it. So David obtained his PhD with Eugene Melee at the University of Pennsylvania and subsequently worked as a postdoctoral research associate with the Materials Research Center at Cornell University. He was then manager of both the materials physics and subsequently the physics of information group at IBM Watson Center, Yorktown Heights. He then moved to RWTH Aachen with the prestigious Alexander von Humboldt Professorship, and since 2011, he has been serving as the Director of Theoretical Nanoelectronics at the Forschungszentrum Jülich and Professor at the Institute for Quantum Information at Aachen. Of course, David's research works span a wide variety of areas, from physical realizations of quantum computers to quantum algorithms to quantum information theory to quantum tunneling of magnetization, models of decoherence in spin systems, and the list would go on. So if you quickly looked at his Google Scholar page, for example, you would find papers on effective mass theory in graphite compounds, to, of course, the early papers on quantum error correction, fault tolerance, universal set of gates for quantum computing, and, of course, the early architectures for physical realizations of quantum computers. He's a recipient of several awards and honors, including the IBM Innovation Award in 2007 for seminal contributions to quantum computing. And much more recently, in 2023, he's been elected a member of the US National Academy of Sciences. Over the last month, over several personal interactions with David, I have learned that he has academic interest much beyond physics as well, and one of this is, of course, the history of science. So as we are today in the 25th year of the DiVincenzo criteria and the 100th year of quantum mechanics itself, it's indeed extremely fitting and appropriate that David is here to tell us about the early days of quantum computing, about the pioneers of quantum computing. Let's welcome David with a warm thank you.
Thank you, Prabha. Of course, you didn't, is this microphone working? I haven't heard it yet, but
Okay, so again, we pause because, all right, we have to check everything as usual. Okay, a little surgery here. Yeah. Okay. It was my fault maybe, but it was one of these things. Is it on? Is it off? And is it on? And is it off? Okay, but all right. So now, indeed, this will be a story about the early days of quantum computing, and I use the word pioneers. And you might say it was a pioneering development or pioneering movement, but I will actually focus on the people pioneers. The actual personalities who shaped this field. We're in this 100 years of quantum mechanics, and this story has a very definite beginning time and ending time. It starts about 50 years ago, and it ends about 30 years ago. And I came along at sort of the tail end of this pioneering period, so I can tell at least some stories about how it developed, how the last few stages of it developed. And it's been very interesting to go back and see, okay, what were the actual steps in this development, because the initial work was kind of in the wilderness, like pioneers tend to be, that they were saying things that other scientists weren't actually that interested in for quite a long time. And so it took quite some strength of spirit for some of these to actually proceed and work on these problems when they were not very popular. So here's, and you'll see stories about many of the people who are on this opening slide. And since this is a story about 20th century physics, it's a story about men, sorry. I hope that if we can tell a story about this for the 21st century, it will be much more balanced. But okay, sorry, these pioneers happen to be people with lots of hair coming out of their faces in many cases. Okay, so a premise, let's see, is this going to work? Yeah, okay. So the people who contributed in the early days were coming from many different directions. And this states a kind of premise that if you think about science in the 20th century, here's a list of ones that you could argue are among the premier sciences of the 20th century. Not all of them, naturally, health or something like that, genetics. But there is, of course, quantum mechanics, but there's also the principles of computing and the ideas of how you compute with discrete objects, discrete variables in digital computing, and also digital communications. And those three subjects brought in thinkers who were really thinking outside the boxes of all these three subjects, even combined. And so I'll be telling the story of a few of these thinkers and how by the end of the century, that is the 20th century, we really had something new, and which then kind of exploded on the scene, I would say, about 25, 30 years ago. Now, a story like this cannot avoid talking about Peter Shor. So, but he will not be one of my pioneers. He's sort of like the next settler. After the real pioneers had hacked their way through the jungle, he was able to stride confidently and do something really revolutionary with the big path that had been carved for him by the earlier pioneers. Now, who is Peter Shor? I know that this is a sort of public talk, but I think I don't have very much of the public. But just as a show of hands, how many of you think you know what Peter Shor's role in this story was? And okay, not everyone is raising his hand, but very, very many. Okay, so you're all, not all of you, sorry, but many of you are aware that he, in 1994, came up with a new algorithm for doing a very important problem in arithmetic, and I like to schematize it this way. So, and it's the problem of finding prime factors. And it was immediately recognized this has enormous technological significance because of the following story, that here's actually an integer. This is a real example. This is an integer with 129 digits. It's a famous integer. It goes along with the names Rivest, Shamir, and Edelman, because it's a number that was put forth to illustrate the cryptographic abilities of the act of being able to factor numbers. Now, this indeed does have two prime factors, and here they're written out, but I bet you can't tell that, and even if you, if you type this into your laptop, if anybody has them open, and say factor, it won't be such an easy job, even for your current day computer. And, well, maybe some good ones really can do that now. I kind of doubt it. But if you make this number a bit longer, that is, you make it 1,000 bits, 1,000 digits in this case, your computer will really get stuck. That it's an extremely challenging problem. Although there is an answer, and the person who created this number can know it's the answer because they could have taken two prime numbers. It's easy to verify, quote, easy, to verify that these two numbers, which are both about 60 so digits long, are in fact prime numbers. You multiply them together, you get that. That you could do on your apparatus. I think even on your phone you could do that if you had the patience. Well, you get your camera, you take a picture of that number, you take a picture of that number, you say multiply, it'll do it in no time. So arithmetic has this famous sort of one-way character, and it's this one-wayness that gives a basis for much of the cryptography we use today. And there was always a niggling worry that this wasn't necessarily so safe, that maybe there'd be ways, some new arithmetic techniques that nobody had come up with that would indeed allow a quick calculation of these factors. But after decades of work, that has not come to pass, and all the algorithms for doing that scale exponentially with the number of digits. However, what Shor showed is that given the rules, which had just barely been established as reasonable rules for this new style of computation, the so-called quantum computation, that he was able to invoke those rules and show that this same problem is solved very fast. And in fact, it's so fast that it's no different backwards and forwards in the quantum world. So with the tools of quantum mechanics, this becomes an easy problem, and that has very big problematic implications for cryptography whenever we can build quantum computers. And we're not there yet, of course, so this is not a current day worry, but it seems to be coming. Let us say. We heard in our meeting earlier today about roadmaps of which company? Well, I do know that Q-Era, who was the speaker this morning who was telling us about neutral atoms, that machines with 10,000 bits are around the corner, they say, and more to come. And if those numbers get to be millions, then indeed this may actually be feasible. So that put quantum computing on the map for the broader community, but as I said, it was preceded by several decades of gestational thinking, and that will be mainly what I'll be talking about in this lecture. Whoops. Now, to say, sorry, my thing's going weird here. I wanted to get to, why is this being very annoying? Okay, we'll do it this way. This is just to illustrate what happened to the field when, this is a sort of before Shor and after Shor. So this was the international conference in 1993 on quantum computing. And that's pretty much all the people in the whole world. This was a meeting in Italy. It's actually pretty much everybody who cared or was, thought it was worth coming together and talking about quantum computers in the year 1993, the year after Shor's algorithm came about. And then within a few years, the similar conferences became ones like this, hundreds of participants and all over the world and every year. So it was a sign that, things had changed. It became pretty soon a really mainstream topic and has been busy taking over whole big swaths of physics in the meantime, and not only physics. Okay, but again, we back up, and a few of my pioneers are in this picture, but we'll get to talk about them as I go. Now, I'll indeed feature, if you were looking at my pictures at the beginning, I had three rather larger pictures on the left-hand side, and those are indeed the people that I will talk about as the pioneers. Now, Now, the first one's the kind of obvious one, I will say. I mean, obvious for physicists. And indeed, we always say, oh, yes, and Richard Feynman, created or thought up or something or other the quantum computer. And I want to examine that and tell you what I would say, what credit we should really give to Feynman, which is quite a lot, actually. But his work by itself did not get us to this tipping point. Okay, but of course he's a famous physicist, Nobel Prize for quantum electrodynamics, and a very well-known thinker and popularizer, but also innovator in many areas of physics. So, okay, again, I'm having trouble with this, so let's go back. Now, this actually is further back even than I said I would start. So, in 66 years ago, he gave a lecture at the American Physical Society, which already gave sort of a few hints. It certainly gave hints that in his own mind he was starting to question things about the intersection of two of these fields, of computing and of quantum mechanics. And he says what his line of thinking is that he's not only talking about computers, but he's talking about making new kinds of circuits that would be based not on the laws of classical physics or classical mechanics, but on the laws of quantum mechanics. And he says a few phrases here, but again, these are just texts from a speech. He talks, well, there are going to be quantized energy levels, there's some kind of quantized spins. And he says, I believe somewhere in here, if you fiddle with, I believe this is the quote where he says, think about 7 atoms. But he says, make a circuit out of 7 atoms, he says. Now, and by circuit, he means like an electric circuit, a wire that would turn on and off a switch. So circuit means something, or 7 atoms means something ridiculously small for an electric circuit. In this same lecture, he made a challenge. He said, I'm also talking about electric motors, and he said, I'm sure you can't make an electric motor that's 5 millimeters across. Actually, he turned out to be wrong about that, and somebody presented him a few weeks later with such an electric motor. He had actually unwisely said he would pay some money for it, so he actually had to pay up for this electric motor. So miniaturization was a known thing, but he says there's plenty of room at the bottom. That is, there's plenty of there are many orders of magnitude still between the 5 millimeter device, operating device, and the atomic scale. Now, in some sense, I would say he led us a little bit on the wrong track with this kind of thinking, because these principles or the thoughts here were still in mind when we started thinking about quantum computers more seriously. And one line of thought was, yes, indeed, we had to go right down to the atomic level. We had to make our storage devices 1 atom in size. And that principle is, sometimes, or we've seen now that that's true, that you can make quantum computers out of 1 atom at a time. But that's actually not necessary. That is, we know of other situations where you have a device with millions of atoms, and yet showing very decided quantum mechanical behavior. And that's good news, actually, for quantum computers, that we don't have to go to the ultimate miniaturization to have quantum effects. Okay, but this was still a good guidepost, and this lecture is considered not only a sort of a founding lecture for quantum computing, it's a founding lecture for all of nanosciences, really, because this was at a time where none of those thoughts existed yet, and so this was a very pioneering thought in that respect. Now, now going forward with Feynman, you see nothing further, really, in Feynman's record of work. Until you get to this. So, of course, Feynman did many things. He actually was interested in new forms of computing, and he spent time at companies that were exploring new architectures for computers. But the first time he then really says something more concrete about quantum computers is in this, written up as a paper, 1982. And this is indeed often cited as the founding paper of quantum computing. And indeed, in the text of this paper, he says the phrase quantum computer. And that is indeed, well, with one exception, which I'll come to in a moment, come to in a few minutes, that was indeed the first time that people had seen that phrase, that it had been stated as a concept. Now, to say that this is a paper and also to imagine that it has any sort of rigorous results in it would be incorrect, because yes, it's a paper, but in fact it's again a transcript of a speech that he gave at a conference. So it, was not indeed announcing anything rigorous. It was announcing again a set of fairly qualitative ideas. So let me, and now, okay, this is far too much text, but just to see that, yes, section 4 is about quantum computers, but also about quantum simulators. So he's thinking about both at the same time here. And this is very colloquial. He's sort of thinking out loud. He says, well, can you do it with a quantum computer? Is a question. And he doesn't finally give much of an answer. He ends up talking about whether indistinguishable particles, Bose particles or Fermi particles might be somehow interesting for this. But there's not really much more here than just a statement that, well, this is a good thing for us to be thinking about. And if this paper is used in any really concrete way, it is indeed used for the idea of simulation. That is, you make a machine that will simulate in a quantum mechanical fashion other systems. And I think it's reasonable to give it credit for that. But it didn't really lay out any useful principles at this moment or at this point for the quantum computer as we now discuss it. Okay, now Feynman had one more paper. This was near the end of his life, as a matter of fact. He died, I believe, in 1989. So here's a paper from 1986. It's again mostly from a speech that he gave, again about quantum mechanical computers, but it was to an audience of quantum optics people. And actually, he did put more energy into this paper, and there is an actual sort of model of a quantum computer in this paper. However, it didn't occur to him that you should use quantum superpositions for this quantum computer. So that's not, well, it kind of missed a big part of the story. So he was mainly concentrating on, could you mimic step by step the process of a digital computer in a purely quantum mechanical evolution? And but for that problem, yes, he did write down some principles. And I would say that the math that he wrote down in this paper, this is one of the few equations in that paper, that they, well, did actually stimulate a very specific, concrete line of investigation in the following years, quite a few years later, 10, 15, 20 years later, on new ideas of complexity in quantum computing. The extensions of the notions of NP hardness, for example, to quantum settings could use this as a basis. This could not, well, let's see, I make a few remarks here. This paper is not particularly close to the speculations that he gave in the 1981-82 paper, the one from 3 years or 4 years earlier. You could say that this Hamiltonian is actually a prescription for a physical system to make a quantum computer, but it's not a very realistic one. It's not one that you could connect really to any actual optics system. We did over the years think fairly hard about this Hamiltonian and think, could it be kind of reduced to a more realistic Hamiltonian? And that's been, again, a kind of profitable enterprise. This, as written, or as a little bit further developed by, for example, Kitaev, led to, I guess, initially like a 6-body Hamiltonian. If you disentangled, I mean, he didn't talk in terms of what we call qubits at all, he meaning Feynman, but if you disentangled it and wrote it as a regular, interacting spin Hamiltonian, it would require 6 spin interactions. So not very realistic, but we were able to see how to reduce it ultimately to 2 spin interactions. But it hasn't taken fire. I mean, there are many reasons why it actually was not the sort of founding mathematical principles of the quantum computer as we now discuss it. Okay, and that's kind of it for Feynman. That is, as I said, he was already quite ill, actually, and he lived only a few more years. So he didn't get to see the further developments of this. I never myself saw him or met him. But of course, he was, reported to be an extremely dynamic person, and also a little bit arrogant, you might say, but actually with a lot to be arrogant about, you might say. Okay, but let me move on. So there's another thread of this history, which not so closely connected, actually, to the Feynman story. And you might say not even so closely connected to anything. It's sort of almost one of these things where the geniuses, it's like the Kerala School of Astronomy almost. There's somebody, scribbling in the privacy of their home, and then maybe eventually sort of letting the rest of the world know about it. And this was almost like the story of this person. So this is Stephen Wiesner. Now, Wiesner I did know, and I knew him more in his older age. But I've seen there's now a complete, there didn't used to be, but now there's a fairly complete Wikipedia page about him, so you can see what he looked like in earlier times. And yes, indeed, he was kind of a wild guy. But let me take you back to what he was doing. So his foundational contribution to this subject came about, was written down in a manuscript, but an unpublished manuscript that apparently was written in about the year 1970. It did eventually, after many years, get published, after 13 years. So my understanding, I mean, those of you, students and faculty who try to write papers and submit to journals will sort of know the experience. I mean, apparently this was submitted, it was rejected. And he didn't care, so he just put it on a shelf. And it was only at the urging of others, which I'll tell in a moment, that it was actually even published ever. Okay, now conjugate coding. What is conjugate coding? It was what we now consider kind of simple insight that superpositions of two-level systems have real information capabilities, capability for manipulating information in ways that are just not available in classical systems. So to give you concretely what he did, so he has several, quote, examples in his paper. And example 2 is quantum money. And actually not in the paper, it was certainly not in this beautiful form, but in sort of subsequent articles. There was, I believe, a Scientific American article that ultimately explained this. But, to explain what this is, I was about to get out a 100-rupee bill and hold it up, because that's what I'm trying to show a picture of here, but that would endanger the whole electrical setup of this lecture, so I'm not going to do that. But so this explains the concept that, what's an attribute of a piece of currency, a piece of paper money. It should have, it has a unique serial number, and it shouldn't be copyable. It shouldn't be that a counterfeiter can just arbitrarily make many, many copies of the same extremely valuable 10-rupee note, or, whatever it is, 100 whatevers. This is a completely imaginary currency. But it's imaginary because the concept of Wiesner is that it should have little containers. I don't actually remember. I think his main language was actually in terms of spins embedded into a material. So it and yet the story is often told in terms of photons, because when he told it to others, they said, well, we like the idea of this for photons better. But that was not his favored way of describing it in his manuscript. But the way I can describe it in my language is you make a tiny little box to hold a photon. So the photon is sitting in there, there are mirrors, it's bouncing back and forth, and it has, that single photon has an attribute which is its polarization vector. And he said, we will use the regular vertical and horizontal polarizations. That would record a regular bit, 0, 1. But let's also use the diagonal polarizations, which are also preparable. But we know, or he stated what then was a sort of novel observation, that if this banknote were prepared, there would be no way that a counterfeiter could read out what these were without causing disturbance because of just the principles of measurement of quantum mechanics. And I think I have a picture that sort of, let's see, is it the next picture? Yes. I mean, it's just, this is just to remind you, most of you are physicists and know this principle, but you can set up a simple crystal, this is a double refraction crystal, a birefringent crystal, and it provides a method of measuring reliably whether photons are horizontally polarized, because that corresponds to the beam that goes straight through a calcite crystal, versus vertically polarized, which undergoes anomalous diffraction and ends up in a different beam, and so can be recorded by just seeing if the photon comes out high or low. But if you send in horizontal, 45-degree polarized photons, it's not so that they come out halfway in between. They will split. That is, half the time they'll come out and look like vertical photons, and half the time they will come out and look like horizontal photons. So that's just a reminder of basic facts about measurement theory, about the postulate of measuring single photons. And indeed, there is no physical apparatus that will reliably distinguish these three cases from one another. And so the basis of copying, which would be to first read out and see what was embedded there, could not be done by a counterfeiter. But it could be done by the bank, actually, because the bank will have kept a record of how it had prepared each of these photons. And when according to its record, if this was a diagonal photon, then the method would be simply to rotate the calcite crystal, and that would turn the indefiniteness of the diagonal polarization measurement into a definite measurement. That yes, indeed, it was definitely diagonal in a particular direction, diagonal, plus 45 or minus 45. So that was the principle that he expressed in this paper, and we can explain it in a few minutes now, but 50 years ago, nobody had thought about this implication, about this intersection between basic needs in the information world and quantum mechanics. So now this is related to what's called unclonability. It's related just to the fact that you can't take one of these photons and make a new copy of it by any physical process. And I'll come to that in a moment. I mean, he realized that, but then quite a few years later also was elevated to a physical principle, but we associate that with some other workers. Okay, now, so this and a few other remarkable ideas were in this manuscript, which just sat, on a shelf. But it was known to somebody, and the important, person who, made it possible that this didn't just simply get lost to history was, in fact, Charles Bennett. So Charles Bennett and Steve Wiesner were classmates in college. So, and the story is that Wiesner had these ideas and he communicated it to his classmate. And there are records, let's see, I think I have it coming up, sorry. There are pieces of paper like this. It's not on palm leaves, but it's almost sort of comparable to that. And these are actually in Charles Bennett's handwriting. And they're, sort of records of some discussions that they've had in the year 1970, and headed by quantum information theory. And historians who are more patient than I could read through and try to sort out what's going on here. But you see, indeed, stories about, well, there's Einstein, Podolsky, Rosen paradoxes, and I think down here you get to various sort of measurement scenarios. There are several pages like this. So it sheds light on where did this manuscript, which I believe was written the year after, came from. Now, let me just go back. Sorry, I skipped over a bunch of things because I wanted to jump to that. So just to dig into, well, who is this person, Stephen Wiesner? He was, in fact, a physics student at Brandeis University. Fine. Did he have any reason to have a particular insight into quantum mechanics? And well, here I stick my neck out a little bit because I will now state some things that are purely, you might say, speculative. That okay, why did he know a lot about new ideas in quantum mechanics? I think not because he because of his professors at Brandeis. I'm sure they were very nice professors, but it may have been because of this person. Okay, so now, okay, Stephen Wiesner is indeed, or was pretty much an unknown. This is Jerome Wiesner. This is his father. Now, I think this audience, I think knowledge of who this person is has faded over time, and especially, maybe here in India. Do any of you, just as a show of hands, do any of you know who Jerome Wiesner was? No. Okay, indeed. So I'll show you that he was indeed a leading scholar in the United States. He was, however, he was from engineering, but it was said indeed that he had quite a lot of knowledge of quantum mechanics. It's also said that he and Stephen were completely estranged. So you have to remember 1960s and lots of rebellion and things like that. And Jerome Wiesner was very much a piece of the establishment. He was the president of MIT for a long time. He was science advisor to President Kennedy. So here's a picture of him at a convocation with Frederick Seitz, I believe, with another well-known physicist. And so he was, in the White House and, having things to influence, to exercise. What I read is that he gave as a very definite piece of advice to President Kennedy that it was stupid to fly human beings to the moon. Okay, well, we know how that worked out. But it was probably pretty sound scientific advice, but probably not good political advice. So he was a powerhouse in United States science and, a considerable scholar himself, but a very influential public figure. Okay, now, does that have anything to do with how Wiesner came out? I'm sure it did, but it made him ultra-rebellious, for sure. He rarely, throughout his entire life after he left graduate school without a degree, and he rarely had a regular job throughout his entire life. He died recently. He lived rather a hermit's life in the desert in Israel for most of his life. Now, but nevertheless, I myself would put his insight that you should, that superpositions of vertical and horizontal produce something that really is important informationally, put him right up in the pantheon of our real greats of the 100-year ago quantum mechanics. I especially think of him as a successor to Schrödinger, because Schrödinger in the 1930s was in fact exploring principles that we recognize today as ones of quantum information science, principles of entanglement basically, but also of quantum steering, and actually a number of fairly technical works that were kind of rediscovered over time. So, well, there's my statement that I think he's actually, Wiesner's the pinnacle, in my view, of the real intellectual contributors to this. And, Bennett recognized that, and he saw that this, the basic concepts that were in Wiesner's work definitely had value, and he then subsequently turned them into a quantum key distribution concept in 1984. The two of them continued to work together some, and Bennett and Wiesner have a well-known paper on what's called superdense coding. But again, all based on the principles of using these, quote, diagonal states, these superposition states. I witnessed myself their interaction, which was not so smooth, actually, that Wiesner always had, a kind of chip on his shoulder and was not the easy person to get along with, but Bennett was committed to making his work known and always gave very generous credit to to Wiesner for the ideas that he further developed, that Bennett further developed. I would say that up to and including teleportation, which is a kind of a dual of the concept of superdense coding. Now, okay, so now to progress further with this story, we don't forget Wiesner, but there is finally a third actor in my pantheon, a third god, you might say, in my pantheon. And to get to that, I remarked that there was an important meeting. So here's a rather largish group of people. I think, sorry, all men, yeah. No, sorry, okay, handful of women, but it's 20th century, remember. So this was a meeting that was convened by various people from IBM and MIT on the subject of physics and computation. So again, a kind of exploratory meeting, you know, not really a very clear agenda, but with, you know, definitely a bringing together of important minds. So Feynman is here in this crowd. He's standing next to a well-known computer architect, actually, at IBM, John Koch, who was the inventor of what's called RISC, the reduced instruction set computing technique. So Feynman really liked computer architects and liked to hang around with them. Now, an important fact about, okay, his presence here is the speech that I was referring to, you know, the 1982 paper. The speech is the speech to this group. I can pick out, you know, just to name drop a bit. So there's Freeman Dyson in this picture. There's Daniel Greenberger, Horn, and Zeilinger. Over here with Peter Gotch. I mean, I could name many more which would not be, say, household names. My IBM colleague Rolf Landauer is in this picture. And then behind him is Tom Toffoli of the Toffoli Gate, with Ed Fredkin. Okay, there are various others. There are even some that I would put in the 100% crackpot category among this group. But and basically, including the guy sitting right next to Landauer, actually a real contrast in styles. I did want to say, before I forget, that there are people that would, in a sense, should be named as people that, while not maybe directly contributing to the key ideas of quantum computers, are worth mentioning. And one of them is Landauer himself, and who, throughout his time at IBM, was very deep in the exploration of looking at physics from an information point of view, and thermodynamics from an information point of view. And then there are quite powerful thinkers in the Soviet Union who were on their own path and were not really so known in the West. But Yuri Manin, who was a computer scientist who then was a long time in Germany, just died a year or so ago, wrote a book in 1980 called Computing and Uncomputable. Here's the text of it. I can offer you. I don't know if it was ever translated. It was, a few pages of it were translated for me, so I knew what was in here. And there are a few sentences that say, give a perfect but very brief statement about what a quantum computer is. You know, that it's composed of Hilbert spaces tensored together in our current language, and that it would therefore have a very big state space available to it, but that's about it. And, but it was well known to, for example, Alexei Kitaev, a well-known contributor to quantum computing when I was first doing these things. And then one shouldn't forget, but this is more in the direction of communication theory extended to quantum mechanics, to the work of Holevo, which also started quite long ago. Okay, now these were maybe partially or somewhat known in this group, and I think they had interesting discussions, and then they all went home and mostly did other things. There was another much smaller meeting the same year in Germany, Bad Windsheim, which was, I don't have it written here, but it's indeed about kind of cosmology and quantum measurement and all sorts of, you know, again, a kind of funny collection of things. I think that there was at least some tenuous intellectual connection between these two meetings, because here you see a small group of people, definitely not the whole conference, but here's John Wheeler. Now, recall John Wheeler was Richard Feynman's PhD advisor and was always interested in the interplay of information and physics. And this was his current groupies of that time. They're all well-known physicists, all physicists. Kip Thorne. He did not continue very much in quantum information things, but did other notable things. Well-known cosmologist Bill Unruh, and then there's also Wojciech Zurek and Bill Wooters, and they were all together with Wheeler in those years at the University of Texas. And what's notable in this timeline is that the year after, 1982, Wooters and Zurek published a paper in Nature, which is called the No Cloning paper. Now, as I said, I would say that Wiesner kind of already knew it. It was sort of implicit in Wiesner's work. However, they stated it in nice, compact mathematical form, and we give them credit for having enunciated this as a key principle of information processing with quantum states. Now, there's another person who, again, don't appear in any of these pictures, however, who was, in fact, in these years, a visitor to this group at the University of Texas, and definitely absorbed a few of the ideas that were current. And that's David Deutsch from Oxford. Another strange character, actually, again, not more of an author than actually someone who does real work, you might say, but a kind of a perennial hanger-on at Oxford for many years after he finished his visiting time at Texas. But he apparently was, sitting and thinking carefully and had knew about certainly the work of Bennett, and therefore the work of Wiesner, and knew about the questions that Wheeler had been asking. And so he, I would say should be given credit for the qubit, although the word itself was not coined for another decade or so, as a matter of fact. But he was the one who said, let's take the extension of information processing principles seriously into the quantum domain. And he took the step that Feynman missed, actually, in his first attempt at writing down a quantum computer. This would also apply to another worker named Benioff, who was also at the 1981 conference, that he realized that superposition would be would provide a real extension to the logic gate principles of digital computation. So he said, well, there are zeros and ones, and those are the basis of the bit, but let's allow any superposition as an information carrier in a computer. And now by extension, or I'll state in a moment what he did, and by extension, entangled states. So this doesn't sound like any big step, but it hadn't been taken by anybody. And he immediately, was working on this and realized very soon that it had actual algorithmic implications. Now, again, I think for this audience, I don't have to say these old ideas, but just to say that he had two papers, quite at leisure in the sense that, there are definite developments from one to the next, but since the field was sort of blank, it wasn't like there was any particular competition. If you made a bibliography of important papers in these years in quantum computers, there would be these, and there's one paper by Asher Perez, and that's about it. So it was a very empty field, so he could afford to think for many years about it. The first paper has more concepts that one should extend the idea of the Turing machine, and not a bad thing to do, but also not very practical. I mean, we don't build computers based on Turing machine principles. And then in the second paper, he got to the idea that you should really think about logic gates, and that now becomes a more concrete thing, and indeed did give a big impetus to the field within just a few years. So, he introduced this idea that you should simply take regular logic gates, like the one I've stated here, making sure that they're reversible, that is, that the the logic could run forward or backward. In other words, the outcome of the truth table would map one-to-one to the input. So that's, for example, the addition of bits mod 2, as long as you save a copy of the first bit. And that's what we now call the C0. That was not ever a particularly popular gate. It is not a universal gate for Boolean logic. So you don't actually focus on it that much if you're thinking of Boolean logic synthesis. But it is a reversible gate. And he just stated what to us is now the obvious principle, that if you present this gate with superpositions, that the rule is that it acts on each term of the superposition the way the logic, the way the truth table says that it should. And so that's, whoops, I see one, buggy, okay, that should have been, of course, the modular plus sign. But this led, of course, to immediately the recognition that entangled states would be something that would emerge immediately if you started running computations according to these rules. And now, in this paper in 1989, he immediately announced an algorithm that would take advantage of this and give a speed up, give actually an advantage over a conventional computation. It was not a very profound speed up. It was something where you'd have to run the regular computer twice, but you would get away with only running this once. But that set the principle that this new rules, you might say, the new software, I'd say he basically said quantum mechanics is a set of new software rules for running gates, and that software was, in his mind, immediately more powerful than Boolean logic software. What he had done in the 89 paper is what we call an oracle speedup. But there wasn't much more. I would say at that point the road had been hacked through the jungle, that all the hard work had been done. A sign of that is that within a few years, I don't say it here, but let's see, I think I have it here, yes, that the timeline then speeds up very fast. That is, so the Deutsch algorithm in 89 was followed up by this multi-qubit version. I just mentioned these names. I think a large number of you know these, but just to state that these are successively somewhat more powerful algorithms for using a quantum computer. The Deutsch-Jose algorithm, so a student at Oxford was working with Deutsch, and they came up with this extension. Then a group at Berkeley took this up. But see, this was a sign that this was becoming professionalized, because Umesh Vazirani is a real mainstream, prominent theoretical computer scientist, and the fact that he took this up means, it was getting clear that this was something well posed and interesting and worthy of thinking. And so once you've got those conditions and you have a powerful mind like Umesh Vazirani, then for sure good things will happen. And they produced an interesting algorithm. And then a follow-up actually from the University of Montreal, extending these principles. None of these first four, earth-shattering. That is, they were solving somewhat contrived problems. So the world could still sit back and say, well, okay, show me. But then, in fact, all of these provided principles that Shor could use for the solution of the factoring problem. So it's, of course, not to minimize the great insights that were in this, but it was certainly of a different character. It didn't require, going against every possible trend of your times. It required, taking up principles that now had been newly formulated, but in a clear way, and really marching with them and finding new things to do with them. Now, the sociology was also changing in the sense that these first few algorithms was enough to convince a set of people, but not very many, as you see, to come together for this first international meeting in quantum computing. And it would indeed have the players that I've been mentioning. Here's David Deutsch. Here's Umesh Vazirani, who had just that year or the previous year come up with a very interesting quantum algorithm. Charles Bennett here with his partner in the quantum cryptography, Gilles Brassard. There's Zurich and, where is he, Wouters of the no cloning theorem, and a collection of other people. Well, there's Roger Penrose, for example. There's, well, let's see, should I mention any more? There's some quantum, cosmologists in this crowd. There's Arthur Eckert, who was important in that he was, in a sense, a kind of student, in this very loose sense, of David Deutsch, and definitely pushed forward some of the other ideas. But was, this whole group was really primed to jump on shore. That is, they weren't all, none of them were smart enough to do it. That took someone else thinking quietly off to the side for a few months. But they were all sure ready to jump on it. And for example, Eckert is well known for having immediately digested it and understanding the full implications of it, writing out a tutorial on it, which was then published, he and Joza, in Reviews of Modern Physics within a year or so that the whole world could digest it, but also to proselytize to the experimental community. And that's kind of what happened next. So let's, well, I have here a photo to say that, you know, the other thing that happened from a sort of fundamental point of view in that, you know, those years, 1993, is the concept of teleportation. And in fact, all of the authors of the quantum teleportation article are present in this photo in Turin. Here's a somewhat later picture of the 6 of them at a sort of commemorative meeting. But let me remark on what happened then in the subsequent year. So there was an agreement that, okay, we should get together again next year in Turin. And this is the gathering in Turin a year later. A little bit bigger, not very much bigger, but with a new cast of characters. Here's Peter Shor, actually, and this was the first time that most people heard in person, you know, outside Bell Labs in a few small circles, what his algorithm was about. Here's Eckert again, but there are some very important new people here who are from experimental physics. So there's Zoller and Sirac are in this picture, and they had come to this meeting to announce their ideas about ion traps. There's several quantum optics people. There's John Rarity and Hideo Mobuchi, so the people who are actually sending photons through fibers, and we're trying to absorb the new ideas. This is Nicolas Gizin, who was important in bringing quantum crypto to the lab. And I myself, indeed, was now finally grown up enough to play with the big boys here, and girls. This is Chiara Machiavello, who's been long a professor at Pavia. But these are all well known to me. There's Charles Bennett, of course, as well. And of course, the rest was history. That is, here's the next year. Many, many more people, you know, very growing group of people. And now you see Barbara Terhal for the first time in this group as well. But as I mentioned at the beginning, this started to grow. I don't have the photos again, but, you know, 10 people became 20 people, became 40 people. And, you know, for a few years, the number of people who were interested were growing according to a strict exponential. I think at this point we finally plateaued, but at the number which, you know, is in the thousands or tens of thousands or something of scientists. And, you know, work continues. Now, of course, did we think that the first ideas of Sirac and Zoller, or for that matter of Günther Mahler and myself about semiconductors would, you know, within a short order produce a quantum computer? No. We actually knew we were, there was a huge disconnect between what we could suggest for work in the laboratory and what could actually be done. And so we've seen now decades of development in that direction. You know, the maturing of ideas needed many generations of new maturing of new concepts of how to work in the laboratory for a quantum computer, for us to even get close to a quantum computer. And I think at this point, we're, well, closer, definitely closer, but definitely not there either. But the world has certainly been changed because of the ideas of these small number of people, and really beginning with just a few scribbling on papers that could have been lost in time, but, well, we could ask what would have happened anyway. I mean, there's, it's said that okay, Shor, of course, discovered the factoring algorithm, but it said that word reached Moscow that some new technique had been discovered. I mean, that there was some algorithm for factoring, and that's about all that had reached Moscow, apparently, but that was enough for Alexei Kitaev to come up with the factoring algorithm. So it was not, it was in the air. It was certainly, it was going to be discovered by somebody pretty soon based on what had been put together. But so that's comes back to my pantheon, and as I say, I give credit to these yes men, crazy men, wild men, not perfect men, but men with a lot of foresight, the ability to hack their way through the jungle with a lot of help, not only from these two people, but from now a whole army of individuals. So, thanks. That's my lecture. I think there will be microphones. Yeah.
I have two questions. The one is, what was the motivation for David Deutsch? In the sense that I heard that there is some relation of his interest in the many-world interpretation that led to quantum computing.
Okay, so yes, indeed true, and that's maybe the not so savory aspect of this, that he was convinced that the main reason to articulate the ideas of a quantum computer would be to make clear to everybody every thinker that the many worlds view is true. He was actually quite doctrinaire about this in his papers. So, not so sort of politically appealing. A little bit like, I don't know if you know the name Rosenfeld. There's Bohr and Rosenfeld. That in almost every paper that Rosenfeld wrote, he had a section about Marxist-Leninist doctrine and the inevitability of the triumph of Marxist-Leninism. Apparently, Bohr forbade him from putting those paragraphs into papers that they wrote together. But all other papers that he wrote had these philosophical views expressed along with his physics. So, you may think of Deutsch as a little bit like that.
Okay, so the other one, sorry, about Asher Perez.
Yes.
Asher Perez. So, when you comparing with, so everywhere.
Just to go back.
Yeah, exactly. So his background is also kind of varying. Comes from the gravitation, and then it work in chaos, and then comes to foundations and these things. So
yeah. Well, I mean, he was a brilliant and amazing scientist. I had the privilege to work with him, and Barbara had time working with him as well. And indeed, he was very eclectic, and was willing to think very, very far outside the box, and was interested in very foundational questions about quantum mechanics. We know the Mermin-Perez squares, which came from him. Well, what more to say? I think he didn't have the big idea for how you would make a quantum computer. It wasn't given to him. Although he had an extremely interesting commentary paper on Feynman's ideas right away. So he was one who was taking Feynman very seriously back in 1985, and was certainly totally receptive to the developments as they unfolded. Unfortunately died rather early.
Thank you very much, David. Fascinating. I also hear from my Polish colleagues about Roman Ingarden and his papers on quantum information back in 1976, Foundations of Quantum Information. So is that something on the lines of Holevo, or?
I guess I would indeed put it in that category. One thing that's absolutely the fact is that I don't know that work so well. I don't think that it really influenced this stream of development that strongly.
It is actually titled Quantum Information Theory back in 1976. So maybe.
Yes, I think people have looked at it, and it's not quantum information theory as we mean it today, I think. Okay, but well, maybe people have to go back and see if I'm really wrong, but that was again an example of, you know, something that was written down and should have had a lot of influence but didn't.
Okay.
Okay, I have no further good comment about that.
Thanks.
Since you don't want to talk about yourself, but you should tell us about how you came up with the idea of what constitutes a quantum computer. You should tell us about that.
Well, as you see, this is very post, right? I mean, all the hard work had been done, and I just come in and steal the show. But actually, what I would say is that I give a lot of credit to Sirac and Zoller. So those two people who were at this meeting in 1994 were experts in atomic physics and were experts in what you could do in ion traps. And they immediately thought through and said, okay, now what are the steps that, you know, could be taken to turn our current knowledge in ion traps into a quantum computer? And they came up with a very nice set of prescriptions, you know, clear that what experiments would need to be done. And for me, that was also quite inspiring, but it also, I was certain that it was transferable to other areas of experimental physics. So I took it back to another level of abstraction, you might say, and said, well, what, you know, now as a sort of meta prescription, that is not a prescription for ions or for superconductors or whatever, but the prescription that will work for whatever platform you want to think about. The way I wrote them, it was also a little bit of a critique of the current trends in NMR. NMR people also were taking up the ideas of quantum computers, and I felt in those first few years, this is like in the later 90s, they were taking them up in the wrong way, according to in my humble opinion, and I somewhat was making criteria to say, sorry, you really haven't got the whole story straight in the way you're you know, conceiving of NMR as a route to a quantum computer. So, okay, that it also motivated me to think carefully about electrons in semiconductors and think about how they would support quantum computing. But it was sort of an application of these more general principles.
Okay, so I have this question. So this Bennett and Prasad's discovery of this quantum key distribution, why did they publish their paper in this conference in Bangalore, India?
Okay, I believe what I've heard, I don't remember the full story, but they actually had quite some trouble publishing it. That it was actually rejected by some journals, and that the expedient of going to a conference and presenting it, and then it became a conference paper, was the way that it got published. So I think it was not their preferred route of publication. You know, this was not an era where everybody wanted to publish in Nature, but I don't know where they probably wanted to publish it in a, you know, really polished, you know, computer science journal, but this was not to be. So I don't know much more about the story than that.
So maybe this is maybe not politically correct, but the story here is about people in what you would call the West developing this. What about the Soviet Union? I mean, were there similar developments happening in the Soviet Union? Because in other fields of physics, there were this great cross-fertilization that happened in the 90s. There's a lot of them came over to the United States.
Yeah.
And they were, I mean, like the St. Petersburg School, the Landau School, these guys came over, except for Kitaev. Who else are the big players from that?
I think it was very tenuous. I think that, okay, I'll give you a few thoughts about that. I think that there were many Soviet physicists who found Bennett to be a baby, that teleportation was trivial. You know, why would you even bother writing down such a thing? That I think there was a bit of arrogance of that it was very unfancy, and so it couldn't really be of any interest. Any child could have written it down. So I think there was a bit of prejudice of that sort. I think that was not reflected by Holevo, who was a good, solid scientist and whose work was known in the West all along in the 70s and 80s. But I think, this timeline, as I said, it accelerated at some point quite fast. And I think that there was nobody, to my knowledge, in the Soviet Union who was sort of keeping up. Okay, and yes, Kitaev is somewhat of an exception. I mean, I know his background is condensed matter theory, but again, very eclectic. His famous early paper was about six-dimensional crystallography for quasicrystals. But how he then got into this, I actually don't really know the story.
I have a question.
Yeah.
So this is probably more speculative, but maybe a couple of decades down the line, what sort of problems do we have today that, if solved, would, the people who solve it would enter the pantheons of a pioneer? And secondly, no, I'm asking what are the open problems that are there? And also, do you think that quantum computing, increasingly now that the foundations are more or less established, is it going to be that anything revolutionary on the technology side, it's going to be like particle physics where really large collaborations are needed for making revolutionary breakthroughs?
Okay, now those are two separate questions. Okay. Now, the first question I would say, of course, I have no idea, but I'm certain that it's something that if we discussed it, most people would say, that's ridiculous, why are you even thinking about such a thing? It's either some kind of heresy or very in bad taste or something. I mean, how could it be otherwise? If it's something that's appealing and obvious, then somebody's already doing it, So I think there's no prescription for figuring out where the next sort of, quote, scientific breakthrough will come from. But as I said, I predict it'll come from the fringes, from some stuff that we don't find so appealing right now. Somebody working in the Trump White House who scribbles on the side. Somebody that we would not take seriously. We can't possibly take seriously. It's some from Doge or something. Some 19-year-old kid working for Musk. Who's busy firing people, and then on the side he's working on some little project. I think that's the way it's got to be. That.
No, I guess.
Now coming to your second question.
No, sorry. I guess maybe my question was, what sort of problems, not the people, more like what sort of problems would be like, would truly take quantum computing from where we are now to something that's more technologically relevant? Would that require large collaborations, or are there?
I thought you were asking what's the next, really just sort of pioneer thing to be done. But your second question, I thought, was mainly what you just said, what we're going to need to do to, get to bigger quantum computers. I think this large team scheme seems to be working. It seems like the average number of authors on the papers on the, leading quantum computers is, going past 200 at this point, and not just at one place. There's Google with 200 people, Microsoft with their own 200 people, Chinese Academy of Sciences, another 200 people, so all sorts of groups of 200 people in the world. I don't know if we'll then have to grow to 1,000 or something. I don't think the quantum computer won't have to be as big as CERN, although it's looking like it has to be pretty big.
Yeah. Hi. So one question I had, so there were people who were working on Bell tests, like testing Bell's inequality, and so were there any insights that were passed on, like even they would have known about non-orthogonal states and things like that? So,
well, I mean, I think that work turned out to be valuable in the sense that it produced the concept that you should, accurately diagnose quantum states. That you should make measurements and really determine what we now call entanglement. How much entanglement things have. Passing the threshold of a Bell inequality hasn't really looked like a very important one, actually, for quantum computing. That's you have to go to way higher degrees of entanglement to get really, get into the range of what's important and interesting for quantum gates. And I myself find that whole enterprise a bit sterile, That is that, just trying to close yet one more loophole is to me a kind of empty exercise, because I say, I get it, quantum mechanics works, you don't have to tell me more. I'm not seeking for loopholes. I don't think they're going to be there. But, as something that exercises and extends the experimental art, it certainly has had some value. Are we wrapping up here, or no?
Hello. Yeah.
Oh, no?
Very nice talk. Thank you very much. I just have one question. Peter Short's first paper, that factoring paper, he credits Benioff as the proposer of quantum computation, because that's a. So, what's your comment on that? And
okay. Well, indeed, I give a little bit of short shrift to Benioff, and he should be credited somewhat in parallel with Feynman, of seeing that in his case, in Benioff's case, the Turing machine could be realized within a quantum mechanical system, within a quantum mechanical evolution. And so that's what Benioff did. In my view, he, again, was one of the several workers who missed the story of superpositions and entanglement. He merely had the, as it turned out, ambition, but not at all not a strong enough ambition to use quantum mechanics for computation. He had the very modest ambition of checking that it could do regular computing, and that was about it. So, okay, but I don't remember with Shor, I don't think he had any special connection with Benioff, but maybe he read a few papers of his and said, okay, nice papers, which I wouldn't argue with.
I had one more comment. You said about 19-year-old coming up with an idea. I think thanks to Shrikar, he explained that BB84 protocol is very close to why nobody can play our best bowler Bumrah. Because it's just, it plays with this two axis, like the rotated axis. So
okay.
So I don't know. It can be 9 years also. Thank you. Idea.
Hello. Hi. Thanks for the great talk. So I noticed that you have completely dropped the 2022 Nobel laureates, and you've only included theorists.
Okay, let's see. You're mentioning, by now we have quite a few Nobel laureates who are in this line of work.
Yeah, the Zeilinger, Clauser.
Okay, because one can go back, the first Nobel Prize that actually, discussed quantum computing was the one of Harosh and Wineland. So indeed it honored rather quickly the work in ion traps, but for techniques in, both ion traps and neutral atom manipulations, single atom manipulations that were in the lab long before quantum computers, but which, have become very prominent techniques. Okay, now the three-person Nobel Prize of 2 years ago, whatever it was, Zeilinger, Clauser, and what's his name? Aspect, sorry. Indeed honors the examination or study in the lab of entangled states and of checking quantum non-locality. Again, not, a sister technology to quantum computing, but not by itself, one of quantum computing. But I should say Alain Aspect is very proud of saying that, I've launched the careers now of like 5 different people who are all in the mainstream of quantum computing, like neutral atom array experiments. He, feels himself to be a bit the godfather of that work.
Mm-hmm. The citation of that year's Nobel Prize says for the development of quantum technology. So I was curious.
Okay. I think the Nobel Foundation likes to try to make its prizes as, relevant looking or as, close as they can to what the ordinary human can relate to. And I think if they had said, for the disproof of the Bell inequalities, then it wouldn't have had as much traction as saying, we have a new technology here. But definitely those experiments by themselves did not constitute, a sort of endpoint of any real technology.
Okay, let's thank Professor David again for an extremely fascinating talk. I request Professor Arul to hand him a small memento as a
yes.
token of his...
I'm looking for the photographer here. Oh, I see. Yes. Okay.
Thank you.
Yes, and thank you. Okay.
Arvinda's taking a picture.
Oh, yes. Oh, the lighting is bad. Let's go up here then. There you go. Okay. With my water bottle. Oh, and well, then it's too bright for that, but never mind. Okay, and so now we're all to go back to dinner. No, well, no. Back to our banquet. What do you mean?
Thank you once again, David. Yeah.
These guys in Poland, they arrange every year this in-garden symposium. That's how I know about it.